पूरा सब स्लाइड ऊपर जाइए ऊपर जाइए। अच्छा मुझे स्टेज लाइट ऑफ चाहिए होगा फिर भी तो मैं नहीं ये लाइट रहेगा
ये ठीक है सर।
फर्स्ट होना चाहिए पूरा इंट्रोडक्शन ये दे दो वेरी नाइस ये इसका प्रोजेक्टर का राजेश जी प्रोजेक्टर नया दे नया दे क्या हुआ ये नॉट गुड इनफ इसका ब्राइटनेस कितना होता है प्रोजेक्ट $10 lakh it works hard but it doesn't say project लग रहा है you buy for leather it will go what's the reason
हाँ ओके ठीक है। सर का हाँ which one? It is TIFR semiconductor work. TIFR semiconductor work? Yeah. अच्छा ये प्रभु गोपाल फॉर बीएमए ये कि बीएमए रिवाइज्ड केएलएन TIFR semiconductor and there is sorry एक मिनट अभी फर्स्ट कॉपी एक मिनट just 1 minute let me see semiconductor with a historical perspective ये ना yes Day two of this meet. Yesterday, I think we had a very nice time, very nice lectures, and also a very nice cultural program in so today we have the three talks in the first session, and now we request Professor Vandana Mohan from UNIP to chair this session. Yeah, please, Vandana. Professor Vandana, yeah, please, all yours.
Thank you. So let me also add my words of welcome to this interesting meeting. We are also looking at various reminiscences and also gives us an opportunity to see all the developments so far. So we have three talks in this session. And as organizers have mentioned yesterday, there are no question answers. So the talks are 45 minutes. So the speaker will get warning after 40 minutes and expected to wrap up. I know the speakers have a lot of reminiscences and stories to tell, but advantage of finishing in 9 times, you will have more time in the feedback to spice up your stories. So our first speaker is Professor R. Nagarajan. When I joined, he was popularly known as Fast Nagarajan. So he started his research career in TIFR in 1964 at the one-year training school of BRC. At that time, it was called Atomic Energy Establishment. He is well known for his contributions to superconductivity, valence fluctuation in radiation intermetallics, instrumentation relating to Mosby spectroscopy, and enabling enhanced performance of low temperature facility of TIFR. He continues to be active and presently teaches at the Center for Excellence in Basic Sciences at Mumbai University. Because one more thing is well known for carrying chits in his wristwatch with all the jobs. And for those of you who may not know, there was also his isotope existed in TIFR. So now over to Professor Nagarajan.
You give me out about 20 minutes. Oh, fine. I'm not sure to go, so I want to talk 3 to 3 minutes. I need 10 minutes.
Okay, so I will tell you at 25 minutes.
Okay, so you are you help me? Yeah. Good morning. About 24 years ago, I gave a lecture in the very same auditorium on the occasion of Golden Jubilee of TIFR at 2012 and the Platinum Jubilee. Chairperson is Vandana Mohan. I think 30 years ago, I was the chairperson for the field exam committee of thesis. I think she was 20% student. Am I right? Yeah, good. Not bad memory. But the roles are reversed. She was the chairperson, but you have a less tougher job, I suppose. Except that you caution me, I will have to step around. So halfway through, give me a caution. Okay. Now, originally my topic was superconductivity, which I said well and good. I will do something on superconductivity. So I took it without reservation. When I discovered I got what went on in the arrangement, there's no one suspect speaking about condensed matter physics. Okay. So I felt it is my duty to see that the condensed matter activity of TIFR is represented reasonably. So I like to do. Okay, I'm not sure I've done justice to the matter. Another thing, considering this kind of audience, I am also likely to be informal. I understand that this lecture is being broadcast live on YouTube. Okay, and I'm not very good at this social media business. So I hope nothing wrong gets broadcast. What I would like to tell the organizers is that for archival purposes, I'll be happy to provide every time the hard copy of whatever I would like to say. with proper information, not that archival medicine, archival material, and not this YouTube, the problem happened today. Actually, the ideal person to talk on this occasion would have been certainly some phenomenon. Extraordinary kindness by the thesis, who has done extensive work. And Professor Ramakrishnan, who has made impactful work in the low temperature physics. Okay. What I done, I will present and give a talk due to their personal commitments. So I will try whatever I can. I do hope for Archival they would give the proper information. On an occasion like this, one likes to go back in time. And the first thing I went back in time was how I looked at 75 years ago. Of course, I was born before TIFR was born, and evidence exists of that in my home. But I don't have a good archival section in my home. So I went to TIFR archive and found what the oldest I can get, and that's what I would like to flash now. So that is how I was. The contrast is not good. So that's how I'm looking at. It reminds me of the then film hero Devanand. Okay, the next best thing is my oldest equipment. I do not know whether anybody wondered how old the equipment we have. I said I'm going to be a little random and so on. I said I don't know whether I'm talking about condensed matter physics or reminiscing my old experience. To repeat of archival, I'll give a proper material later. When Golden Jubilee TIFR was trying to set up an archival section, they brought some nice museum like that cupboard or whatever you want with the glass thing and so on, put a bulb inside, and they are putting inside the thing of our annual reports. I felt that's not really archival. Since many things I worked with my hands, I never leave them. So a lot of old things were around me. I said I'll give you. So one of the things I have put here, I guess would be the oldest one with the earliest accession number. This is a hair hygrometer. It is there. These things I have kept in the backs of the auditorium fire, nicely hidden behind posters. Whoever is curious can go and have a look. And it turns out that except for 3 items, 2 glass blowing things and one given to Professor Mathur, a small ion source gadget, all else are put by me, of which I will show one and mention about another one. Then I was just trying to see whether this technique has gone wholesale outdated, because now you have electronic sensors and so on. I find that there's considerable discussion in the website on the hair hygrometer, and even suggested on school experiment for that. People who are curious can go and look at that. So in that one, I put a tuning for oscillator. Crystal oscillator didn't exist at that time. We made our own proponent counter. I will flash a slide of the person who was behind all these things, very, very important person. And I put 4 generations of the counters, the gamma ray counters. Someone was mentioning yesterday, all our computation went with punch tape, punch cards, but mine was even earlier. I had a punch tape also there. And at that time, I put one slide rule also, borrowed from Professor Mathur. My own slide rule, I have kept that. There was no calculator except that time. And all these things you can see there. Now let me see what next I do. Where this pointer works from here? Or where is the detector for the pointer, please? Yeah. Anyway, my topic, I said, nuclear physics of superconductivity. It so happened that much of the origin here centered around nuclear activities. One was nuclear magnetic resonance, even though there was no radioactivity, the condensation of nuclear exists. Then the nuclear spectroscopy, which originally was originated for looking at the nuclear decays, etc. I am happy that Professor Pill will be giving me a talk after that. So whatever I am messing up, he will clean up during his talk. And then it turns out that when they have this angular correlation and its effect with the internal fields, become a solid state tool. Then of course, Mossbach spectroscopy, about which I'll say a few things. Also a nuclear tool. but was extensively used for solid state investigations. And so that is a nuclear origin. And therefore, what I will do is I'll start with the NMR because that was the fundamental thing. And then say a little bit about busbar spectroscopy, and then end my talk with three highlight contributions, because we said landmark. So maybe we are supposed to talk what are the landmark results that happened here. That is Professor Dharmati, and Hosur made my life easy by talking about him. Therefore, I'll skip this slide. This is from Vijay Raghavan, who followed Professor Dharmati. He built the first NMR spectrometer, I am told. Incidentally, Professor Vijay Raghavan is still active and with his daughter at US, and he is in touch with me more or less on daily basis. Part of this part was directed by me, so to speak. So he made the spectrometer himself. It seemed that they got a mag from Switzerland and then used war surplus to make the electronics, and detected sodium resonance, and he was very happy that he could see the sodium resonance in sodium hydroxide. Now, this is a slide which is little distant I have put because of the early day. Again, Hosur yesterday remarked that the MRI was declared on this very stage. And it so happened at that time, the NMR people, this is Chowgule whom you are seeing, and Kasturi was there at the time. He was also interested in biological sample. They were already investigating biological sample using NMR. And then the Nobel Prize winning scientist, Lauterbach, he visited the section and he seemed to appreciate it. Just before his talk, and then in the talk he declared his MRI. I think I saw a Google's write-up somewhere that his conference contribution actually was a poster to start with, and later on seeing the importance they convert into a plenary talk. Somebody can verify and confirm that this story is true. Okay, these are some of the early pioneers of NMR. Professor Gupta, Professor Malik, V. Nagarajan, he did zero field NMR. That is Chowgule, who was behind a lot of instrumentation and support activities in TIFR. At the earlier version, perhaps that 14 megahertz NMR spectrometer for the solid state investigations. Okay, this is a variant spectrometer which did a lot of NMR bulk activity. I have listed all the members of that time, okay. And since there was no other technique available, almost all of them were working on NMR for something or the other, the entire bunch. And the one which I put at the bottom, they were earlier and they left much earlier. DLR Shetty, V.S. Rao, Saraswati, Mungurwadi. B.K. Basu was working on ultrasonics because as a condensed matter, I just put it there. And many more I must have left out. Now, one of the earliest contributions from them was that one could see the s electron density at the nucleus, and then from there, then the polarization of d electron, and this, which in turn has effect on the s electron density. From there, one could detect the solid state property at the nucleus. Was an important thing in RPT5, and it is, I think, formed a part of Professor Malik's thesis. And this was done under direction of Professor Vijay Raghavan. So it's a very, very important work. The next important thing that happened, because I am on NMRs, I am jumping and skipping in time, was the NMR in copper nucleus, where at that time our interest had shifted to rare earth intermetallics, and this was days of the rare earth valence of cerium, europium, and ytterbium, shuttling between two valence states. And again, its effect on the copper nucleus could be seen, and is considered the first such example of solid state valence fluctuation seen through NMR. Therefore, this is a well-received result from TIFR. I think this formed a part of Sambat Kumaran thesis. Now come the point of condensed matter physics. It is Professor Vijay Raghavan who really took a lot of pain and interest in trying to make this condensed matter physics. At that time, it was called solid state physics, because only part of the activity that it established well and grew up. He had an extraordinary knack of getting people together and manage them. It is a special skill, part of which I think I have acquired from him. At that time, since yesterday, Professor Russo was mentioning, originally the group was called NEM, electron and nuclear magnetism. Then it got split into three. One went under Balu Venkatraman, chemical physics 1, one under Kanekar as chemical physics 2, and then the third one under Professor Raghavan as solid state physics. I didn't know when this department went, even though I was there. Pinto tells me it is 1997, when the then solid state electronics, and then we had a subsection called material science, and then solid state physics merged into the current department of condensed matter physics. Okay, since I talked of nucleus, I must also talk about my boss. I started my career in nuclear spectroscopy, and that was Professor Toser, who are the head there. Incidentally, Baba ensured that he gets prominent people who all worked with Nobel laureate. Dharmate worked with Felix Planck, this gentleman worked with Kai Sigman, and one more, which as I move along, I will tell you. So this group was established to study nuclear spectroscopy, beta ray spectroscopy, etc. But then around 1958, Mossberg discovered the famous effect. I'll skip the other detail there. And then in 1960, I think, Pound and Repka used Mossberg effect in confirming the Einstein's relativity, that the redshift and the gravitational field. That really pushed the thing very high in the popularity. And then it so happened that 14 kV radiation of iron, commonly occurring element, and you have huge number of iron compound. So Mossberg spectroscopy became very popular, and TIFR being in the forefront, he latched on to the Mossberg effect and did a lot of work. Interestingly, one finding which I find is around 1961. That's here. Now I discovered that this 26 kV gamma radiation can give you a Mossberg resonance in 161 dY, was done by S. Jha. This is not our solid state physics S.S. Jha, but there was an earlier one. He later left for US and did some work there. Now, because this work resonance is so popular, almost everybody was working on it. You can see a lot of lists there. Dr. Fatehli, whom I joined. This gentleman, Prahalad Sastry, I will tell later. So we too worked with him. Girish Chandra had one, R.P. Sharma had one, H.E. Devara had one, then K.R.P.M. Rao from chemical physics had one, which later on Date took over, which Hosur mentioned yesterday. Multan in material science. It's possible I might even left out one or two. K.G. Prasad, Vandana's boss, was working with R.P. Sharma. Now, I jumped to disjointly because when I'm on Mossberg spectroscopy, since I did a lot of work, I felt like reminiscing something about the equipment we had at that time. Cooling the sample was a problem. Ice was available. The next best was dry ice. Sardar Carbonics somewhere in Prabhadevi, we used to get dry ice and put chloroform or acetone and then go down to minus 27 or something and put the whole thermocol cryostat. BSF had just then come with thermocol. Okay, there's a constant mass per spectrometer mechanically moving. The whole thing will make a lot of noise and move till we manage with something. Then we had glass cryostat. I am sorry that I am not able to flash the complicated helium cryostat which are glass blower cooled. Incidentally, the glass blowing section of TIFR is a precious department of the institute. I do not know, the high energy physics people had told that the counters were made there. And these days, of course, the importance has gone down, except perhaps for sealing samples. I do not know how much work goes on there. I did take some photograph, but I couldn't incorporate in the one. And incidentally, there is one glass cryostat in the glass blowing section. I've asked them to preserve it I strongly request that that be shifted to archives and preserved. Then metal cold fingers, flow cryostats, and so on. Two of them I show, which are one of them actually more important. Yeah, incidentally, this gentleman is my very close friend. He, in the early days, people, as somebody mentioned, came from DRC training school. Maybe I came and 2 years more training school input was there after they stopped. He is a very good electronics person. He automated mass bar spectrometer, okay, and even had this glass diwar automatically filling a small diwar every 2 hours or so. Okay, very brave man. Okay, it's a wonderful thing. The mass bar spectrometer had become a speaker. There is a counter there. We will not go into that. The other one was equally complicated spectrometer cryostat. This one. See, KRPM, long Telugu name, Kallakuri Mallikarjun Rao. This is an interesting personality. He was my close colleague. I do not know. Anybody recognize him? Nobody would write. I don't think anybody would belong to that category.
He came to SSC.
Yeah, he came to Self-Alpha. Yeah, great. Good that at least one person remembers. See, so he is the one who was 3 years senior to me, Nishta Pahela Sastri. He could do anything as a genius, very rational scientist. This cryostat was design was published in Nuclear Instruments and Methods. Wonderful thing. You see, there are 3 chambers. They all hooked together with metallic stainless steel wires anchored. Okay, therefore the heat conduction is extremely small, and then it will suck helium from the other end and come out from here. It sucks the cold gas and does that helium crash. The sample sits there, and then this for taking the helium in, there is a stainless steel tube. Okay, there are no tube benders available. The magic stuff was machined in the workshop. Okay, but much of the welding was done in our lab. He even made a stand for it so we can rotate. We had acetylene, gas torch, everything in the lab. Probably we did in the mezzanine floor. Okay, CM30. And the tube benders, what he did, he took filled it, the thing with water, and dip it in helium, liquid nitrogen, it becomes ice, so it becomes solid. Then he bend it, and then heat it up, the water melts off, and use the tube. That is how the thing was done. Okay, wonderful technique. This cryostat I put in the archive, so you can have a look at that. It really, it developed a cold leak in the center, so I couldn't use for helium work, but this was my workhorse for nearly 20-25 years, till Professor Bate left TIFR, and his cryostat, which I'm showing you the next one, that we used later on. This is another flow cryostat, but this was imported. And this also has some memory, some electronics for which was a bit known. And Dinesh Sharma, I'm very happy, is here. Was an accomplice in the later part of it, getting into microprocessors. Incidentally, I can very happy to tell you that I grew with Intel. Intel started with 4-bit microprocessor, I think 8004 or something. Well, no, 4004. And then it was 8008, then 8080, then 8085, and so on and so forth. Charming memories. No tutorial, nothing existed. Everything was done from the manual. Thanks, Dinesh, for giving us that moral support. And here, there is a mass bar drive, which is not easy to see because of the contrast problem. And I owe this to Professor Pillai. I think if he's here next time, he will tell you. Because Devare brought a drawing from Groningen, I think. And then we machined it and constructed. Then I made some electronics. We one more slide, which I'll show you where you can see that better. And this became very popular. And many groups in India took that know-how. And I used to think I'm like Sankaracharya. There is a pitam in every part of the India, that south, north, west. Kashmir I didn't have, but it was there, including Professor C.N.R. lab. The other one, where Dinesh has a larger contribution. This picture is not for showing me, but this one, where I made the multi-channel analyzer. Incidentally, whenever these nuclear physics people do their nuclear spectroscopy, you have to see the energy. Therefore, to scan energy again. Essentially, they have what is called a multi-channel analyzer. The whole nuclear spectroscopy group had only one. And as you had seen so many names, all of them had to only one equipment. So they would go to BRC, read it and bring the thing back and then use that multi-channel, do that. And it will go from one room to another. Professor Vijay Raghavan used to call it, yes, that it is Dhampati going from one husband to another. Now, we are using our all our Mosbar data manually. I wish I had included that one. The process was to sit down almost the entire time of 10 hours and recording the thing. Okay, so if I have the permanent virtual material, I'll put that photo there. So we also used to sit late, and it so happened ESIL had made their first multi-channel laser, and that when this doping action takes place from one room to another room, it would break down. Okay, the engineers used to come and repair that, so I used to be with them and watch. Then I discovered what I wanted is a very small part of the whole thing. So I made my own, and that is sitting there. It was never enclosed in a box. It remained there. It served for me 20 years without problem. The triangle generator there, which was on a so-called prototype breadboard, it remained like 20 years. They all work. But the most important thing is the two wires going here and the socket here. You may not be able to see. I connected this by then. TIFR across Cyber 360, and some of the labs got terminals. So there was a nice gentleman by the name Dosadai. Okay, he was accomplished. So I said I will cheat the cyber computer by the keyboard signal. I break the keyboard outgoing signal. Then it connect the keyboard out to my data. So I could directly transmit data to central computer. Perhaps that was one of the first computer automated experiment that we had. It's one of the charming memories I have. Now that Vandana has warned me, I'll skip to the remaining and push through. Now we had by then the most active work. We had all become sort of condensed matter physics. Ramakrishnan had many interesting systems called charge density waves. Grover got into vortex dynamics, Malikandar, and a lot of interesting intermetallics and boroids. Some of them I would like to say. Nigam also had a Mosbar spectrometer. He made magnetoris, superconducting magnet. I would just like to flash through them. This is how the Mosbar spectrum looks like. The x-axis is velocity, which represent energy. You can see the resonance happening. In this system, another important system from TIFR, which attract a lot of international attention, is a compound called European Palladium 2 Silicon 2. This also became part of Sampath thesis. Now, an equivalent thing which came from Malik group, but of a different variety. If you can just go back, here the signal simply shift with temperature. Okay, this the valency remains fluctuating, and what you are seeing is the resonance is the average of the two valence states. Okay, it just keeps fluctuating right down to 84K, which what you are seeing. But here, the valency is fluctuating, but it starts separating out into two separate charge states, and so much that at low temperature, this divalent even magnetic ladder. This was a equally interesting system, which had a lot of international interest. You can see Professor Dhar there. Okay, now that this, if you want to do superconductivity, you have to have low temperature. That origin came from Professor Girish Chandra. He worked in Moscow State University. I am not sure that because Kapitsa, I find is also Moscow State University. Whether he worked at Kapitsa, I don't know, but certainly he worked in Kapitsa's lab. And he was the first man to produce millikelvin in India. Again, it had a nuclear connotation. Okay, some bit of history. When I talk about nuclear origin, it so happened that it was Dharmati who started the asking for the rather ordering the first helium liquefier. There's an archival letter from him to Saha. January to 1962, he says that if they want to depute their person to see how the thing is being installed, they are welcome. The other one is equally interesting. He informed Baba saying that helium has been produced in the plant. So this for information. Baba says, I have seen it. Then he says for record, where it went, I don't know. But it's an interesting way the administration worked that day. Now this is the helium liquefier development here. The plant I think I have wrongly labeled. The first plant was 3 liters per hour. The next plant they acquired was, I think, 10 liters per hour. The third one which you see is at 24 liters per hour. I think now they have 80 liters per hour flourishing. The important personalities I want to show here are Professor Nigam is here, the SC Agronomy engineer of LTF. This is Sekura. I want to come and say something a little more about him. Professor V. Nagarajan. These people were the ones who were handling the thing in the most critical time in the late 80s and beginning of 90s. Really, they had a hard time. Those condensed matter phases would have, but they tried their best to do that. And when I take over, it is this Sekura who was really not the person for me to do that. If Nigam is here, he would certify as the importance of Sekura. I want to use this occasion to propose that I would like to institute an award in his honor for a good technical person of TIFR. Okay, please remind me on that. Other one which is currently there. Pardon? Yeah, okay. I said that there's a mix up there. Actually, I want to put the Collins one, 3 liter, which got shifted up. So all that you will correct in your lecture. Yep. In fact, Pillai has been doing the same on everything and anything, let me tell you. It's a precious commodity in TIFR. Okay, this is how the helium progressed, because helium has been sort of lifeline for condensed matter phases. We keep talking about helium. Okay. Okay, this is Professor Gish Chandra's publication, DA Symposium 1965, where he reports achieving 10 millikelvin. Okay, I don't want to spend much time there. Okay, you can see, all I can tell you is that it is detected by nuclear orientation, and the value he quotes are here, 0.024 at this point, this is 0.01, okay, 10 millikelvin. These are set up with Professor Gish Chandra used, they are there for a very long time, and that is the electromagnet which he used. Incidentally, the technique is called adiabatic demagnetization. I don't have time to tell that. In fact, much of physics and technology I will not tell because the time is running short. I must project what happened. People who are interested can come and talk to me, or as I said, I am hoping to document them in hard copy. So here is a cryostat which used to move inside the magnet, then they would magnetize it and then switch off the magnet. Incidentally, they have to do it very carefully, I am told. It may take about 10 hours in this case. In the case of Ramke and microkelvin, it takes 2 days to pull the magnet down. Okay, so I'm not getting into those intricacies there. And one man who can tell you a lot of stories about it, we should call him sometime, T.S. Radhakrishnan. I don't know how many of you have seen him. He worked with Professor Mendelssohn, the great man who has written a book and it's there in the TIFR. People should read that who are interested. Quest for Absolute Zero, wonderful book. He visited and he invited him to Oxford, so he worked with him. And it so happened he also worked with Prabal, who was a microkelvinian at that time, and Ramke also visited him. So anybody want to know the histories of how low temperature was in his time, in the late 60s, Radhakrishnan the man, I am trying to get him invited for a conference which LTF is organizing. Now I am on to business now quickly. Some of the important thing that did, Professor Nigam made the first superconducting magnet. I think it is how much? 5 Tesla or 6 Tesla. Okay. And the thing is, it was hard work. I believe Pillai also would know, because after him, I think they also made 1 kilometer of neobium titanium manually wound. You have to wind it tightly, otherwise the windings will shift around and quench the magnet. But it was used and a lot of work has been done. Since I am supposed to show some physics also, I flashed this one. This lady is my colleague at Mumbai University, Radha. You may not know, I do not know whether she is in the audience. Yesterday she was there. Okay, the important thing as a piece of physics, later I'll talk about the so-called borocarbide. He can see this one the superconductivity goes up, so to speak, and then trying to die down and then again pick up. This is so-called re-entrant superconductivity, and that is what made this system bit famous, about which I'll flash a slide again later, hopefully. This is my friend C.R.K. Murthy, very, very important man for me, because I cut much of my thought processes discussing things with him. And he was a geophysicist who shifted to condensed matter physics because he was on rock magnetism. He made his own equipment. He worked with Blackett, early persons again, Professor Homi Baba sent him to London to work with him. And I put one of his equipment in the archive, I think, and see. Professor Grover, if he is here, would know that he used this equipment.
Did not work with Blackett, he worked in
Correct. No. The Blackett came, sorry. The Blackett was the inspiration for the whole affair because he was interested in continental drift. That was the idea, paleomagnetism. Grover, so you know, C.R.K. Murthy's your lecture is already over, so you may correct it in the hard copy, say anything more.
That is Khandala, which everyone wanted to visit.
Wonderful, yes, he is equally known. And there was some Pandu who used to make good upma, that much I know.
Yeah.
Okay, then come the STC. This is, I do not know whether I mixed up my slides. You may see it a little later. 1986, this high temperature superconducting revolution came up, where superconductor discovered at temperatures of liquid nitrogen. So people thought that everything going to change and a lot of money was being spent. Rajiv Gandhi offered 100 crores and Professor Siyanara was the chairman of the funding committee. It was split into two. Professor Ayangar was the chairman of the applied committee and Professor Vijayaraghavan was the chairman of the basic science committee. So a lot of money flew into TIFR. At that time, we acquired some equipment. So let me see whether I have those photographs here. Yeah. So we got a squid magnetometer of 5 Tesla, vibrant sample magnetometer at 12 Tesla. Then we have a PPMS, physical property measuring system, which could measure everything: AC susceptibility, heat capacity, resistivity, and maybe thermo EMF and so on and so forth. There was also a closed circuit refrigerator for AC susceptibility, which is missing in the slide. I don't think Professor Paulus got it out of the STSC funding, but since I couldn't get him in my sequence of event, but he had a dilution temperature much later, out of which a wonderful quantum Hall effect was result was produced. I think Professor Arora would mention in his talk. Okay, I may flash the result there. Yeah, beautiful. You can see. Okay, here comes Grover. He dedicated his life to vortex dynamics. He was in Japan. I think Ito dedicated one instrument to him. Was very happy because in TIFR would get turned once in a month. We had only one squid at that time. And he did work. I'm not really competent to comment everything. But what I want to present here is the amount of detailed work that Grover and Ramakrishnan did. See here the number of points. I think they were all taken. I think every maybe next one has a slide. 0.1 millikelvin accuracy, and every 10 millikelvin they had a point, something of that kind. Okay, see here, this one you can see the reduced temperature range 98, 97. That is just within 1% they cut, and then got this so-called purifier, out of which they would say how the vortex lattice is melting or solidifying and so on and so forth. This is what they said. They said they discovered Nelson's laws. See, this is a phase diagram, and that I do not know whether Grover could correct me. It goes from liquid to solid, and then it goes one way, and then again it returns back. So this is a so-called re-entrant business, which was a critical requirement for the existing theories then. While I'm at it, I want to talk about this two slides on material science, because a lot of activity went on at that time. Professor Multani started along with Patankar and my friend Shastri, whom I was saying. Okay, the Shastri end, actually, I skipped. I would like to use this occasion to say that he did a variety of things. He did most of spectroscopy. After it, he said, no, I want to change over. Then I think he went to here. And then he said this is not enough. Then he went to solid electronics. There he tried to make a calculator. I was accomplished for that. We had a calculator about a rack long. Okay, we did many things there. By then technology changed. DCM came with their compute calculator and then went off. Then he went to ESIL as a consultant for that. Then he went to Zambia for about 2 years on a teaching assignment. He came back as a Guruji. Finally, he's a full-fledged Guruji with international following. He has a institution called Devipuram in Visakhapatnam. Unfortunately, he passed away 3 years ago. But there's a big institution there who are religiously inclined. They can go and see the clip. The puzzle really for me is that how come a totally rational scientist could go totally differently spiritual and so on. And I tend to believe maybe there's something spiritual there. Okay, Vandana is further warning me. Let me rush through finally. Okay. Okay, now here is my the outcome of the material science. Since I am supposed to be on superconductivity, my present colleague at CBS, Sangeeta Bose, whom many of you know, Bhushan student, she worked on this fine particles and showed that the type 1 and type 2 behave differently when you make them into fine particle, about which I don't want to get in now. Now the finally will make maybe 2 minutes each on the 3 landmarks, because it's a landmark one. Director, I think at the time it was Sandeep Trivedi, he mentioned a lot of landmarks. In condensed matter physics, he mentioned 2. One, a work which with I was associated, the so-called quaternary borocarbide. Other one was the discovery of superconductivity by Ramke at 005, about 500 microkelvin. Sampath Kumaran, extensive work, okay, enormous work he had done, and he informs me that this compound is gaining international prominence. So I would like to say a few things about that. These 3, and then wind up. That is Sampath Kumaran's lab. He states that in this material, this is a comparison material, you can see an Hall effect taking place as the temperature is reduced. When the field is 0, the resistance goes up. Inside, not the resistance would come down. When you apply the field, the resistance comes down like a metal. This is like a superconductivity. When you have superconductivity, you have something in the heat capacity. When you apply field, superconductivity, it behaves normally. It does something crazy like that. And the net result is he got this anomalous Hall effect over this field range, okay, at 4.2 K. Now, this was somewhere in 1998, I think. Now, 2019, there's a paper on this very same material in Science, claiming that they have found topological Hall effect in frustrated triangular lattice magnet. The net crucial observation is the same, which I will flash in the next one. Yeah, you can see the similarity against magnetic field. So Sampath strongly feels that he should get the recognition for discovering this aspect, about which he has sent a CONMAT archive, which I reference, I have put there, you can see later. And the other important thing which I have done was discovering a material called terbium-2 barium cobalt oxygen 5, where we find this is temperature, this side is dielectric constant, and each one you are applying a field. You have a ferroelectric material which respond to application of magnetic field. These are called ferroelectrics, and this is happening at the highest temperature, and therefore he believes this will be an important material for application. These 2 must be noted. Now, there is a bismuth work of Ramke. How much time, madam, I have? 5 minutes. Chalo. So, the important thing is here, Ramke's work, I call it as a complete science, because number 1, he proposed the problem, he devised the technique to solve the problem, and solve the problem also. So, The entire thing he has done. And as I told in his farewell function, it really requires a lot of courage to sink that much money, that much time, that is effort. You must have spent about a decade just trying to achieve the microkelvin, which itself is an achievement. And then having done that, put bismuth in that, and then go and get measure and establish. Fantastic work, let me tell you. I will skip this slide because too many things there. This also I'll skip. This just shows the complexity of the setup. Okay. What are things sitting there? You have to have a 1K you achieve. Incidentally, he achieves the millikelvin by standard so-called dilution refrigerator. The remaining are designed and developed by him. You achieve the normal millikelvin or the other one, Girishchandra one, I said adiabatic demagnetization. We use a paramagnetic salt. Here we are doing adiabatic demagnetization on nuclear magnetic moments. Okay, nuclear magnetic moment. It is there they get cooled. Now the nuclear temperature should go to solid state temperature. That's a problem by itself. And he waits for, I think, 2 days before the solid can really get cooled. These are all technical detail. I don't want to get into that. He achieved 39 microkelvin. Fantastic thing. I think world about 4 magnets are there. 2 of them may not be working. So in that sense, we should really be happy that TIFR is doing their basic work. Now here is a basic result. You can see the superconductor occurring. Okay. It's about 0.5 millikelvin, 500 microkelvin. Simply getting a resistant drop incident, this is susceptible, not resistance. Okay, diamagnetic circuit you are seeing. Simply seeing a transition is not a proof. It should respond the way superconductor would do, which you do by applying field. Okay. Now, the other important thing you should see here is see the amount of field he is putting 4 microteslas, particles. Okay. I hope my number is right. And then that's such a small field, and you can see the thing shifting. And if you want to have an effect of this field, even the earth field should be shielded. So shielding magnetic field itself is another crazy thing in this setup. And he did all the thing. And what is the impact? He says that normal metals have roughly like 1 free electron per atom. Okay. In this case, the carrier density is so small, there's 1 electron about 10,000 atoms. Okay. The electrons are too few. For superconductivity, the electron must pair up. Such low density, 1 in 10,000, will they talk to each other and produce superconductivity? This is a question mark. So that is a problem which he has posed to the world. This is what it says. The results mark a new episode in the history of superconductivity. This is the editorial comment in the Science article. So now can I come to the final one? I kept it final because even if it doesn't say anything, nobody is going to complain. So there's a lot of teamwork. And Professor Gupta suggested that we should work for in the series of rare earth nickel for boron. And then we went into the whole business. Now these are the 2 students who really worked hard for that. This Chandran Majumdar, he is now a professor at science and nuclear physics. He is a professor at IIT Kanpur. He should have got more reward than what he got, but somehow field being what it is, it didn't work out. Part of the fault might have been mine. My favorite on this thing is just I said that the bismuth superconductivity had its own structure of science. I gave this talk once or twice. I tell them this is a classic case of a scientific discovery is made. I'm not going to tell all of them here. I only tell the steps. Choice of a favorable system, luck, systematic hard work, experience, literature survey, conjecture, verification, consolidation, killer instinct. Our friend Ramchandran Bajji, I believe, will be here. He is the one who wrote this saying that TIFR lack killer instinct. That story is later. Progress, birth of a subject. The work had all these components, classic case of, but then I'm not going to talk about it. What I'm happy about when I wrote this article in Current Science, editor seemed to have taken a note of it and he remarked in this editorial comment. So there is some truth in that. Now I'll quickly flash 1 or 2 slides and wind up. Okay, so this is how the whole thing started. We are measuring that one. We got a small cut here, but not zero. Susceptibility had a small variation, but not diamagnetism. When it went into low field, there was a diamagnetism. We said there is some superconducting signal, but we did not go into zero, what it is. So we went after it. Anything which you do, repeatability is important. We tried 4 samples. We did get them. But the interesting story is here, the first sample had a much larger dip, 1 to 0.7. Other guys are only 5%. Why so? I will not tell you now. This is for a graduate student lecture. Heat capacity is supposed to have a jump across the TC. Nothing happened here. Okay. Leave it at that. I hope people can see who are the authors. We went after it. I tried to crack what the problem was. Made all sorts of alloys. I felt it's an impurity. In 3 samples, we got this small signal, but still resistance was not going to 0. So I felt that the thing might be something else. I guessed it could be carbon. Why I guessed, I will not tell you now. How I got the carbon also is an interesting story. I will not tell you now. So once I put carbon, the resistance went to 0. Okay. So that was the proof that I got the thing solved. The final proof, you can see now the heat capacity anomaly in this sample becoming much larger. So we knew that the compound is YNA2, but we could not figure out what boron and carbon. Bell Lab cracked it 3 months later and found the compound to be B and C is 2:1. So they made the compound YNA to B2C. Now you can see the heat capacity jump going more. And when you make a single crystal, it becomes a classic superconductor with a straight jump, and you can do other calculations as well. So YNA to B2C was the one. Bell Lab made the whole series. They really made an impact. So there was so much, and the famous ITC came the first transient temperature report of Bednar's and Miller for 39 Kelvin. Okay. Nobody noticed for about a few months. Somebody picked it up and then it went to more than 90. The record was around 135 and the pressure 165 and so on. So anything new which is coming up is exciting. This phase replaced nickel by palladium. It went to 23K, which was highest for metals at that time. So nature said, with a new route to high TC. And then that became a whole news. Everybody went helter-skelter. All metal physicists went about melting sample. Now, as I said, this is going to the end of the step, which is called a birth of a subject. It found all sorts of things. I think about 40 compounds it forms with all sorts of properties. This is a list of compounds which others made, not we did not make it. And then the other interesting aspect was that this thing produced 3-4 compounds which are so-called magnetic superconductors, which I told you the re-entrant part. Okay. So the Physics Today article that this being a pie box for that. And then we had an international conference, NATO, to what should I say, compensate for the killing in war. They also hold scientific conferences. One was held on this discovery at Dresden, that I believe was really a climax for it. And now I'm coming to the last slide. So with that, I finish that one. I must mention something about the present one, which I learned from Professor Hosur yesterday. I listed the present, the bunch of people from the department, from the website. All I can say that I find that they are exploring new lands, and my best wishes to them to make new landmarks. Thank you, friends.
So thank you very much for this nostalgic journey. And as I said, maybe things in the last decade or so will be covered by somebody else later. So we move on. And next talk is by Professor R.G. Pillai. He is going to be talking about the accelerator developments. So he joined TIFR in 1974. In the previous talk, you already have heard his name referred to many times. So his research interests span many areas of physics, covering nuclear physics, accelerator physics, condensed matter physics, and material science. He set up the first national high purity germanium based high speed spectrometer for nuclear structure studies at TIFR and has played a major role in development of heavy ion superconducting linac accelerator at BRC TIFR Pelletron linac facility. So he was awarded IPM Murli M. Chobani Award in 2016 and was awarded prestigious DAE BRNS Rajaramanna Fellowship. So, so I will tell you also after 40 minutes, or you want a half time?
No, no half time. So Nagarajan has made my life somewhat easy. So I'll try to tell you something about the accelerator development from the history that I can trace up to, that I'm familiar with. Okay. Of course, it all culminated in the present accelerator facility that we have. So I'll describe that also to a somewhat of a detail. So, not working? That's not working.
Yes.
This is not working. It's working. Okay. So the earliest accelerator in TIFR, sorry, was the cascade generator. It's a 1 million volt open air machine. Okay. And this was installed in this campus in the year 1953, 1954. Okay. So the buildings were still under construction, but during those days, we didn't have to wait for any occupation certificate. So as the buildings were being built, you could actually quietly occupy and put your equipment into place. Okay. So this was actually installed in 53, 54. So it's a proton machine basically. So 1 million volts. So the cascade hall, which is still present, it was installed in the cascade. So it was an open air 1 million volt and accelerating protons. Okay. The advantage of the proton is that if you hit on light elements, you'll actually make neutrons if you have a nuclear reaction. And you could get a spectrum of broad energy spectrum of neutrons, or you could get monoenergic neutrons. So that is also relevant from the DAE fission programs and other. So the neutrons was also physics with neutrons also was being done, and that is also so the nuclear reactions group. Okay, at that time there were two groups: nuclear spectroscopy group, which Nagarajan mentioned. So that was headed by Professor Thoser, and I was part of nuclear spectroscopy group. And all of us registered with Thoser. So Kurup was the last student who was registered with Thoser. But by the time my turn came to register with Thoser, he was on the way out. He was retiring. So I was the first person who had to register with somebody other than Thoser. So the nuclear reactions group was headed by another gentleman called S.K. Bhattacharjee. Okay. And that was an independent thing, and they used the cascade generator. Okay. So they also dabbled at some point into condensed matter physics and so on, but not everybody, mostly. So there, the last person who did his PhD on the cascade generator was Amit Roy. Amit Roy and Deepan Varja. These two people were the last to use that machine. Okay. And then it was dismantled and then donated to Calicut University. I've seen this machine in Calicut University. It still exists, but it's too difficult and too expensive to keep it turning on. The people who took it, turned it on and used it, but those people have also retired. So now it is just a museum piece there. So it had a relevance to the DAE program. And Rajaraman was also part of the nuclear reactions group when he joined, because he joined TIFR. BRC did not exist at that time. It was probably just coming up. So that was the origin of the first accelerator. So S.K. Bhattacharjee was the nuclear reactions group head, and Thoser was the spectroscopy group head. So starting with this machine, at some point when in the 60s, Baba had decided that you should also go in for other heavier energies. So one proposal was to make the variable energy cyclotron at Calcutta, and associated with this was a proposal to buy a heavy ion machine to be installed in Bombay. Now, where exactly, whether TIFR or BRC, it ended up being at TIFR. Okay, so these things were actually envisaged by Baba in the 60s, and in the 60s the VCC was being made, homemade, and this was not so. And then we had to buy the machine. So because it was to buy the machine, it got very delayed, and we could do it only in the 80s. So so the Pelletron came in the 80s. So I'll describe that a little later. Okay. So this machine, once it was dismantled and sent off, then we built the Pelletron, adjacent to the cascade hall, and the cascade hall became the user beam hall for the Pelletron. So both the things are adjacent and in one corner of the institute. Apart from this activity, okay, there was also a micro engineering group, and they also built machines, but they built electron machines. Okay, so in the basement, there is one machine which was built by Professor RVS Sitaram. Okay, so this is a 3 MV electron linac, and then once they made this demonstration piece, then they started making compact machines and selling it, and actually initially not selling it, just giving it away. Okay, so the first machine they made was actually was sent to VCC Trivandrum for doing materials analysis using the X-rays. So the electron is you use it on a target and make Bremsstrahlung X-rays, and it's a very powerful X-ray source. And you use it for looking at metallic components and all that which you make to do to radiography of these things. So that was one of the earliest machine. The second machine which they made was a medical linac, and that was in PGI Chandigarh. Okay. Subsequently, they have shifted out of TIFR, and then they actually make these machines and give it to many places all over India. Okay, but they're not very good at commercializing it, so they're not able to compete with Varians and other places. But then they make actually good machines. Okay. So this is just another development which is happening in TIFR, in the basement, in the auditorium basement labs, well hidden from everybody. So let me come to the Pelletron. So once the project was envisaged that we should buy a machine, and then during those days foreign exchange also was limited, and then and BRC was always under some kind of sanction. So it was decided that we keep it in TIFR. Okay, so that's how it started. There was another machine at BRC, a Van de Graaff, which was already there, which was a 5 MV machine. Okay. So the Pelletron actually is a Van de Graaff itself. It's actually a design which is basically based on a Van de Graaff. But the Van de Graaff, when it was designed, used a rubber or an insulating charging belt to make the high voltage. This was what the design was. Okay, so that was the breakthrough came from a person called Professor Herb at Wisconsin. So he changed this rubber belt by using a nylon rope with metal beads on it. So he just made a mala of metal beads on a nylon rope, and you charge the beads. Don't charge the nylon. Okay, you go and charge an insulator, it is anyway bound to fail on you. Okay, so as soon as you charge the beads, then the charge which you deliver to the high voltage deck, okay, it becomes very stable and also larger in value. So you could actually make machines, and you could break through a regime of the order of million volts, which was what the Van de Graaff could do, to of the order of 10 million volts. Okay, of course, this technology also could not be upscaled too much. So if people wanted to make 20 million volt machines, it wouldn't operate at 20 million volts. Okay, so 14 million volts turns out to be an optimum. If you design for 14, you get 14. If you design for 10, actually you can get 12. But if you design for 20, you will have to struggle to get 18. So 14 was optimum for this particular technology. So we went in for a 14 million volts. Okay, so this project was approved in the 70s. Okay, though envisaged in the 60s, and then later it got sort of commissioned and built in the 80s. Okay, so today, of course, it is no longer a rope with beads looking like a mala. It's a proper chain with links, which are metal links, and bushings, which are nylon. Okay, and this whole thing is made very flexible, and then that's how the charging system works. Okay, so it's a modified Van de Graaff generator. Okay? And so because of this system of steel pellets which goes around, it derives its name, and it's called the Pelletron. So the Pelletron is nothing but the charging system. Name is derived from the charging system. Of course, people used to tease me and call this also the Pelletron at times. Okay, so this project, when it was proposed, it was 6 people, 3 from BRC and 3 from TIFR. So Sharmaji, Devare, SK Mitra, and MK Mehta, Kapoor, and Baba, who was then at BRC. Baba was actually the first training school batch, but he always worked with SK Bhattacharya at TIFR. Okay, so when this project got finally approved, he shifted to TIFR permanently, though he was always working in TIFR, but he was actually a member of BRC. So he shifted to TIFR permanently. So it became, at some point, it became 4 versus 2. Okay, But when this project was up envisaged, it was already clear to us at that time that the 14 million volt for doing nuclear physics had to be extended. So we had already thought of, these people had already thought of that they will actually add to this machine a superconducting linac booster, a heavy ion linac booster. And there were only two of the kind which were being made at that time in the world. Okay, it was still under construction. So they said that we should adopt that technology and make it. Okay, so this was already envisaged. Okay, so when this project was executed, they already made a hall for us to put the linac in. Of course, they had no clue what the linac will look like. I'll show you the hall later. It was a miserable hall, but then we managed to fit something in. So this was the era in which it was done. So this is P.K. Iyengar was director BRC and Srikantan was director TIFR. So this is, right now, at that point of time, all this was just vacant land. So and then it slowly became the accelerator building and that. So you had the tower, you also had a lab block, and it was linked to the cascade hall so that the cascade hall could be used as a beam hall. And then there was a mirror hall built on the other side, on the Casuarina side, which was designed to house the linac as and when it came. Okay. Well, so apart from that infrastructure of all the buildings, the project also provided a new air conditioning unit for the TIFR, a new substation for TIFR. So all that was bonus for TIFR. So it was inaugurated. It took nearly 8 years to commission the machine. So it was inaugurated. And by then the director had changed. It had become VC. Okay. The chairmen had changed. It had become M.R. Srinivasan. So once it was inaugurated, the users started using it. So essentially from 89, it was in use because December 30th, it was inaugurated. Okay, this is how the accelerator looks if you go inside the tank. Okay, so you actually see sections which are 1 million volt sections, and there are 14 such live sections. But since the accelerator is very tall, you also need to focus the beam and do diagnostics en route. So you also have a dead section. So you actually have 15 sections on each side, out of which 14 are live and 1 is dead. No voltage across it. And the machine as received in the 80s, today is actually quite different inside. So many things inside have also got changed. Okay. So this is just a cutaway view of the building. So you start with the negative ions, accelerate towards the 14 million volts, which is in the middle. And then when you're in the middle of the terminal, you get rid of the electrons by going through a foil. So the negative ion becomes a highly charged positive ion. And since the atom is already the ion is already quite fast, most of the light elements up to oxygen, you can actually get fully stripped. So you can get 8+ or the carbon 6+ and things like that. Okay, and that is re-accelerated in the second half of the machine. Okay, so this is actually the voltage is used twice. It's called a tandem accelerator, and because of the trick of stripping it once it is already fast enough and getting a highly charged ion on the way out, you actually get a much bigger utilization of the voltage than you would have just done if they stuck the ion source inside the voltage here in the terminal. Okay, and once you come down, you take the beam and give it to the cascade hall for using it for experiments, or shoot it into the superconducting linac side. So this was also since it was envisaged, this magnet was also designed and purchased in that fashion. So it can switch the beam in either of the two directions. Okay, so the next job was to build a superconducting linac. Okay, so by then Kurup and me had finished PhD, so the job was dumped on us. Okay, maybe this transparency should come first. Okay, so this was a project again jointly proposed by BRC and TIFR. Okay, so from TIFR side there was Professor Devare and Professor Sharma, and from the BRC side it was V.S. Ramurthy and Dr. Kapoor. So this was the team which proposed the thing. Since we had just finished our PhD and just employed in the institute as probably we were just RAs at that time. We were not even fellows. Okay, so we were too small a fry to be part of this senior gang, to be part of the project. So the dirty work was dumped on us, and we started with a very small number of people. Both of us went for a sabbatic, not for a postdoc at Stony Brook. So Stony Brook was one of the labs which was building us a linac booster, superconducting linac booster, And there was another booster which was being built at Argonne National Lab. So these are the two projects internationally which were doing, they were building a machine for heavy ions. Okay. So we went there to learn what they are doing and see it and then come back and implement. So let me go back to the thing. So how do you build a linac for heavy ions? Okay. For an electron, it was very easy because the electron is very light. So a little kick and it's relativistic. Okay. And once it's relativistic, it's traveling at close to velocity of light. And so if you have a radiation RF field, okay. So the RF field is also traveling at velocity of light. So the only job is to sit on the crest and ride with the wave. So your energy is transported, the electron gets accelerated by you sitting and riding on the wave, and you are at velocity of light, the wave is at velocity of light, no problems. Okay. But as soon as it becomes a heavy ion, okay, then you can never synchronize yourself with the electromagnetic wave. So the next best thing we do is build a cavity and put a standing wave inside the cavity. Okay. And once you have a standing wave inside the cavity, so you charge the two faces of a pillbox. So this will be positive and this will be, oops, sorry. So this will be positive and this is negative in one half cycle, and in the other half cycle, the charges transport themselves to the other side, and this negative comes here, positive goes there. So current is flowing up and down on the walls of the cavity, and the faces get charged back and forth. Okay. So when the voltage is in the right direction, okay, the voltage, the electric field is positive, and it's in opposite direction is negative. So you have to, first thing is, this is not a DC machine, it becomes an AC machine, and pulses or pulse of beam can be accelerated if it arrives at the crest when it is in the cavity. Okay. And you don't send beam at the rest of the time. Okay. So you send beam only in a burst, and that burst you synchronize with the crest. Okay. So it gets accelerated. But once it gets accelerated, it should now be synchronous when you come to the next cavity. But since the next cavity is an independent cavity, I can always time the RF field in the cavity to time with the arrival of the bunch. So a sequence of such independent cavities make an accelerator. That's basically the trick. Okay. So you don't have to worry about synchronization of yourself riding a wave, because you should be at the same velocity of the wave. You don't care. Now you come at whatever velocity you come. I can synchronize from one cavity to the next cavity independently. Okay. So this is basically the trick that we do. The other thing is that if you want a sizable electric field so that it behaves like a decent accelerator, okay, then the charging currents to make this voltage also becomes very high. Okay. So the cavities actually dissipate a lot of electrical energy. Okay. And this dissipation also you can overcome if you make it superconducting. Okay. So that's basically was the leap in technology. You make it cavities and you also make it superconducting. Okay. And this is what was the thing that we envisaged. And the particles which we are accelerating, since they are heavy ions in the periodic table, okay, the typical energy per mass number, that is MeV per nucleon, which you are interested, is in this pocket, 5 to 10 MeV per nucleon. Okay, and this was the number which comes from wanting to do nuclear physics. Okay, so if anything is lower, then you will now be able to overcome the repulsive force between two nucleus. Okay, so you have to be in this pocket. So this is roughly of the Coulomb repulsion that you see when you two nuclei try to come to each other. Okay, so that's roughly that pocket of energy. That's when you do nuclear physics. If you are much higher than that energy, then you smash the two nucleus and you get rubbish out of it. Okay, so then that's not nuclear physics. Okay, so we leave it to other people to do that. So basically, so this is the energy which is interest, and at this energy, the particles are of the order of 10% velocity of light. Just for an information. Okay. Okay. So we built the linac. We had to put it in the hall which already was built for us. Okay. So I will show that hall. So the linac, if you expand the word linac, it means linear accelerator. Okay. Now the hall which was built for us, we couldn't put the machine in a linear manner because we had done that, we had hit the sea. So we had to build a bend in the middle of the linac, and that actually complicated life quite a bit. So I'll just show you an exploded view of the linac hall. So it's a 15 meter by 15 meter hall. Everywhere it is 1 meter thick, excepting in the tunnel which connects to the Pelletron, where it is 1.5 meters thick. And since the hall is already a given hall, we had to fit the machine to the maximum capability. So we had to come in, take a kink towards the outer corner, and then bend back towards this. So we had to have a bend. And if you see the bin, it's also a complicated bin. It has multiple elements in it. And it occupies quite a sizable surface area of the hall. Okay. So the linac, we could put only 4 accelerating modules here and 3 accelerating modules here. We have one more cryostat here, which we call the buncher. I'll describe that as we go along. And then all the cryogenic system which cools the entire linac is kept in the middle of the hall. Okay. This is what is a cavity. This cavity was designed at Stony Brook, and you plate lead on this cavity. Okay. Now lead is one superconductor, elemental superconductor, which is superconducting at 4.2 Kelvin, because this TC of the lead is 7.2 Kelvin. The other element which we could have used was niobium, whose TC is 9.2 Kelvin, and that was being built at Argonne National. Niobium was a tougher technology. Okay, so between the lead technology, which is just electroplated, and the niobium, which had required much more complicated business to machine and weld and join and so on. Okay, that we said we will not enter into. But Delhi, IUSC Delhi, when they built their accelerator, they collaborated with Argonne National Lab and went in for niobium technology. Okay, but they took them longer to master that technology. So we thought the lead would be simpler, and we stuck to the lead technology. It turns out it doesn't matter, whichever you choose. But today, if somebody builds an accelerator, they will not build it with lead on copper. They will build it with niobium. Okay. So this was the thing. So this cavities was designed in Stony Brook. Okay, but we had to adopt that design for our purposes to be made locally. This material could not be was not made in India, so this had to be imported from Japan. Okay, and during those periods we were under heavy sanctions, so that also we had to struggle to get the high purity copper material. Okay, so we could not get it from Europe or anything. We had to get it from, so we got it from Japan. And a lot of this machining also had to be done at BRC, and they also had to learn how to handle this copper. So the very high purity copper is actually extremely soft. So if you scratch it with your nail, it will get scratched. Okay. So if you want to hold it in a lathe to machine it, if you see in a workshop, he will put it in the lathe and he'll crunch it till it is tight. But copper is soft, so it will keep oozing and oozing. So the more he crunches, the more it will ooze. Okay. So so even the workshop people have to learn how to handle such a soft material and do machining. And similarly, if you're trying to do a machining on a soft material, it behaves like chewing gum. So you want to cut something on a chewing gum, it doesn't work. It'll come out to be rough and miserable. Okay, so everything had to be over the learning process. So the welding copper is even tougher because it's a very good conductor of heat. So if you try to melt it, it will refuse to melt, and when it melts, it will boil like milk. So it will splatter everywhere. So even welding copper was a trick which we had to learn. Okay, so most of our failures in this cavity making was actually due to the welding. Okay, but we had to learn. We never threw away anything. So once it came from the BRC workshop, quietly take it into TIFR and do something and make it work. I will not explain what we do, but then we used to do something and make it work. Okay. So why superconductivity? Do we really gain, or it is just a fancy way of doing it? Okay. If you go from room temperature to liquid helium, of course, you have many other cryogenic steps which you could have also used, but there are no decent superconductors there. Okay. And as Nagarajan mentioned, you have these ITC superconductors, which actually in principle could have been used nitrogen and above. Of course, it was not yet invented when we were doing this. Okay. But even today, a high temperature superconductor is unfit for using in accelerators. Okay. It's a dirty superconductor. Okay. Because why? I'll explain. So the two superconductors which are useful to us is only lead and niobium. So the DC resistance goes to 0. Okay. So any of these 1, 2, 3 compounds or bismuth compounds and all that, they all will go to DC will be 0. Okay. But AC resistance is never 0 because when the RF is oscillating, the electrons have to know which direction to go. They can't be just going in any direction they like. So the electric field and the current density have to be parallel in some sense. There's a non-zero, which is not that the electric field and is 0 and the current density is present. So because I have to change direction. So the current has to follow the sense of the electric field. So E dot J is never 0. Okay. So that is why this has some kind of a resistance. Of course, if we compare it with copper, the surface resistance of copper at a typical RF field, RF frequency will be of the order of 10 milliohms. Whereas in the case of niobium or in the case of lead, they'll be nano-ohms. So there is a huge gain in the surface resistance. Okay, so the loss becomes very, very small. Okay, so that's the advantage that we use in when you go to superconducting. So if you look at the cavities which we make, okay, if we made it out of niobium and compared it with something which we make out of copper, okay, for the same accelerating field, suppose I want 500,000 volts per charge state or acceleration in each cavity, then it will cost me 50 kilowatt of RF energy per cavity. It will be an all India radio station per cavity. Okay. Whereas if I make it with lead, it will cost me only 5 watts. Lead being a slightly inferior of the two families of lead and niobium. If I made it out of niobium, it would have costed me only half a watt. Okay, so the electrical energy which I use to power up the cavities goes down tremendously by a factor of 10 to the 4 to 10 to the 5. Okay, compared to copper. Okay, and also copper, if I want to make 0.5 megavolts per charge state, it will cost me a lot of energy, but I can't even make a cavity to operate at that electric field because it will melt. So I'll have to distribute it over many cavities so that the power is distributed over many cavities. Okay, so the cavity, once I go superconducting, one gains on the real estate because the cavities go to higher electric fields, so I can make the whole linac smaller and compactly, and the whole machine is compact. Okay, but there is something which you pay for. You have to go cold. Okay, and to go cold, you have to make a refrigerator which is operating at 4 Kelvin. Okay, so but then the room temperature is 300 Kelvin, so this ratio is 75. So Carnap tells us that the ratio is 75. So for every 1 watt, I should use only 75 watts in the line power. It doesn't work. We typically use 750 watts in the line power. So it's like 1 in 1,000 rather than 1 in 75. So, but this is only 1 in 1,000, whereas I gained 1 in 10 to the 4 to 1 to the 10 to the 5. So the overall, I'm also extremely energy efficient when I go superconducting. So I make a smaller machine and it's also energy efficient. This is basically the trick of going superconducting. There is this pain of keeping everything cold. So when we started, I didn't include that picture. When we started, we actually, the LTF, when they shifted from the 1410, which was a chota machine, to 1620, which was a bigger machine when they bought. Okay, but 1410, we didn't throw it away. We took it to the linac and we tested everything with the 1410 and then we discarded it before we bought our own machine. Okay, so 4 such cavities make 1 module. So we use 4 such lead plated cavities go into 1 module, and we have 7 accelerating modules. And each cavity is capable of giving us, as per the design, 0.5 megavolt per charge state. So each cryostat gives us 2 megavolts per charge state. And if you have 7 modules, we get an additional 14 megavolts per charge state. So we actually double the energy of the pelletron. Okay, on a good day, we can actually triple it because then the charge state coming from the pelletron also can be increased by stripping the more electrons off the heavy ion. Okay, so it can be double to triple the energy that comes out from the pelletron. Okay, so that was sufficient to do interesting physics up to the range of heavy ions that we were interested. Okay. So once these cavities are put into place, the next step is how do I accelerate a bunched beam through this cavities? I have to first do a bunching. Okay, so I'll just explain that which you do. So this is a different kind of a cavity which we got from Stony Brook. Okay, actually we bought it from the persons who sold it to Stony Brook. Okay, so if you look at the hall, this is a 15 cross 15 meter hall, and it's only internally about 5 meters. Okay, and the accelerator, the beam line, is at a height. It is at 1.75 meters. It is not here, it is here. Okay, the reason being that you want equipment to come underneath, and you also want space to go from this side to that side. So it is always kept at height. So the beam line is actually 1.75 meters in height, and the hall is only 5 meters. So you have to lift everything, equipment, and bring it. So the whole thing was even from the headroom outside was crunched. So that also we had to cheat a little bit, quite a bit. Okay, and the tunnel was even shorter. So we could not put a quarter cavity here. Okay, so we had to put a small cavity. So hence we had to by what we call a split loop cavity. And this was what was used in the Stony Brook linac. So we bought one from there and we used this. So this is just to show you the cavity with before lead plating and after lead plating. And we use this to create bunches which are now accelerated through the linac. Okay. How do I bunch a beam? It's very easy actually. If you're driving on Marine Drive, you will find that when you start, all of us are at different speeds. So the guy who's faster catches up with the slower chap. So by the time you reach Chowpatty, we are all in one bunch. All the slow guys slow down, all the fast guys coming from behind, and everybody is in a bunch. It happens naturally. What you need to do is modulate velocity. So you take a chunk of DC beam. The guys who come early, you make them slow. And the guys who come late, you make them fast and let them go down Marine Drive. And by the time they reach over, they will be in a nice bunch. Okay, that's how you bunch it. But the linac cavity is operated at 150 megahertz. So the time period is only 6.6 nanoseconds. And you want to find yourself close to the crest. So the beam dynamics tells me that the bunch should be of the order of 100 to 200 picoseconds. Okay. So I have to modulate this velocity so that I can do the bunching and they'll catch up together. But this modulation is of the order of 1% of the mean beam energy. So if I have a mean beam energy coming from the Pelletron, which is of the order of 100 MeV, then I need 1 MeV modulation back and forth on the beam to be able to do this crunching to 100 picoseconds. Okay. Now to generate a 1 MeV acceleration requires me to use a superconducting cavity. I can't do it by a room temperature cavity. So that is why we use this cavity. So we call this the super buncher. So it's a superconducting buncher cavity. So it bunches the beam and makes it into 100 to 200 picoseconds. Okay, and then I have to shoot it through the accelerator. So I ride the crest of every cavity as I'm going along. And then I come to the mid bend of the linac. Okay, because I have to turn around and come out parallel to the sea. Okay, so we come to the mid bend. Now the mid bend is a very complicated beast. It has many magnets, many elements, vacuum systems, power supplies, water cooling, all kinds of things. Okay, and a bending magnet is nasty business. Now I have modulated the velocity. So I have modulated the velocity so that it is about 1 MeV on a 100 MeV beam. I send it to a magnet. Magnet, high energy, this will be low energy that way. It will disperse everything. So everything will be lost. Even if I come monochromatic, if I have come in and I come with the benched beam. I come with a benched beam all at the same time and monochromatic. So that there should not be any variation. But when I go to magnet, some people go this way, some people go that way, they take different orbits. Okay. So when I emerge from the magnet, the bunch will get spread out in time. So I have to make the bend isochronous and achromatic. And that is why it requires this 2 pairs of magnets. So the first magnet does damage, second magnet undamages. Okay. And so if you look at all the high energy magnets, synchrotrons, and so on and so forth, let's see, everywhere, every corner will always be a pair of magnets with lenses, so that the first magnet damages, second magnet undamages, so that you can, it's a mirror symmetric bend corner. Okay. So that is why we end up by being this huge magnets, pair of magnets is a lot of things. So you not only have to make it achromatic and isochronous across the bend, you also want to have unit magnification, because I left the first half of the linac and I was pretend I never bent. I must go to the second half of the linac. So I must have unit magnification. I must also have unit angle magnification, so that the beam goes through exactly as if the bend never existed. Okay. Now this is very complicated, but it's luckily for us, EM theory allows you to do this like it. So you can do mirror symmetric bending magnet. So this we have to design and also crunch it so that it does not occupy too much space. So if you were in RRCAD, a generous space, the linac, the bend itself would have been 15 × 15 meters. But we have to crunch it to something like maybe 3 meters by 3 meters. So it was all very complicated. So this we had to, so we cursed Sharmaji and Devare and all for building a hall, which was almost unsuitable. So the next step was to cool everything down. So we bought, so initially, as I said, we tested it with the 1410, which was discarded by the LTF. Then later we bought our own machine. So this was bought from Switzerland. So it's the make is Linde. So the Germans, Linde multinational, had already taken over what was called Sulzers in Switzerland. So we bought this. We placed the order in 1998. And once it came, we started using it for the linac. But in between, about 10 years down the line, after we bought it, the LTO bought a new machine, which we mentioned, 80 liters per hour. But if you go and look at that machine, it was vastly different from the machine which we had, because technology had evolved quite a bit in the 10 years. So then I told the manufacturers, I also want to upgrade my machine. They said, send it back to Switzerland. I said, nothing doing. It's inside the hall. We cannot take it out and send it to Switzerland. You send me all the goodies, we will do it. They were most reluctant. They said, lousy technology in India. They said, nothing doing. You send it. We'll match. So we opened the cold house, hacked everything. So by then the cost of the machine was something like 12 crores, but we were brave enough to open it, do it, and then retrofit it back. Nobody will dare to do such a thing. 12 crore machine, you cut open and do it. So we did it, and we upgraded this machine so that it became same technology as the LTF machine. Okay. So now the cryogenics is completely stable. You turn it on, and you don't have to pay attention till a power failure hits you. And when you run the linac, as Vandana will tell you, when the linac is running, there will invariably be a power failure. It also has to be transported. So all these transport lines for the liquid helium, liquid nitrogen, everything was made in situ by our workshop people. Okay. Then we also have to control these cavities. As I mentioned, the Q of these cavities is very, very large, 10 to the 8 to 10 to the 9. So when it is oscillating at 150 megahertz, the intrinsic bandwidth is less than a hertz. So it's 1 part in 10 to the 9. Okay. And you have to match all the cavities so that they all operate at the same frequency. So most of our gadis and all, there is great difficulty at 10 to the 1 part in 10 to the 6. And this you have to do 1 part in 10 to the 9. Okay. So there are tricks to do it. So this circuit was developed. Of course, it's not an invention, but once you develop this circuit using the electronics division at BLC, made it. Okay. This was also sold by electronics division to USC Delhi and also to Canberra later. Okay. So where they were building their linacs. Okay. So this was something. So we imported all the components. Very few components we could get from Bharat Electronics. Some RF amplifiers, attenuators, some things we could get, but majority we had to import. Okay. So this was it was again a development which we had to do ourselves. Okay. Then there was also power amplifiers, but power amplifiers at 150 megahertz, we got it made at Bell. Okay. It turns out that 150 megahertz also is a military communication band. So most of the RF thing was sort of auto syllabus for buying. So we had to do a lot of back bending to get these amplifiers made and so on. And then you have to have a control system. You have to have a control system to connect everything. So you need a local control system so that you can actually stand in front of things and turn it on. But you're also running it as an accelerator from a control room. So you also have to have everything. So this was again developed by the electronics division and nuclear physics division. And many of the other things like power supplies, cryogenics, all these also had to be dual control from the master control room, also from the inside. Okay. So most of these things also were done by people from TIFR. Okay. So there was a lot of work to be done and all this had to be integrated. Now we are trying to do an upgrade of this business so that it looks even better than what is currently operating. Okay. And there are many, many pieces of hardware which we had to make at the TIFR workshop. Okay. So these are vacuum systems made at the TIFR workshop. These are beam diagnostic equipments made at TIFR workshop and later made by a company which is a breakaway from TIFR. Something called Excel Instruments, so there's a PI and so on. So then all these beam lines, for example, all these vacuum pipes lines and all that had to be made in the workshop. So many of these things, and this is the hall. So we got stuck. We made this part in 2002 and got it operational, and we started doing experiments here. So Professor Zhao, the director, said, "You start using it. Forget about this hall for the time being, because of the sea and the change in environmental rules, coastal regulatory zones. This hall we had to wait because we had to go to Delhi for clearance. So Kurup and Saha used to keep going to Delhi for clearance, and I used to do the donkey work here. So finally we got this clearance for building this hall after a 5-year wait. So once the hall was built, we made everything. So by then Vandana had also joined. So she was instrumental in this entire hall. The experiment and all the beam lines and all that, this was her responsibility. My responsibility stopped at this wall. So this is the view of the halls when they are populated with experiments. So we artificially partitioned this hall using radiation shielding walls into 2 halls, so that when experiments are going on there, people can work here, and when experiments are going on here, people can work there. Okay, so it was artificially segregated by building these walls. And of course, when the building was being built, okay, the civil engineer said nothing doing. You have to tell me where the weight is coming. Now these halls, these are 1 meter thick concrete things which are about 4 meters tall. So that's a huge loading. So they wanted to put piling wherever this thing. So we had to think before the building was built, where what will come. So that they could put extra piles, because BRC is a factor of 8 safety. Factor of 2 safety is more than enough, but then factor of 2 will not work. So another factor of 2. Then for the crew, another factor of 2. So factor of 8. So the whole thing had to be designed, a thought process well before we could actually implement it. Okay. Okay. So this is how the linac looks today. So the first half, which has 3 cryostats, acceleration, 4 cryostats with all the transfer lines and all that which you see. The power amplifies, power supplies for all kinds of magnets. And then in the distance, you can see the superbuncher cavity. So this was this whole thing was by and large made here, excepting for the liquefier which we had to purchase. Okay, everything else we either made everything in-house. Hard work. And in fact, most people used to tease us that it will never happen. But we did it. And so the first half was commissioned in 2002. So in September 2002, actually, we celebrated 20 years of the linac. Okay. And the second half was commissioned in 5 years later, once the hall was built, the new hall was built. And so of course, there are lots of people who helped us. So in 98, when we were busy with the linac, Professor Jha made me chairman of the Scientific and Engineering Services Committee, much to my dislike. I said, no, I don't want to do it. He said, no, do it. But that was very helpful, because then I could drive the central services and the workshop guys and get my work done at a high priority. Okay. Of course, there was also stuff, BRC people also, a lot of division in BRC also, which helped us. And all the vendors were also very cooperative. Okay. So this was the inauguration of the thing in the first phase. So Jha was the director at that time, and Kakotkar was the chairman. This is Sudha Bhave, who was the JS R&D at that time. She was friendly with TIFR. Subsequent JS R&Ds have become decreasingly less friendly with TIFR. Then when we inaugurated the full linac, it was the chairman was Banerjee and Mustansir was the director. Okay. And whenever there is a visitors who come to TIFR, that is one beast which is taken for showing. So you show people the Pelletron accelerator and the linac. Thank you.
Thank you, Professor Pillai, for a nice and well-timed talk. We move on now to the last talk of the session, which will be given by Professor G. Ravindra Kumar. He is a distinguished professor of Nuclear and Atomic Physics Department. Is well known for his research on ultra-short pulse and warm dense matter. He is an elected fellow of Indian Academy of Sciences and Indian National Science Academy. He was awarded Shanti Swarup Bhatnagar Prize for his science and technology contributions in physical sciences in 2003. He is also a recipient of BM Birla Science Prize and Infosys Prize. So, Professor Ravindra Kumar. You're starting with a blank slide.
Yeah.
When do you
On
want the
karne.
warning? When do you want the warning?
40 minutes should be.
No.
Good morning, and thank you for being here. So this talk is not about a department, it's not about an activity. It's about lots of activities, and it was a huge challenge for me, because it doesn't have, the way I saw it, a long history. And whatever history is there, I had to make my own version of the history. And so this is, with due apologies, this is what I thought of this topic, which is listed, as you will see shortly. Lots of things here are to tell you that this is a story of, at TIFR, of light from fundamentals to extremes. I think at the end of it, I'll flash this slide again, and maybe you can see how much of justice has been made to whatever I showed here, the different pieces that you have on your screen right now. So, well, this is, I think everybody says this, so I must say my piece. My motivations were to trace the evolution of activities, most importantly, people and events, right? And you will see how this evolution of people through the slides that I'll show you. And the thing was about searching for common themes. Since I said this is not one group activity, a small activity in a department, what was it that was common among all these things that we will talk about? And how did this happen? People separated across different groups, came together to make things happen. And what was that kind of, what drove them, what brought them together? Hopefully we'll capture some of that. And the caveats are, of course, that this topic overlaps with several other things. Yesterday, Professor Hosu stole some of my thunder by talking about what happened in chemistry using light. But I think I'll give my own take on it. And so cannot cover everything because I, have my own limitations of what I understand of these activities. And the story is much briefer than the others because it is not like cosmic rays, particle physics, which started very early on, but it's about 4 decades old. So roughly about half the time that we are celebrating, half of 75 years. And getting archival material proved a big challenge. I gathered whatever I could and I put it together, but I wish I had got more. And the apologies are, of course, because I just chose activities and probably caused a lot of offense. But, I am sorry that if I missed out some things that need to be equally celebrated, but we cannot cover everything. And just to illustrate these themes, I have picked up activities. So if you look at light, it's presumptuous to say for one person how the field has evolved, the entire field of optics, light, photonics has evolved. It's been at least some of the major goals that we have had are to look at scales which are extraordinarily small, never thought of before, right? And at the same time, spread into larger and larger regions in a different scale. Maybe length scale, we are talking about extraordinarily small. Time, we talk of extraordinarily small. But on the other hand, the spectral region that we have covered has just bloomed like anything. We can now produce, we had traditionally microwave, radio, all these sources. There was a huge terahertz desert, and the desert has been blooming for the last 2 decades or so, 2 or 3 decades, and more so in the recent past. And so we have covered, and now we go all the way up to hard X-rays. So the spectral region that we cover is enormous now. And so we have been trying to look at the fastest possible events, the smallest length scales that we can, and very, very fundamental processes. And also, as I said, what were considered barriers early on have been overcome in the last 2 decades or so. So you have the diffraction limit, which has been broken, and I'll give you one example of that right here at TIFR. And so this have actually, the fact that we have broken the barriers have unleashed, this has unleashed so much of new discoveries, so many new things have happened that it's very difficult to capture. So this is my own take on how optics, so fast scales, large spectra, then fast scales in time, small scales in length, and huge leaps in fundamental science and imaging, which has also led to leaps in fundamental science. So there's been a major revolution in imaging, the way we see things, where they happen, as they happen, right? And so we can make sense of how these things are happening. So TIFR always did things differently, and that I don't think I need to say it louder in this room. While the rest of the country, IIT Kanpur started in the 60s with lasers, but they just went on chasing this continuous wave laser, that continuous wave laser, building more lasers, doing frequency domain spectroscopy with them. But TIFR chose to enter the ultra short domain. And as it turned out, well, it's fortunate that TIFR can do all this, that in the mid-80s, while the technology was still just becoming mature or accessible, TIFR got the probably 2 systems of the state-of-the-art ultra-short lasers at that time, which were picosecond duration. So let me tell you what fundamentals that we talk about. So this is a picture. Look at it carefully. I call this a historical event, right? 1987 Lonavala conference, and Mahendra Jadhav was just referring to this in the morning when I met him at the tea. And this is several luminaries of the field who were already beginning to be luminaries and later became bigger luminaries here and elsewhere. People like Graham Fleming, who's a very famous chemist, ultra-fast dynamics person, he's here. Robin Hochstrasser, I think, who is Sudipta Maiti's advisor, he's here, and several TIFR people. I'd like you to particularly pay attention to Dorai here, whose picture I have not found separately, but he appears only in this picture. So all of them are standing celebrating the ultra-short conference at Lonavala. And out came 2 volumes of what was discussed at this meeting, fast chemical processes in molecular state, free molecules or smaller systems, and then again in the condensed state. So what you see here, the pictures of the laser, the kind of lasers that were available at that time. I think there's a CPM dye laser, colliding pulse mode lock dye laser, and then various decay scales here, which are all referring to something like nanosecond, sub-nanosecond, with the fastest detectors that they could access at that time. And the people who made these things happen are all here. Balu, GK, Ranjan Das, Sanjay, Peryaswamy, and Doraiswamy, whose solo picture I just could not find. I saw one picture of him with the microwave setup yesterday. He actually came from microwaves to the visible and infrared region. So that, apologies for that, but the rest of them are all here. And I'm glad to see GK is here, and Sanjay is busy with his daughter's wedding, as was mentioned yesterday. And so what happened in the 80s with these lasers? So again, basic processes about, for example, you have molecular dynamics happening in a solvent, which is something that all chemists worry about all the time. And the fastest, what scales do these molecules actually move at? And this business of molecules rotating inside a liquid, how fast does it happen? What is it controlled by? Things like viscosity, right? And the orientational dynamics actually give you all this information. And I recall vaguely that they were talking about Debye-Smoluchowski equation, how that can be verified with this, and so on and so forth. And so this is I think there were papers before that, but I just picked this up because this is a representative, it's a somewhat of a classic paper on the kind of work that was actually going on. And again, diffusion control reactions, transient effects, and all these things were done by looking at the fluorescence that comes from these molecules as they tumble around inside the liquids. So controlling reaction, how these reactions happen and how the fluorescence signal gives you information on that. So I'm not an expert, but this is the kind of broad thing that I get. And you look at the decay scale here, it's just about a few nanoseconds for those who cannot see. And so this is ultra-fast decay scales of fluorescence as given by those times. And in the 90s, Sanjay entered chemical physics and he brought his own flavor. He started this jet beam spectroscopy, supersonic jets, which actually cool the molecules so that you can look at the details of the, the substructures that you get in molecular spectroscopy. And as it turned out, he eventually branched out into looking at bond formation. I think Sanjay's major work has been on how the hydrogen bond manifests itself in different environments, the nature of the hydrogen bond itself. And in this, he has done a lot of work and on which he gave several colloquia at the Institute. So simply put, so this is gas phase spectroscopy, unconditional hydrogen bonds. I will not talk too much about it. I do not know much. But one of the things that Sanjay did was he also introduced things like, apart from fluorescence, ionization spectroscopy, resonance ionization, where you actually ionize the thing and pick the particles very, very cleanly, you can track them very, very nicely. And so that he did in something called resonance enhanced multiphoton ionization with the nanosecond laser setup that along with the supersonic beams that he managed to set up in a small room. In fact, I recall that he actually converted a toilet part of the toilet, he actually took over into the lab in the B block, first floor, the ground floor. And now, as it turns out, that has gone back to being a toilet after Sanjay retired a couple of years ago. So, and things were happening because people were talking. And that's again another unique thing about TIFR, that we talk, this one building which brings lots of people together, makes them collide. Even if they don't like each other, they have to see each other. And sometimes the barriers can be overcome and good things happen, right? So these are people, of course, who got along very famously across barriers also, even geographical. This is GK's work, sitting here, but collaborating very actively with Jayant Udgaonkar at TIFR NCBS. And I'm glad to see Swami is here. I told him I'll flash his name. So Swami, please put your hand up. And so this is high profile work which happened. You can look at the kind of things. Buried tryptophan reveals the presence of partially structured forms during denaturation of bar star. And I think there's a lot of story about bar star that happened that GK can tell you. And all these techniques were because of fluorescence, resonance, energy transfer, something that they call FRET, right? So a lot of fretting about what happens in these systems. And the good thing about TIFR is also that you see Deepak Dhar, not only for sand piles and abelian sand piles, whatever that is, but also for real things like proteins, right? And this is a paper that GK explained to me long ago, saying that, how the collaboration was so exciting that when they took the data to Deepak Dhar, he sort of cleaned up the whole stuff and said, this is the essential thing that we must look at. And then they wrote this celebrated paper in PNAS. So this is, I think, something that we ought to preserve, no matter how big we grow. The fact that people can come together and do things across departments, across expertise, areas, and so on. So simultaneously with the chemists, the physicists were not to be left behind. So solid state electronics, as it was known at that time, Arvind Vengulekar, Gopal and Prabhu, who is now, Prabhu, where are you? Yeah, right here. So he's in the front seat. Okay, good. So Prabhu beaming there, and now Gopal has moved on to new things, bigger things, but he still does a lot of research here. So this is about, you're talking about dynamics in molecules, but around the 80s, everybody was looking at semiconductors. In fact, I recall Jagdeep Shah from IBM used to come regularly here, and there was a very active collaboration with IBM on understanding the basic decay processes in a semiconductor. And this is about, quantum wells or barriers in semiconductors. How fast do these particles move? Very crucial for electronics, making devices of all sorts. And that happened in TIFR using, and these particles called excitons. All of us know what excitons are. But the dynamics of excitons is a problem that really interested a lot of semiconductor physicists, continues to interest them for a long, for as long as these semiconductors have existed. And the first studies of these dynamics were actually, these are among the first that were done. And very proud to say that, this paper appeared. It used to be very difficult to get into PRL those days. But this is one of those papers that managed to break through the barriers. And a very great piece of work. And while investigating dynamics, of course, there was another revolution that was going on. Condensed matter has benefited from fabrication technologies that were made, that were evolved, that were built, developed for making very smaller scale devices, nanoscale and microscale devices. And now these fabrication techniques, as we realize, have led to lots of new materials. For example, the whole field of metamaterials, which is negative refractive index, or the ability that you can shape refractive index profiles the way you want, has all happened because of this, the fact that you can take those fabrication techniques from the industry and implement them to make new materials in the lab. Look at this, so many papers all done at TIFR. So this is the kind of the power of the fabrication technologies, and I'm happy to say that TIFR managed to keep pace with time. And I think we have very good fabrication, the nano fab it's called. And I believe it should be raised to the next level by the time the next plan comes up. So I'm encouraging them to go for a state-of-the-art machine that can keep up this lead. So high-profile papers again, driven by Gopal and collaborators. about magneto-optical effects in plasmonic crystals. Plasmonic crystals are again a class of materials which are built by this nanotechnology fabrication processes. And the fact, more details, of course, you can talk to the experts, but just applying very, very small magnetic fields, Gopal and Co showed that you can actually have enhanced transmission through these structures. So these structures have dispersion relations, they have gaps, they have all sorts of things that you can talk to the experts about. But the fact that you can control these properties by structure and applying small external fields is something very, very exciting. And that is continuing to be pushed by these groups here. And Prabhu comes back from a postdoc and changes whole direction. He was earlier looking at dynamics. Now he decides to enter to bloom the terahertz desert. And the blooming happened right in the C block second floor. That's where the seeds were planted. And I'm glad to say that he has made tremendous advances, not only here, but is also helping lots of labs around the country to develop terahertz technologies. And these are devices where I believe he's also helping the country in interesting and important ways, where he makes these devices on a small scale, large arrays of them to produce a large amount of terahertz power, and for various applications, both in basic science, in strategic areas, and so on and so forth. So all power to him, and more terahertz as he moves on. And simultaneously, Arnab entered late 90s, and he pushed the optoelectronic systems. I will not talk much about it, probably because Aroraji might say things. But these were again devices or materials which are extremely important for semiconductor, optoelectronics, lasers, and so on and so forth. So this is again fantastic work. And the last thing, when gallium nitride became very popular, and I think TIFR was very quickly on that, and they also made several interesting gallium nitride devices, the blue diode lasers. So let's come to, that was all about dynamics and spectroscopy and stuff like that. Now, back to chemistry. Sudipto, 1998, he enters, and Sudipto has done, as I said, Robin Hoekstra, who was in that 1987 picture, was his PhD advisor, and is for Cornell, he goes to Cornell for a postdoc, works with a guy called W.W. Webb, right? It's true, please Google, I'm not joking. What Webb is the short name. So what Webb, I do not know, but Sudipto at Cornell, along with Webb, pioneered the multiphoton spectroscopy. I think just at the time it was happening, he happened to be there, and they wrote one of those seminal papers in Science on this multiphoton spectroscopy. And he comes here, partly I am to blame because I championed TIFR, and I don't know, he still, whether he blames me for it, but I don't think so. He has done very well here. So Sudipto and Co. use this multiphoton microscopy to great use. I mean, he used it to such a striking effect that he actually imaged the serotonin and dopamine in neuronal cells and built India's first multiphoton microscope just about 4 years after he came in 2002, right? So that's just something that is dramatic. He can now image these things inside cells, the concentrations of these things using multiphoton microscopy. And that has several advantages. It breaks through several barriers. And so I had something else. Yeah, so high resolution imaging. And then he also works on a very interesting problem, this Alzheimer's, which is supposed to be in my limited understanding. It's because of protein aggregation in the brain. So he actually has been investigating this for a long time, looking at aggregation, how this aggregation happens, how do you sense where this aggregation is happening, and so on. And again, wonderful collaboration across NMR, laser, multiphoton imaging, and so on and so forth. And a very powerful paper came in Angevant Chemie that really made a mark for itself. He also made devices, like Prabhu, he is also helping other people in India build up these devices. In fact, as Professor Hosu said yesterday, he conducts regular workshops where people come here, all the materials are provided, he knows where to bring all this, the items from, the components from, and they build and they take these microscopes back. The fluorescence correlation microscopes are actually, spectrometers are taken to individual labs after this workshop is held. And he helps them beyond that to see what kind of, if they have any problem and so on. So he has spread the fluorescence correlation spectrometry widely in this country. I'll have a little thing to say about the device that you're seeing here shortly. So designing drugs, so more of the same, using these tools to great effect to design drugs now. So all using single molecule techniques. And Jyotishman Dasgupta, 10 years later, enters and now takes it in a different direction. He starts looking at solar energy conversion, not in the sense of at a applied level, but at a very basic level, controlling the molecular processes so that you can enhance the conversion of photons to electrons. Professor Husserl again stole the thunder. This is what I was saying. He stole here also. So he explained how the excitation gets carried, more electrons are generated. You can modify the molecules, whatever you want. And so this is the lab that he has built. He did several other things, very high impact work again in science advances, nature communications, what have you. But more details, JD can answer. So, well, not to be left behind, again in the 90s, laser cooling started in the 80s, and people were excited when Bell Labs, people got the first prize for laser cooling, Stephen Chu and others. And then soon in 95, the Bose-Einstein condensate was made, and there was a lot of things, why is TIFR not doing anything? And well, TIFR did a little later, but well caught up, I must say. That this is how lasers are. These are continuous wave lasers, small diode lasers used to stop atoms in their tracks, and so you use multiple lasers to stop them in the 3D, and you can also cool them, you can trap them. Everybody knows this stuff now. And the first experiments were started by Uni, and here you can see the cold atoms hitting a surface and sort of bouncing off. This is Ashok Mahapatra, was a student who worked very hard to get these experiments going, and he also made the Bose-Einstein condensate a little later, which attracted quite a bit of attention. There's a lab that you can see on the right hand side, and so it was also covered in popular press. And of late, 5 years ago, in DNAP, Saurabh Datta entered, and he wants to now make cold molecules. And in fact, I think he was one of the first people to make this alkali dimers, sodium, rubidium kind of molecules in the US, where he actually started this work from scratch in that lab in the US lab. And now he has come here and he's very busy setting up these cold molecules, which can have applications in basic physics, not just fundamental interactions among atoms, but also in quantum technologies. That's something that Spenta said we should be entering very soon. So another thing, and this is how TIFR typically grows, that we said we're doing lots of optics, but around that time in the 90s, random lasing became a big thing. And Sushil had done very interesting work at RRI with Hema Ramchandran as his advisor. He went on to do very striking work with Wiersma in I think somewhere in Germany. And he came here in 2006. He started looking at mesoscopic optics, lots of microparticles in a liquid, and you shine light, and the randomness, so the multiple scattering leads to very, very interesting effects. It can trap the light. It can also amplify light, which is called random lasing because of the feedback from each of these scattering events. And Sushil, the good thing about this is that this is a disordered system, which mimics several things in condensed matter in disordered solids. Like, for example, Anderson localization can be easily seen, or analogs of that, or that can be checked. What happens in disordered solid, which is very difficult to see, can be easily seen in an optical system like this. And so he made some very interesting advances in Anderson localization, showing the parallels and so on. More details you can ask him. And also something about the statistics of, how this, if you look at correlations of this light, how these statistics are influenced by how they look similar to what is called Levy statistics or bird flight statistics in my crude understanding. So this is also something that I think I've seen other people mention this in several conferences, saying this work was done first at TIFR. So it's a very, very proud thing for TIFR to have this. More recently, in systems where this is an experiment, I think in the terahertz region, where they're actually trying to control or look at transmission through the waveguide and how this is facilitated by the structure that you have and what Anderson localization does to this anomalous transmission. Okay, so a little bit, 5 minutes so I'm not taking too much about myself, but this is a story of highlight intensities, extreme optics. So we began with normal optics. Now we'll go to nonlinear optics and extreme optics. So all of us know that if you crunch laser power into a short duration, you can enhance what is called the peak power. So 1 joule in 1 nanosecond gives you 1 gigawatt. And we bought, when I came here in 92, the first laser that we bought, we decided that we should enter this field of high intensity interactions with molecules and so on. So we bought a 35 picosecond laser, Nd:YAG laser. And you can see the laser is here, focused by a lens, a green second harmonic of the 1064. And if you can see from the front, I don't know about the back, that you can actually see that there's a spark here caused by the focused light. So the nitrogen and oxygen at the focus are actually ionized by this, producing the spark here. And that's a group, can you recognize them? Well, much younger, Ravindra Kumar and Deepak Mathur. And I'm also glad to see Riju has come to this meeting. Riju Isaac, who was a postdoc here. Reggie promised to come, but he has not come. That's next to him. And so on and so forth. So this is the story of electrons being pulled far from their equilibrium positions, not just gentle perturbations like in linear optics, but far from their equilibrium positions, making the motions unharmonic. And this leads to all sorts of things. And I just want to present one result, which is that, small amount of light is transmitted through an absorber. But if you shine large amounts of light, it just soaks up. It sort of, builds appetite depending on the intensity of light. And this is what is called optical limiter. It's useful in various contexts. For example, you can just clamp off the light at a certain intensity. So eye goggles, for laser safety can be made using these materials. And we looked at several other effects like this, but this is just one subset that we did in our lab. And this is to show that in my earlier avatar, I used to work on gigantic molecules. Like this is tetra-toluyl porphyrin. And I'm glad to see that Prem Kiran, who was my postdoc at that time in the late 90s, he is here in the audience. And this is the work that was done by him, where we showed that small amounts of light, you have linear transmission, but if you have large amounts of light, it actually gets clamped and the excess light is absorbed. So moving towards extremes, so this is about, as we kept moving from 10 to the 9 watts per centimeter square to 12 watts per centimeter square, we investigated molecules. M. Krishnamurthy, much younger, right? Also much younger here, and Deepak Mathur, who has moved on in 2017, he retired from here. And single molecules, clusters, what have you. And very nice results were got from these interactions and about dissociation, ionization, and how these processes happen. So then we escalated further. We went to, we became hungry for power in a way. So 100 terawatts from 2 gigawatts in 93 to 150 terawatts in 2019 and beyond. So this is a 100 terawatt laser that we had from 2010, producing 10 to the 19 watts per centimeter square, which is 3 orders of magnitude larger than the electric field corresponding intensity between the hydrogen nucleus and the electron. So that is 10 to the 16, this is 10 to the 19. So obviously, also this is a laser like that. These are the people who invented Gerard Moreau and Donna Strickland, who was a graduate student with Moreau. Moreau visited us in 2009, 9 years before he got the Nobel Prize. And nice picture. So it's me there and MK, Amit, and Rajiv, who was a graduate student at that time. And so this is a story of extreme light, where we bring in this powerful light and explode the solid, create extreme levels of excitation in a very, very short time frame of 30 femtoseconds or so. I will finish shortly. And you create all sorts of things. This is a story of literally what happens inside stars on a tabletop. So you produce relativistic electrons from 1 eV photons. You produce huge amount of ionization. So you have a plasma, which is like what is inside a star, some part of a star. And you have secondary, so these are sorts of rich secondary emissions, ionized particles, free electrons at MeV energies. And you have terahertz radiation coming from here. You have huge magnetic fields that have been set up because of these fast electron currents, which are of the order of mega ampere pulses. I don't have all the time in the world to describe. I just want to show you that the magnetic field that we measured here, flashing on the left-hand side, changing very rapidly, both in space and time. If you take a power spectrum of that, that actually looks like a, that has a nice scaling law on the right-hand side. And this mimics the astrophysical turbulence, what happens inside the sun and various other stellar environments. So this is what is called turbulent tabletops, and Nature Physics wrote a highlight and called it, they rejected the paper, but they wrote the highlight saying that it is probably a mini solar system in the lab. That's the underlying statement there. And then we pursued this further, looking at this mega ampere electron dynamics, and several other results came out about their transport inside nanotubes, inside bulk solids and so on. And MK made the world's first neutral atom accelerator. So neutral atoms, Pillay talked about charged particles. This is neutral atoms at MEV being produced only in TIFR, nowhere else, right? And people say that, how do you do this? So it's by ionization and subsequent recombination, leaving the energy intact, but neutralizing the charge. So this is the world's first, very proud of this achievement. And we also did several things in collaboration with Pushan Ayub, and you can see other condensed matter colleagues elsewhere, where we pushed the plasmas to emit brighter and brighter X-ray emission. And an accidental discovery was the fact that we started competing with Prabhu. He produces nanojoules and picojoules. We said we just put a liquid in the laser, and now we're getting microjoules. Well, it was an accidental discovery because we were just testing out something else, and suddenly we saw terahertz emission coming. This again became very noted. And in the last 2 minutes, Vandana, sorry about this, is that the work became, now it's getting global. We now have an Extreme Photonics Innovation Center in TIFR, presently, actively being pursued at the Hyderabad campus, where UK has invested £4 million. We are providing the sort of in-kind contribution by our expertise, facilities here, and so on. The thing is to generate technologies for the next generation high rep rate lasers. And I'm glad Rajiv is in the audience. I hope he has come for this meeting. He has been the main driver behind this collaboration. So Extremes in future move to Hyderabad, where we have lots of space, and we'll put a petawatt laser, hopefully by 2024. If the bureaucracy can be overcome, they have a lot of stopping power. So this is the lab that's being built in Hope. Huge hangar. It looks like a Boeing hangar. Please go and take a look before it becomes an enclosed lab. It's really nice to walk in and admire, oh my God, how big it is. It's probably much larger than this auditorium, right? So what we will do, we will do everything under the sun, from astro to accelerator to condensed matter physics, warm condensed matter physics, and even QED. That's what we promise. How much we'll deliver the next 75 years will tell you. And research at TIFR itself is probably, it's too presumptuous to say, because who expected all these things to happen? People come together, things happen, and then people move out to do different things. Some areas of immediate expansion that we are thinking of is tremendous amount in quantum technologies, because optics is where quantum technologies are very easily doable. And basic physics in all these quantum areas, attosecond physics, which has been a dream for about 10 years, has not happened, but should happen. Precision quantum optics, again, TIFR is for fundamental research, so that, and unheard of so far, but we are probably moving in different directions. We are thinking of a Section 8 company to commercialize things that people like Sudipto build, and several others, maybe terahertz devices also for the country, right? And startups. So maybe many of the future people can have startups. In fact, they're already asking, thirsting for, I want to start a company. I want to start a company. How can I do that? Several young people are rooting for this. So they will happen. So you'll see things changing dramatically. And so now if I tell you this, have I covered all this? Perhaps I have. There are, high intensity lasers, basic aspects of light propagation on the right-hand side, high energy density science, tweezers, cooled atoms. I guess I have given you a flavor of all this. And so you say that, fundamentals to extremes. What a title. You start from fundamentals, you move to extremes, but extremes again reveal fundamentals to you, right? So this is a cycle that keeps repeating endlessly. And thanks to all the people who shared the slides with me, and also to these nice students who made the slides, the interesting slides of this talk. And if you still have a little bit of appetite, just one more minute. Sorry to be eating into a tea break, but this is probably worth it. So you're not coming to the lab, so I have brought the lab here. So something for the TIFR people, this is, come on, you've shown this before. So please close your eyes. The rest of you, look at our 100 terawatt laser beam, which is shown on this red paper blinking away. White flash is a spot at the orange thing is the laser beam. You can see it moving about 7 centimeters or so, almost half of my hand. So the lasers become bigger in physical size as they become higher in power. And so now let's go and see. We focus it. We move the red shutter going up, and it falls on a target. Now, can we have louder sound, please? So this is literally ending with a bang for you. So that's the 10-second response, not very high power because it's happening in air. So very low power, being focused on a target and creating havoc there. And if I continue, I'll show you a close-up of that also. Increase the sound again, please. So you can see that the target which is there, you have a plasma blooming out, and you hear sound, which is actually the shock wave caused by the rapid explosion of the plasma from where this has been irradiated. So this is a sound and light show that we have routinely in our lab when we are aligning target. And I thought I'll just bring a little bit of that to you. So, no, this is not in vacuum, this is in air. The intensity is low. In vacuum, when you go beyond 10 to the 14, you cannot have these pulses propagating in air because they cause lightning. So we also done those experiments where the light pulse actually causes, it streaks in the air, causing, you can see lightning happening in air. And so that's what is called filamentation. Right. So thank you so much, and apologies to the chair and other people, all of you, for overstepping.
Thank you, Ravi, and I think you've taken the organizer's privilege to take extra time in the session. So thanks to organizers.
Thank you so much for changing this session, and also thanks to all the speakers for such wonderful talk. And thank you Roshi, for taking us these big rides. Actually, loved that you covered, and we talked a little less about your own work. So thank you very much, all of you, for coming in the morning. Now we will break for the tea, and then we will again assemble here at 11:45 for the next section. Thank you so much. Fantastic.
He will just use this. You use. You put it. While you do the initial opening and then I'll. Okay. Okay. Then everybody knows you.
Yeah, ठीक होगा? So I'll also hide. उतार दिया मुझे याद दिला Okay.
Start. Welcome all of you for the second session of today morning. So today, it's my great pleasure and honor to invite Professor Dinesh Sharma from IIT Mumbai. And he used to be here. I'm so glad that I was his Unitherapy student. I did my Unitherapy under him. And I hope he remembers. I mean, I can also tell you that he is the father of this EVM, our electronic voting machine. So I'm sure that it is always criticized that maybe because it's just the election took place and three different parties won in three different states. So now nobody is claiming anything against the EVM. So let me just request Professor Dinesh Sharma to chair this session. Sir.
Thanks, Prabhu. You've given more prominence to the chairman than to the speakers. And also, I am not at all the Indian voting machine. I am a member of the Technical Advisory Committee of the Government of India to it. The voting machine had indeed been made by other people before me. Coming back to the session, our first speaker is Shobhana Sharma. She joined the molecular biology unit of TIFR as a PhD student in 1975 and earned her degree in 1981. She continued here for a brief postdoctoral fellowship and then went on to New York University Medical Center and finally to Duke University Medical Center. She came back to the molecular biology unit as a faculty in 1987. In this time, she transited from physical chemistry to molecular biology of plants to malaria parasite molecular biology and immunology. After coming here, she has set up her lab on the study of malaria parasite and some other protozoan systems. She has published extensively on parasite biology and has also filed for patents. She is a recognized expert in the field of parasitic molecular biology and immunology, and has contributed as a member of several scientific advisory committees and governing bodies. She has mentored and supervised the research work of nearly 30 PhD and MSc students who have carried out the legacy of being successful scientists all over the world. She has also been involved in women in science activities and indeed figures in the famous book on women scientists from India, Lilavati's Daughters. Shobhana Sharma.
Thanks very much for this kind introduction. As you see over here, I'm going to talk mainly about the pioneering of the molecular biology, and the organization is over here. So history will form the major part of my talk. And then, of course, I'll talk about research activities in parallel and some of the teaching and workshops. And I'll talk about the current status at the end, and obviously that will be quite incomplete, as you'll see. Okay, so history. So biology is at 60 years, not 75. Obaid Siddiqui joined in 1962. And the story is very well known. He was handpicked by Bhabha. Most people in those days were handpicked by Bhabha. Subsequent members of molecular biology unit were handpicked by Obaid. The group was then called Molecular Biology Unit, and I will comment on that also in subsequently. So Obaid started research in Tata Institute. Of course, many physicists who were asked by Bhabha actually said that this is not the right stage for any biology person to join. Where are the resources? What will he do, etc., etc. But nevertheless, Homi Bhabha had decided based on various criteria. So he had joined, and he had narrated these stories that initially he had only, he didn't have an autoclave where you could sterilize things. So they used pressure cookers and so on. So all kinds of jugaad, which TIFR is very famous for, he used, and he started with bacterial and fungal genetics and did seminal work in the first 10, 12 years. In that field, Ram Naresh Singh from BRC training school also joined. But the trend for molecular biology unit in early days were individualistic. Everyone did her own work, and you'll see that. So such a subject, molecular biology, did not exist in any biology syllabus. Even now, you don't find it as a subject per se. These traditional biology subjects, botany, zoology, microbiology, were getting modernized in 60s, and some places were calling it life sciences. But Obaid had this vision of biology at the molecular level, so he called it molecular biology. And he also convinced University of Mumbai to start a molecular biology department. We all earned our degrees in molecular biology. Nowhere else in the world do you earn your degrees in molecular biology. Now, deemed university gives it in biology, so I'll come to that. So soon after Obaid, it was Dr. P.K. Maitra who joined along with Arun Singh. Arun Singh joined actually earlier, P.K. Maitra joined later. And he worked on utilization of glucose by yeast using genetics and biochemical tools. His personality was such that he would be in his lab all day. We had a common lab, and he could see us from his office, from his lab bench all the time. And we were extremely upset that we couldn't do things which otherwise, at night, we might want to do, sing songs or whatever, have the radio blast on and so on. He was always there in the lab. Subsequently, and of course, they did fantastic work on glycolysis. I'll come to that. UN Singh, M.R. Das, Kenkare, Johri and Babu joined. And initially it was these scientists who played formative roles. Anil Sadgopal also joined, but he's from Caltech, but he soon left. He had completely leftist tendency and wanted to, teach science to rural school students as well as farmers over there through innovative methods. And this was Kishore Bharati. Eklavya is the fallout of that which exists even now. I don't have a picture of Anil Sadgopal. I'm sure we can get it. He was associated with Central Institute of Education in Delhi. Umakant Kenkare and M.R. Das. So he used enzymes and studied their structure function relationships and regulation. M.R. Das worked on RNA tumor viruses, which was a very hot topic at that point. He worked with Saul Spiegelman and came back and continued to collaborate. And there was a lot of clamor among students to work with M.R. Das at that time. But in early 80s, he left TIFR. So Obaid's dominating, personality was very difficult for people who wanted to, start domains themselves. So many people have left, and M.R. Das also left and joined CCMB Hyderabad and found his own institute, Rajiv Gandhi Center for Biotechnology in Trivandrum. But TIFR is also, this was one of Homi Bhabha's expectation that TIFR will actually have scientists who will move out in the rest of India and start important institutions, directions of work. Manmohan Johri, his picture is put up outside. He is as one of the unknowns, but he did very, very good work over here. He came with plant molecular biology, and Obaid was not at that point looking for plant molecular biology. It's a difficult field to start with because growing plants, you need space, resources, etc. But he met Obaid and Morris Fox, both of them at MIT, and had a day-long interaction, and then Obaid offered him a job. And after joining, he tried many projects, which were, some of which did not quite work out, but finally he settled with the project of moss cell differentiation, which was essentially done very nicely, because normally moss grows on solid agar. That's how they're grown in the lab. And any study is very difficult. You can do microscopy, but it's very limited. But he developed the technique of growing liquid cultures of moss cells, and we could follow that for their cell differentiation and development, and that was that gave very unique features. I'll come to the work actually. Babu. So these were the early people. So he was a PhD student. He also came from BRC training school, did the PhD in theory physics in TIFR, but he was attracted by the possibility of genetics and molecular biology. And after a postdoctoral stint, joined MBU and brought with him the system of nematodes, C. elegans, and worked subsequently with fruit flies as well. And he was involved in neurobiology, developmental biology, mainly using the tools of genetics. I have never seen Babu do anything but genetics, and he would always leave dirty biochemistry to other people or collaborators or students. He always worked with genetics. In the late 80s, again, Babu decided to, he was a very restless personality. So he felt that he was doing the same thing over and over, and that why is it that we could not buy reagents for recombinant DNA technology, which was coming up at that time. We had to import all of it. So he took this giant leap of moving to Bangalore and starting this company, Bangalore Genie. And all of India is very indebted to him for this company because now they could buy it in Indian rupees, the reagents, and it was really one of the first kind for India. Subsequently, 72 to 82, Krishnan and Vidyanand Nanjundaya joined. Krishnan joined in 77, Vidyanand joined in 1980, and both came with physics background. You can see all of, other than Manmohan Johri, P.K. Maitra, Kinkare, they all had chemistry background, or like Babu, Krishnan and Nanjundaya had physics background. So not many traditional biologists joined at that time. Even among students, that used to be the flavor. Most of us came from chemistry, physics backgrounds. So Krishnan started with snail biochemistry and neurobiology. And many of you might be familiar because soon they escaped the animal house and was all over the colony and, moving around very freely. But subsequently, he moved to Drosophila, and Vidyanand studied cellular slime mold. This is an amoebic organism that lives as single cells when food is plenty. But then the moment starvation sets in, they actually aggregate to form one body, and this body moves as a slug and develops apical and polar specificities. One part becomes fruiting body, the other part remains the anchor. And so it is a very attractive system for looking at signals that would cause these differentiations. So 72 to 82 also heralded the neurobiology in MBU. So Obaid went for a sabbatical study and came back with the idea that there should be higher organism. Bacteria you cannot is limited only to very basic cell biology or molecular biology. So he started fruit fly neurobiology, and Veronica, who was one of the PhD students who joined in 1976, pioneered the studies. And of course, famous are the home-built, glass-blowing section-built Wymies apparatus, using which they got wonderful, so you feed in the flies and you put air on one side and the particular chemical on the other side and see whether flies move to this end or that end. You count the numbers and you can see whether, so you know what the normals do and you can generate mutations and look at what the mutants may do. And she joined as a faculty in 1982. A whole bunch of our students joined the department at that time. I have already talked about Veronica. LC Patty joined in 76. Vijay joined in 83 or so, and I joined in 87. Zita Lobo moved from scientific to academic stream. Here is Zita Lobo. And Gautam Jarori moved from solid state physics. So he was a member of solid state physics. I noticed that his name never came up. Kasturi's came up, but he was a solid state physicist until about mid-90s, and then he moved to MBU. So Gautam in the early days. The only non-TIFR alumni inducted during this period was Subrata Tripathi. 82 to 2002, molecular biology flourished in TIFR Mumbai, but space constraints were very real, and Obaid wanted to expand. And there were many people who could join and join the existing programs as well as other programs, lines of work. So he realized that he could not expand in here. And in Obaid's own words, the idea that TIFR should start a center for biological research was mooted in 1982, following a suggestion by Ramaseshan. But that could not happen. That is location at IISc campus. But the Planning Commission in 1984 agreed to fund a center for fundamental research in biological sciences. And the center was to function as an autonomous unit under the aegis of TIFR and conduct fundamental research and training in areas of biology at the frontiers of knowledge. So I believe there were questions about why biology should expand, but clearly Obaid could convince them. And after several years of research, University of Agricultural Sciences at Bangalore offered an attractive site on their campus. And this was a very good move because it wasn't new land. New land had a lot of problems. So it was within the campus, their existing campus, and an MOU was drawn up and signed in February 1991. Since the funding had already started, Obaid had already started recruiting for NCBS. And Jayant Utgaonkar, M.K. Matthew, Panikkar, these were some of the early appointees who worked with members at MBU in the department, in the labs. There were lab spaces assigned to them. And only in 91, 92, they moved physically. So first to the IISc building, which was available to them, and then to their new building. And of course, from the department, I forgot, Geti Hassan also joined around 1987, 88. She was a postdoc with L.C. Padhi, and she became a permanent member. And these people moved from MBU to Bangalore. Meanwhile, in this period, B.J. Rao, Rohit Mittal, Shubha Tole, and Vidita Vaidya were inducted in TIFR Mumbai. This wasn't easy. Once Obaid decided a new center would be formed, all the good cases, quotes, he would take the files and he would keep them with him for NCBS and would not allow molecular biology unit to appoint anyone. Dr. P.K. Maitra, who was an excellent scientist, but did not have the kind of administrative acumen to override this or to search for people on their own. And of course, who could match Obaid in the charisma and attractive power? So we had a tough time. We also had a tough time because it was expected that biology would die over here and everyone would move to Bangalore. And why recruit people? But thanks to Porter Commission, I think, I'll come to that. So nevertheless, we could induct excellent people over here who continue to doing work over here and excellent work at that. So NCBS, coming back to the history. So this is from his own write-up, Obaid's own write-up. He says that he went by the guidance of Flexner, who proposed the creation of Princeton, the Institute of Advanced Study in Princeton, and that it should be small. Its staff and students or scholars should be few. The members of the teaching staff, while freed from the waste of time involved in administrative work, should freely participate in decisions involving the quality and direction of activities. The living conditions should represent a marked improvement over contemporary academic conditions, and its subject should be fundamental in character, and it should develop gradually. And that was something he adhered to, because initially there were about handful, 8 to 10 scientists, and it slowly grew. And that has its own advantages, because he could really look at certain fields and induct. So of course, this is the current status. He was the center director until 1997, after which Vijay, and then now it is Jitu Mayer. Hyderabad, I have just one slide because it's going to be talked about separately. The point is that, and this is again from the director's note for the Hyderabad. And I just want to point out that currently there are about 30 faculty members, of whom about 50% are engaged in some form of biology research. Some of them are totally molecular biologists or immunologists. So Pratim Majumdar, who was a student of Shiv Prasad from NCBS, is one of the first biologists. And now there are Monica Vij, who's an immunologist, and Adish Dani. So some who are basically molecular biologists, but then there are many others who have, who collaborate. So they are from physics and chemistry, and there's a very viable, there are very viable collaborations. So research areas and activities. Do tell me when I have 5 minutes left, okay? So Ubaid encouraged all faculty members to find their own questions and their own models. And this was the beauty of TIFR as a whole, I think. Basically, people were free to do their own work, whatever kind of science they wanted to do. So the early areas, 62 to 82, were bacterial fungal genetics and biochemistry. So Ubaid worked on Aspergillus, enzyme kinetics by Kinkare, viral molecular biology, plant development and neurobiology. And he tried to unify these into neurobiology and molecular biology. This was because the planning commission didn't want to hear about 10 different projects. So he realized that some kind of grouping would be useful. So neurobiology is very clear. The rest of the people got clubbed into molecular biology. So molecular biology has been a topic that was very useful. He was also keen on group of scientists working with infectious diseases immunology, and that's how myself, Sudhir Krishna and Apurva Sareen were recruited. And subsequently, Sudhir and Apurva were clubbed into cell biology. I'll come to NCBS. They were in NCBS. In the 90s, the term molecular biology became highly questionable. It got associated with recombinant DNA biology, which is genetic engineering, and it lost the general value. In 1997, somebody was asking when the structure happened. So 1997, the Porter Committee came and gave their report. There was a large-scale review. And instead of groups and units, so the only school that existed at that time was School of Mathematics. The rest was called School of Physics or Physics Faculty, which was, of course, not so suitable for us and for many others. So then 3 schools were formed: computer science, mathematics, and natural sciences. And the groups and units got designated as departments. So molecular biology unit became Department of Biological Sciences. And at that time, I remember we were quite unhappy about this change, and many of us would call it a dubious department and so on. So in 2002, TIFR became a deemed university, and under the biology subject board, the degree which is conferred now is biology. So the name does matter. I mean, even though great poets have said what's in a name, but name does matter. Okay, I am now showing some slides prepared by my colleagues when we had to prepare for NAC. And so I just thought these were beautiful, and they were made in 2016. So NAC is the Committee for University Accreditation. So at that time, we had all these model organisms, and I just want to, and we grouped, as you see, it was nice to group. The same person would occur in many groups, depending on what their work is. But I want to talk about the model organisms. So fruit flies system was brought in by Ubaid in 70s. Yeast was worked by P.K. Maitra, but when Maitra and Zita Lobo were no more, then this sort of died, and then it was revived by Himanshu, and then again he left. So no more yeast work. These are red cells containing plasmodium. These are zebrafish. Zebrafish also. UN Singh, Uday Narayan Singh, decided to work with zebrafish, and for about 6 months we had this beautiful aquarium in the common lab, and he did some developmental biology work, but later gave up. Anyway, he moved out to Delhi University. But now, I mean, subsequently it was brought back by Mahendra Sonavane, and Shailaja also worked on it. Mouse system, of course, thrives the most because many of us worked using the mouse model. Shubha and Vidita, the prime users. Ullas, myself, we were also extensive users. This is the cellular slime mold. So Vidyanand brought it with him, and he left in late 80s to join IISc. So this work stopped, but then Roop Malik came in and did a good bit of work in using cellular slime mold. And so it came back. So model systems keep coming and going. C. elegans nematodes were brought by Babu, and it was given up early, but then Sandhya Kaushika brought it back, and a good bit of genetics and molecular biology is carried out with it. This is this should have been green in color. It's Chlamydomonas, which B.J. Rao worked with apart from bacteria. And so the topics or the models kept coming back and forth for TIFR. Again, in 2016, we were 14 at that time. The academic strength, if you look at postdoctoral fellow students, it was 107, of which 56% were women. Faculty was 43% women, and this is probably the best figure for institutes all over India. Typical representation in a good place is of the order of 25 to 30%, even in biology. Hosur was talking about interconnection. And I'm glad because somebody did this. I'm not sure. Vidita probably made this slide. And you can see the interconnections between the people at that time and the kind of work that people were doing. And each group interacted with the other, and there were each individual scientist interacted. And then there were common publications quite often. Subsequently, many of us have left, and new members have joined in. Devashish Das, Amitesh Anand, Nitin Singh Chauhan, and Sundaram Naganathan. And so somebody will have to make that chart all over again and look at whatever fields they are studying. So the strength of Department of Biological Sciences has been between 10 to 14, and the kind of space it has at the moment can accommodate no more than that. Achievements, very difficult to talk about achievements, you know. How do you judge achievements in fundamental science? Mainly publications, right? So I have listed the kind of journals that we have published in from molecular biology and DBS, but it is representative of all of TIFR to publish in these journals. And I will pick up a few and talk about them. But I wanted to highlight publications arising from interdisciplinary research within TIFR. It has been heavenly for interdisciplinary research. We've had close interactions with the physics and chemistry members in the canteen and everywhere. And such fallouts have been magnificent. So these are the publications that I've listed. This is also till 2016, there might have been more. So people must excuse me for such limitations. Okay, what I wanted to point out was also extramural fellowships and grants. So this is something that biologists have always sought, because money was always limiting, and it was also prestigious to get some of these grants, and they are extremely competitive. So this is again a list from 2011 to 2016. So it doesn't include many of the earlier grants also, but you can see that you know, the total funds for those years did reach a very considerable amount at that point, which helped in bringing in a lot of equipments and consumables. There's a huge amount of expensive consumables required for molecular biology, for any kind of biology research. So now I'll just pick up some papers. I must say that every individual was publishing very well. We are talking of 75 years. I can't think of anyone who hasn't published well during this period. At least there have been peak times when they have published very well. So these choices which I've made, and these are from MBU DBS, are my own selection. And For Obaid, I have picked out this paper and this paper. So this was his bacterial work, where Vijay Sarthi actually showed that, and Obaid actually showed that DNA synthesis is not necessary when you're having bacterial conjugation. When bacteria conjugate, DNA from one bacteria go into another bacteria through special cell biology mechanisms. And at that time, there was a question as to, did it happen with new DNA synthesis, or did it not require DNA synthesis? So these two papers, there are two papers in JMB. They are seminal papers for that at that time, because it was new knowledge really. This is also a work which was very remarkable. I mean, the fact that they were studying mutations which did all kinds of funny things to chemosensory perception was common. There were many papers published by Veronica also, and so this paper has Veronica as the second author, Kavita Arora, Veronica Rodriguez, and 2-3 others, Obaid Siddiqui. So this essentially describes work in which, for the fruit fly, a salt repelling receptor gets changed to attractive receptor using certain mutation. And then they have characterized that mutation as to what that is. And that was one of the early studies of this kind, where you can change from dislike to like for your receptors. It would have long fallouts. All those people who don't like bitters, then you can change your receptors and start liking it as sweet receptors. So, but TIFR has been rather poor on, and it's not their mandate to take it to applied sciences. As Ravi was pointing out, maybe futuristically one should look at that, but taking it to any kind of industry was not TIFR's mandate. So MM Johri and Shaila Desai, they looked at this Moss differentiation and showed, using those liquid cultures, that indole acetic acid regulates the differentiation from one stage to the other. And this they showed with very beautiful biochemical work as to what exactly happens when these things differentiate. So the very nice pictures in which chloronema has certain cell property, and then the cell wall becomes oblique. How does the cell wall change from vertical to an angular one? These are all famous cell biology problems, and he has addressed some of them. Krishnan initially worked on snails went everywhere, but I think his work did not go anywhere. But so he moved to Drosophila and he studied anesthetic response. And this was again very elegant. So using homemade funnels so that you have 5 minutes, okay. You have flies which you put them on top, and those who are normal, they will just come down. Or maybe it's the other way around. You put them at the bottom and they will naturally go up. And those who are, if you put chloroform, those who will get anesthetized will fall down. But mutants which are refractory to anesthesia will continue to go up. And he has characterized several of them on that line, and he has moved on to many other aspects. Krishnan was also very restless. We moved from one project to the other. Maitra and Lobo, I cannot pick one paper because there are dozens of papers, but they did outstanding work on glycolysis, and so did Kinkare on enzyme brain hexokinase. Okay, some more recent examples. I do not have time to describe them. So, you can, you can see that these are all very, very good. These are just examples of excellent work, which I would have liked to have highlighted for each one of them, but I'll just go ahead. Research at NCBS. So NCBS has a faculty strength of about 40. And each group has 7 to 15 lab members, which is really the kind that one would like to have for any effective biology, experimental biology research. It has enormous strength in these traditional subjects, which is what I have described for DBS. And in addition, it has built strengths in ecology and evolution. And you can imagine that whatever I have described for DBS, NCBS has 4 times that in terms of its prominence, not prominence, in terms of quantitation, publications, and in terms of its impact in some sense, because they have huge labs. And so I cannot talk about NCBS. Somebody else has to come and talk about NCBS, because it's an institute by itself. So, and a fantastic one with doing fantastic work. So, but I would like to mention 3 programs, actually 2 main categories. One is the wildlife training. So this is unique. This is unique in this country. It trains people to do wildlife biology conservation, as also work on it at the molecular level. So there are wildlife programs, and you can join some university or other centers where you can follow the animals. But here you have the opportunity of taking samples and then working with them in the NCBS biology labs. And it's a very successful and unique program. There are students clamoring for it. I think something like 12 to 15 students are selected for the master's course, and it's very competitive. The other programs, these are centers and programs of NCBS, which I have picked up. One is chemical ecology, and this is in collaboration with scientists elsewhere. Currently, it is only Balaram and Reni Borges from IISc, but it clearly plans to expand. I couldn't resist the temptation of the beautiful pictures that were on their web pages. And they look at molecules exuded by them or secreted by them and look at their chemical composition. And I would have liked to have added cone snail, which is what Krishnan was working with, but I couldn't find a beautiful picture. So, but that was another one of these. And Krishnan, I mean, this was started a little later, so it's following the tradition of Krishnan. This other program is that of ADBS. This was launched in 2016, and this is using NCBS, InSTEM, and NIMHANS. And this works with, so Shona Chatterjee is the major driver. Deepa Agashe was the major driver in the earlier program. Shona Chatterjee is the driver of this. And they essentially collect material, human material, to look at genetics and genomics and, look at mental disorder. And right now, it is still in the data collection stage, but it is expected that this will give enormous value. This has enormous value and will be enormously useful. And yeah, I'm almost 2 more slides, sorry. So this is the third one, which is a lipid research, Max Planck NCBS Center on Lipid Research. And you can read the thing, and I like the logo. So these are membrane molecules, bipolar. So hydrophobic head followed by tails, and then the keys which can unlock such properties. And some of the distinguished alumni. So this I've just listed over here. This was also one of the 2016 slides. So it just lists people with their accolades. I haven't talked about awards because they have been, you name it, Infosys prizes and Patnagar awards and so on. They're both for DBS and for NCBS. And I just wanted to list alumni with applicable achievements. And I wanted to, of course, talk a bit about my current work. So Handa, who was a student of M.M. Johri, he went to Purdue University, and his work gave rise to genetically modified tomatoes with high pectin content. And these are in the market. and they are great favorites for ketchup production. But of course, you know, the inventor's name never doesn't come up, but you feel so satisfied. I mean, he told me that I feel so happy that my tomatoes are in the ketchup, but you know, that's what it is. And we are trying to test out nanolipid carrier mediated formulations for antimalarial delivery. And we have the work done in collaboration with ICT and TIFR using animal models shows very clearly that it can be used at about 1/5 concentration. So right now there is a lot of weightage on people because they have to take combination doses, 2 tablets 3 times a day, and they have a lot of side effects. So you can reduce it to 20%, and that such combination drugs with the use of these carriers can be delivered intravenously, which can't be done as of now. That's very important because in cerebral malaria, patients go into a coma, and then you have to put intravenous drips. And you can only use artesunate, which is soluble, so it becomes a monotherapy. WHO has mandated combination therapy, but for those patients, you cannot help it, it's a monotherapy. So we have shown that okay, here, sorry, I have 2 more. So we have shown all that, you can look at. Workshops and conferences, you know, Mahabaleshwar seminar is one I wanted to point out because our department keeps asking for money from TIFR to conduct this. It's a very successful conference. Some of the visitors at MBU, traditional to TIFR style, fantastic workshops. So you have, I think this is Maurice Fox and Frank Stahl, the Michelson and Stahl fame. He came and he was so much into Indian this thing that he would confer. You can see Obaid over here. So he got into Indian dress and gave degrees to students. And of course, Watson's visit to TIFR and to labs also. Then some of these labs, and you know, I wanted to show this. This is Maitra Udaynarayan Singh, B.N. Apte, one of the first few students of MBU, and King today. The rest of and Kakeri, who was our engineer. The rest of the people I don't know. This is N. Gautam doing experiments on ultra centrifuge, huge ultra centrifuge, and SM Joshi doing some experiment. Frank Stahl teaching MS Shaila, who was a faculty of, who's now retired, but was a student in that workshop. So thank you very much. I don't have time to explain those colorful slides, but
Shobana, thanks. It's now my great pleasure to introduce a lifelong friend, Professor B.M. Arora. We have worked together for long, and even after leaving respectively to different destinations from TIFR, we have continued to meet, collaborate, and teach together, and it has been a great pleasure. Professor Arora joined Solid State Electronics Group as a visiting fellow in 1972, and then retired as a professor from Department of Condensed Matter Physics and Material Science in 2008. He and his students worked on growth of gallium arsenide and related materials by liquid phase epitaxy and of quantum structures by metal organic vapor phase epitaxy. His students have worked on spectroscopy of quantum structures. He also applied quantum structures to develop optoelectronic devices like diode lasers and photodetectors. This is the bio that he has probably supplied, and in his eternal modesty, he has not included the very important fact that he owns the original patent on plasma display devices. You hear about plasma displays and so on all over the place, and I had the pleasure of seeing pictures of his early work on plasma display devices, and I was so pleased to learn that he in fact owns the original patent on this very important class of displays. Professor Arora.
Okay, thanks, Dinesh. That plasma display work was a long time back. So I'm here to tell you about semiconductors work at TIFR, and this presentation will cover up to the year 2000 or something approximately that. As Dinesh said, I joined in 1972, and so the group was started, as I will show, in 65, and then I will trace the history along as it went along. In this thing which I have put up, I have been helped by many people who were working in something called solid state electronics group, which doesn't exist now. It was merged into a department of condensed matter physics and material science, which came up when Professor Jha instituted that framework. Dr. Zarabi is not part of TIFR, he was never part, but he did spend some time. You will see when everybody knows there is something called the only semiconductor industry which worked on integrated circuits with semiconductor complex, and so he was a managing director for several years, and he was in fact involved right from the beginning. And I should add, thanks to TIFR archives and photography section, and also library. I forgot to mention this here in the pictures which you will see. Okay, so then when did and how did this work, which later on became some sort of thing which applied work, that is how the TIFR is an institute of fundamental research, and then how come it had this inclination to work in this area? Well, it was not the only work which was applied. There are microwaves, you have already heard about it in Pillai's presentation. So solid state electronics group. So the first Indian made digital computer this is the motivation. This is from the source book, 25 years, was designed and built in the institute in early 60s. This computer used thermionic valves. Many of you may not have seen them. And it was soon realized that the future generation of computers and computer-based technology could be advanced only by resorting to solid-state devices. And so rationale for working on semiconductors, which were the materials for making solid-state electronics devices. And this gentleman is D.Y. Phadke. I don't know if many people may have seen him. I owe my own induction in TIFR most probably due to Professor Phadke. Thin film and semiconductor electronics were supposed to be the areas in which this solid state electronics group will work. K.V. Ramanathan, he was in US and he had been working in industry of silicon, and so he came with the background of silicon devices and kick-started the solid state electronics group to develop what was at that time developing all over the United States, at that time silicon integrated circuits technology. And so this was the beginning, and then later on the group diversified into include physics and technology of non-crystalline semiconductors and compound semiconductors. So this is really the beginning of this activity. So this is a picture which I could get with great difficulty of K.V. Ramanathan. So he initiated the work on discrete silicon devices and bipolar integrated circuits. You see, transistors come in two varieties. The ones which you got Nobel Prize by Bardeen and Shockley, they are called bipolar junction transistors, and then later version, which is the technology which is in the devices in computers and they are called MOS transistors, or field effect transistors. So they were the two basic types of devices, and initial work was on bipolar transistors, and there were many members. Pinto is there in the audience here, and P.M. Muskar, of course, is left. Some of you may recall Apte, who was backbone of this program. S. Chandrasekhar, he worked on some aspects of research on this topic. D.K. Sharma is, of course, with us, and he is the chairman here. P.S. Subramanian, he was partly in the computer group and partly worked with solid state electronics group, and he designed many of the things which you will see his contributions. And Vengurlekar, he was a student in theoretical physics, and later after finishing PhD, he joined us in solid state electronics. So the group established an integrated circuits lab. Early work was on design and fabrication of what is this TTSL. I told you two types of transistors, that bipolar junction transistors, that is the basis of this. And later the group established also the MOS based, which is the current lot on which most of the thing is based. So these I have called early pioneers. There are two persons you can identify who on whose shoulders the rest of the group developed. The second person who joined in 1967, 2 years later, was Guha, Shubhendu Guha. And his early work was on some devices which are actually resistors, but at very high fields, these resistors produce microwaves. They have negative resistance. They're part of the band structure of this material. And so he started work. And when I joined, V.T. Karulkar was working with him, was used to make gun diodes, and they used to burn very quickly. And some of the early, my association with this, I did something with them, and the devices became more stable. But anyhow, by 1970, Guha was trained in Calcutta School, Radio Physics and Electronics, and so he was he was looking for new venues, and so he started two activities, partly based on this work, gun diodes, which were gallium arsenide instead of silicon. They use gallium arsenide that has the right band structure to do such things, and so I joined this activity, which was already begun by and Subramanian and A.K. Srivastava, and Guha also had involved many students from different places in the country. So this is one activity which flourished, and I sort of continued to work in that area. The second activity which he actually began was the physics of amorphous semiconductor. Now, these are non-crystalline materials, and then people were beginning to look at what is the role of disorder in amorphous materials, and so the rules of the subject. So I've been in interaction with all these people whose I have taken them from their quotes. Rules of the subject were just being formulated, and Guha decided to start this activity. And members who contributed in this were Narasimhan, several of you know. Inakshi Bhattacharya was a student. Stanislav Petrushko came from Poland. He was a student. K.V. Krishna was a postdoc, and D.R. Papat was helping to formulate. You know, we had to make our own systems and everything, as of course many other people who have gone before me said we made our systems, and so we also made our systems. Now, this is one of the, if you ask me for landmark and something which you can call, which will live for a long time and everybody in the world will use, and this is that kind of result. This is a world-leading result. There is some element of chance and good luck, which Nagarajan said. So in the late 70s, in the late 70s, there was a lot of interest in amorphous hydrogenated silicon for its potential industrial application. The material was usually made by decomposing 100% silent gas. Guha and colleagues in Narasimhan and Petrushko found the material deposited from 10% diluted hydrogen. This is a SiH4. So it can be diluted in hydrogen, and they used this dilute hydrogen. And it turned out that this material has superior properties. Of course, they had to establish that fact, and that this is the paper which there are not many publications which I am going to project, but this is this paper is referred by all people working in this area, and it is used over and over again all over the place to work to synthesize this material. Guha, of course, had fundamental physics as one of his goals. So he actually organized a conference in 1981, one of probably the earliest conferences in India to be organized in this way. And many of the, so I have a copy of this and I can give it to the archives, and it can be available for anybody to look at it. So this is one of the things which will happen time and again to people working in solid state electronics, and I will have some 1 or 2 comments later on to make on this aspect, why people were leaving. Doesn't matter. So in 1982, Guha joined a company in US called Energy Conversion Devices, which was working on devices using a hydrogenated amorphous silicon and particularly solar cells. And it was anticipated that material, solar cells made from this material will dominate the solar energy. It turned out that did not happen, but that did not was not very clear at that time. So later on, Guha became the president of United Solar, which is another offshoot of this, and which became the leading manufacturer of. You see, these days you hear about a lot about solar cells and solar cells of multi junctions called tandem devices. They are the rule. They will rule in the future. Silicon, of course, ruling just now, but his hope that so Guha was a pioneer in that region because of some requirements of this type of solar cells, and he also demonstrated the highest efficiency of solar cell and modules. So Guha became very, very well-known technocrat in US. In fact, I have seen pictures of him with President Bush and President Clinton, and so what I want to say is that this was somebody who really made a mark. So morphosilicon work in TIFR, of course, continued to be done beyond 1982 when Guha left, and this was pursued largely by Narasimhan, but not only Narasimhan, Dinesh, Srivastava, and several other people. Inakshi is, by the way, a faculty in IIT Madras, and so they all investigated. You see, this is an amorphous material and it has a lot of disorder, and it is of interest always to semiconductor scientists to look at electronic energy states, where they are in the band gap or mid gap, and so on and so forth. So that occupies a lot of our time. There can be optical techniques, there can be electrical techniques, and so there were many experiments which were set up, which involved photoconductivity, field effect, thermal deflections. This is an optical spectroscopy, and there were many publications. Now let me take you back. What was happening during this time in the silicon? Silicon field, I introduced the main characters of that. And so the first major person I want you, he's present here in the audience. And so he joined very early, just after Ramanathan joined, and in 1965, you see, and Pinto is a master builder. He's a master builder in the sense that thin films was one of the areas which was supposed to be progressed. And so he designed these systems early on, Magnetism sputter system for high rate growth films, and also RF sputtering systems. And you will see that throughout his life, here at IIT and now also, he is continuing to build on various things. Secondly, because the group was supposed to work on integrated circuits, so that integrated circuits required a laboratory which will be called clean room. So he built our first clean room in India, and believe it or not, when he left TIFR, he went to IIT and he built their clean room for what is known as the Center for Excellence in Nanoelectronics. So you see, he is a master builder. That's what I call him, master builder. So design, and so secondly, he set up the silicon device fabrication facility in second floor C block of TIFR, which included a clean room for device lithography and various other things. Based on this clean room, these ICs were being made in TIFR, and then I will show you some kind of a. This is now an applied landmark, which was very important for TIFR at that time. This is the landmark. You see some picture which is maybe not so clean, but at least you see some images, which is an image of a bipolar transistor circuit, which works as a NAND gate or something like that. I will not go into the details of it, but there was important thing of this slide is that these devices were built, designed in TIFR, and then a team consisting of Apte, Maiskar, Pisharudi, under guidance of Kunamnath, and of course, they went to Bharat Electronics in 1972 and established this technology in the laboratories in that industry. So this was the earliest technology transfer, you can say, from TIFR in the area, which was supposed to be developed by this group. And there were many other things so this, according to Apte, this was first ever designed chips in India and first ever fabricated in India. So you see, TIFR was progressing along some directions. Sorry. Which was expected to do and doing pretty well, I would say. Now, the second type of transistors were this field effect transistor called metal oxide semiconductor or silicon transistors, and these are the main players in that game. And Dinesh here, Apte, and P.S. Subramanian. I don't know, many people may know him. So these MOS field effect transistors were the basis on which the large scale, LSI means large scale, and later on VLSI, very large scale integrated circuits were taken up. Next level of involvement in IC revolution. MOS gate technology was developed. So this technology had to be, when devices had to be built and then tested, and various aspects had to be done. And this development finished in 1979. So you can see that by 1979, TIFR has all the basic aspects of MOS technology. This was a very important date, fabricated in and large scale integrated circuits were fabricated in the institute at that time. Apart from this, this required various background activities. For example, activities which Dinesh led the circuit design, and then graphics were led by P.S. Subramanian, and the technology was evolved by this. So this forms the trilogy, Troika, which was the basis of this. I want you to remember that this 1979 is very important, because later on I will tell you how TIFR connection with this development of technology which occurred in this very institute later on broke. TIFR role in this was not recognized in the ultimate establishment of semiconductor complex. Before I do that, so there were, of course, Dinesh Sharma was also very active. He had spent time in Cornell, which was yeah. So in any case, he was doing research with a topic, role of heat removal and how heat generated, etc. And he was modeling these things. The electrothermal modeling, according to him, has now become the mainstream again these days. Dinesh also recalls that in addition, and this was recalled by Nagarajan in the morning also, that in addition to computer-aided design, PS and he worked with Multani for developing an electronic calculator long before these became common items. Manu Multani, of course, went on to establish the nanomaterials activity in TIFR, leading the Indian research in this area. So this you can say is the earliest person who diverted from whatever he was doing as part of this solid state electronics activity. Dinesh also had left by 1992 or 91. So you can see one by one, several people who were involved in silicon particular activity, they had to leave. Though I will give you some reasons for that. But before doing that, TIFR was intimately involved not only in making these devices, but working on the background of materials and physics of those materials. And so one of these names is Chandrasekhar. Chandrasekhar, he was working towards his PhD. They're growing silicon on silicon dioxide. Next slide will show you that. And so there are parts of this circuits which involve P region, P-doped region, N-doped region, and oxide. All these things have to be, their properties had to be controlled and optimized. And then ultimately they made transistors which were, so CMOS became the vehicle based on which all the rest of the industry grew. But all this was being experimented. So look at the dates, you know, it's 1980. So there were, so this silicon was being deposited on silicon dioxide and then by CVD, and then it was being crystallized. This is a very difficult problem to grow a crystalline material on top of an amorphous material like silicon dioxide. But this was done, and I will show you a minute in that, and devices were fabricated. Chandrasekhar also left TIFR to go to Bell Telephone Laboratories, where he became the leader of development, subsequently integrated optoelectronics for optical communication. So this is a picture which shows this is a as deposited silicon. You can see diffraction rings, which is polycrystalline, and then same has been crystallized here, and you can see the dots which belong to the crystalline material. And this is a device made MOS transistor, and this is the first time IV characteristics of such a device. The other person who led the research in silicon was Arvind. As I told already, he was doing PhD in high energy physics, I think so, in theoretical physics. And then he came to solid state electronics group, and he worked on this. This is a structure, by the way, that a MOS structure. So this is the metal, oxide, and semiconductor. So it looks very simple, but it has all its complexities, which were and there were some things which called reliability or instabilities of such devices, because devices work at very high electric fields, and then so the electrons can go from metal to the insulator, and then they can change the threshold of transistors and various things which can happen. And he was studying that phenomena with his student Lakshmana. And the other thing is that so this is according to so when Vengadekar joined the group, so there was other things which were going on at the group, was large scale integration design, and then there were several other people who, some of them I don't remember now in the pictures, I could not get. And Subramanian was working on tools for making these circuits, layouts, and using some of these tools. Vengadekar also made a circuit which was the NMOS static RAM LSI. So you see, it was a group which was not only working on materials, devices, but large scale integrated designs and then rendering them. TMS Murthy, he joined as a postdoc, I think from ISC he was a PhD, and then he was actually making these fabricating chips in the laboratory which was established by Pinto. So only this member joined semiconductor complex later on. There are some other things. TIFR was also spreading the culture of this technology which had got acquired, and so these people went to IIT Madras and then offered courses, and then several students were coming and doing projects in these things at TIFR, practical projects. And there was, of course, now these periods are much later periods, and the technology was, there were two from Opte. And so there was a project, UNIDO, UN project, where Pai and Apte and Joshi, they went and established this technology there, and with 90% yield according to Apte's report. And then Apte also established bipolar transistor technology in 1988 at IIT Kharagpur. A.V. Joshi, who I mentioned here, was a very competent chemical engineer. In fact, he established a company. This is another factor which happened, that people from TIFR, they branched out and had their own companies, and he helped them, I think, this high energy physics detectors, and Mandal may know quite a bit about it. And the other thing is, Pinto started this. This is now in still in 70s, and so he spent some time in Alan Clark Research Center in UK, and then came back and they made charge coupled devices. And for developing that, there was, earlier I told you the gate was metal. Now for these requires high precision and silicon gate instead of metal gate, and that technology was developed. And at the same time, believe it or not, he also made in-house an ion implanter to shift the threshold of transistors, etc., etc. So you see, all these developments were occurring simultaneously, developing our instruments, etc. All of us were involved in how we hardly bought any instruments. We mostly developed them over here. Now, most of the people who worked on silicon, they shifted house, they shifted their nature of work because semiconductor complex got established. Although it was initially supposed to be an initiative from TIFR and political leaders of the country, but ultimately that didn't happen. That story I'll tell you at the end. But in the meantime, the members had started looking for other possibilities, and then this happened. High temperature superconductors were discovered in 1986, and TIFR also, there was a lot of excitement, and Pinto decided to work on thin films of these new materials. He had these sputtering systems. As I told you, he was a master builder, and he had several such RF sputtering. So he started with this, but he found that there was these were multi-element systems, so there was non-stoichiometry. And following a visit, which was attended, house, our AG16 was full. I also remember that day. And the pulse laser deposition, Venkatesan said that it is very suitable for these multi-organic, multi-component films. And so Pinto shifted immediately to this technique. And then in this Pi helped him a lot, and Opte also started working on the microwave properties of these thin films, because it was supposed to be something which films were the applications of these high temperature superconductors. Now, as several people have remarked here, SP Pi went on to establish Excel Industry, known for excellence in design and fabrication of vacuum systems, supplying to labs all over India, and not only India, several people abroad. He also has supplied this pulse laser deposition systems elsewhere. This is another activity which is much later, but this was done simultaneously while Opte was working on other things, because we established an electron beam lithography on electron microscope we already had. And then so when I established this, then there were many. So this is a micro electromechanical systems, which is a sensors based, and Opte always had interest in sensors, and so he used this activity to design such systems in TIFR. Let me now go back. So I have covered large part of the silicon and related materials and activities. What is happening in the gallium arsenide? So gallium arsenide was started, as I said, in late 70s, late 70 or 71. I joined in 72, so some basic system already existed, which got fabricated. In 1974, Subramanian joined this activity in this group and started working on growth of epitaxial gallium arsenide films. And now there was lots of problems which I don't want to get into, but there was one particular thing, that the surface of the material substrate on which we were growing films used to get affected during the it's a process which occurs at some 700 degrees centigrade. So some deterioration of that surface used to occur. So we decided that we will freshly etch it by a solution which is undersaturated, and then lo and behold, we made some publications on this, so that the nature of the liquid phase epitaxy growth became very nice and regular and shiny, and it's reverse quality. So we did make devices subsequently, but not only that, the activity expanded to include many materials, aluminum gallium arsenide, gallium antimonide, etc., etc. You can see there's a whole range of 3-5 compounds we could grow. And one of the students spent part of her PhD growing these aluminum gallium arsenide layers and studied the property. Raj Lakshmi also studied some of these materials. A student from Bombay University, Prakash Murala, also studied some of these. And Suresh, who has been here, who was my colleague, and we advanced these things. So now we could grow some materials in which we could make devices. So for doing that, you need many layers with different materials, etc., etc. And there was a board design which we chose, which was perfected in a laboratory in IFA Institute in St. Petersburg, and I had connections with them. And so Suresh spent some time with them, and they also came. And our glass blowing shop made some very nice graphite boards in which we could go 6-layer, 7-layer devices, and we made ultimately high quality diode lasers. That story I will tell you. The other work which got started, which Subramanian participated was, so the defects, as I told you, defects play a big role in the semiconductors. And so it is the job of persons working with semiconductor device physics or semiconductor material science to investigate these defects. And something called main electron trap, this was investigated. It was suspected it may be due to oxygen, but later on we made materials with oxygen and various things. Subramanian studied these things, and that was the work he did. Then there was another defect called DX center. We'll not like to go into details of this, which so this is another interesting thing. This defect was discovered in gallium arsenide under applied pressure, but it occurred naturally also in aluminum gallium arsenide alloys as grown. And so both of these types of materials studies were done under pressure, etc. And something called deep level transient spectroscopy was also established. This group discovered, so when we were making so many things with alloys, we also discovered that the signatures which you get by those DLTS, they were broadened, and they were due to the alloy disorder. Something called alloy disorder is so these are crystalline materials, but nevertheless, because compositions have fluctuations, local fluctuations, and they give rise to changes in the signatures of the. And then also Narasimhan realized at some stage that we were measuring properties of these defects, which are energies and then cross sections for capturing the electrons or holes, and something called Mayer-Nelder rule applied to such things. So there were several people who contributed to Vijay Singh, who was partly a postdoc theory physics, also participated in some of this. The other work which started early, and Guhas had initiated that in 1977, was the work on junctions. Metal semiconductor junctions have played classically a role which is investigation of you have to make metal contacts to semiconductors, but metal semiconductor contacts are not necessarily oblique contacts, and so one has to study their physics. And so Atul Srivastava joined in 1979, and he carried out detailed investigations of current transport in metal semiconductor contacts. And subsequently, he also applied it to some form of transistors, which were phototransistors, and people from Samir also participated. Another area in which I worked was, you see, insulators on semiconductors have always played a very important role. So we worked a little bit on that. And some work was also done with Kurup and R.P. Sharma on the ion implantation of such materials. Okay, so this is the break where we have now looked at what was started early on, and now there is going to be a break in the activities of persons, and optoelectronics would emerge. Okay, if it is 5 minutes, I will be very quick. So, so there are 3 different areas. I continued with optoelectronics of 3-5 compound. Optoelectronics meant lasers, work with optical spectroscopies and devices. And then there was work on organic semiconductors and ultra-fast optoelectronics. Fortunately, ultra-fast optoelectronics, some of it was covered by Ravindra. So this is a school which organized in 1989. It was organized with help. So it turned out that Atul, who is somewhere there, he went to US in Bell Labs, and then he became familiar with, and so many of the speakers for these schools came from this Bell Lab. Okay, so let's see, what do I want to do? So this is Atul, and Atul MOVP growth. So we acquired an MOVP growth system. So this is a first system. The rest of the things we used to build. So this was a system which we got it, and then he optimized the growth, not only optimized the growth, and he made multi-layered structures, which included quantum wells, which I worked on for many, most of my students worked on, but he made lasers in 1993, and these are modes of cavity, longitudinal modes of the cavity, and then all this luminescence spectroscopy, etc., were established. And see some of the devices which we made, up to 1 watt diodes which we made, etc. We also made some quantum well based photo detectors which worked in the range of around 10 micron, etc. And porosilicon is, you see, silicon is not a good optoelectronic material, but there was this material called porosilicon, which was emitting red light. It was very strange phenomena, and Narasimhan looked at it, and Sonali looked at it, and they came to some conclusion that this is some emission due to some related to internal surfaces of porosilicon. This is a very important development which occurred in the institute. Much has been said about the collaborations, but this is between Narasimhan, who was working, of course, in solid-state electronics, and then Professor Paris Fermi, who was in chemical sciences, and they combined hands to work on optoelectronics of the organic materials. And so there is a lot of students who worked with them. He was a synthesis chemist and he was a physicist, and so they combined and the students went from one lab to the other. It is very rare such things happen. And the ultra-fast optoelectronics was, of course, has been said earlier by Ravin Kumar, was led by Bengaluru, and work was on done by Prabhuji and Vipul Pal, Rajesh Kumar, and Achanta Gopal. And this involved ultra-fast optoelectronic process in semiconductor and plasmonics. And so this picture was earlier. This is a transistor picture, and this is a quantum laser picture. And what you're seeing is that the electrons are at very high energy, and how they relax. That is the process which is being, and here they are recombining electrons and holes, and how fast, etc., etc. Those are the things which you. So this is one of the pump probe experiments in which there are two beams. One is a pump beam, another beam which can be delayed with respect to the probe beam can be delayed with respect to the pump beam, and then you can measure the transmission, reflection, photoluminescence, wherever or whatever. It depends on the technique. And then so this ultra-fast pulses based exploration of semiconductor nanostructures and work on cosmonics and terahertz at TIFR remain unique in India even to date, and it has been commented upon others. And then you see this is a mixed state of electrons and photons called polaritons. And so that was so electrons move under electrical field, but they're slow. Whereas light is fast, but it's not controlled. But there are these species, they are called resonances, which can be excited, and they can be used hopefully in futuristic. This is futuristic. Can you make contacts in which the delays are not by RC like time constants and things like that? And so my students, of course, they worked on spectroscopy of these quantum structures. Nagarajan showed a quantum Hall effect signature, which I will not, this is some laboratory which we had established. And so the quantum Hall effect involves both Bell states and edge states. And Viswajit, he was able to look at spectroscopy of electrons at the edge, as well as spectroscopy of the electrons in the bulk of this quantum Hall effect materials. So now I will require some 3-4 minutes. Yeah? What I want to say is that what is the story about this semiconductor complex? I think it's important to know this story. So in 1976, the government of India made a cabinet decision to establish semiconductor complex. Dr. Zarabi, he was a PhD from Institute of Science, Bangalore. He was the officer on special duty, and Professor K.V. Ramanathan was the project director. K.V. Ramanathan, which I already described. At that time, it was anticipated that semiconductor complex will come up in New Bombay. It was clear at this stage the future of integrated circuit was MOS devices. I already explained. Professor C.R. Vishwanathan, he gave a set of very nice lecture, and many people from the country actually attended that. So there is Zarabi. He was actually managing director of this complex from 1993 to 2005. Dr. Zarabi was operating from the Air India building, which is located close to TIFR, and he had a lab, etc. And according to him, he was attending to work in air in the building in the mornings, and in the afternoons, he will have sessions at TIFR and discuss various aspects of what is this semiconductor complex going to be. Now, this is a quote which I quote from a report, which is from the so Ashok Parsarthi. He was the Electronics Commission Secretary in 70s and early 80s, and he has a paper called Building Capacity in Electronics Sector, which is shared by Dr. Zarabi with me. And this is a quote I'm giving you from there. An important aspect of setting up and launching SCL was the selection and appointment of Mr. Virendra Mohan as SCM, the chairman, managing director of SCL. And this is Parsarthi. I got Mohan's summary biodata and took it to Mrs. Gandhi and convinced her that he was the right person for the job. Mohan took charge of SCL in May 1981. So this is how the TIFR, so all of us, in some sense, in the early 80s, we had a great uncertainty. It was sort of rumored in our group that solid state electronics is going to close, because most of the people will go to SCL. But it so happened afterwards that none of us actually went to SCL. In the context of our and eventuality, none of the other persons except TUMS, he was postdoc from ISC, joined SCL. It is useful to consider a hypothetical question: what would have been the course of process? You see, you hear a lot about chips and this and that. We were working on these things at that time itself, right? And then if a whole group of very talented persons from TIFR, all working in various aspects of NMOS, PMOS, CMOS, process technology, VSS design, computer design. So SCL tried to recruit technical persons from abroad, but none came. It is my gut feeling that if the leadership of SCL had come to TIFR, the outcome could have been very different. Okay. So now there was subsequent participation. Dinesh kept on participating. He went on going to SCL and gave lectures on the design aspects. And so happened that many of the people he trained, they eventually left the SCL and rose to senior positions in international companies when these came to India. So you know the desire that several software companies have come to India, and where the people came from, Dinesh and his training. This is probably the last slide, and many people from all over the world have been involved physically, coming to TIFR, spending several. So Professor Gottfried, he used to come for 20 years. For every year, he spent 1 or 2 months. Currently, also he has collaborated with Prabhuji and Jagdeep Shah. Of course, you heard he was with Vangur later, and so K.S. Chandrasekhan, professor, he retired from Madurai Kamraj University, and his son was in Bombay, so he came and worked with us for nearly 10 years, etc. Prusken used to visit theory group, and once we invited him to our quantum hall result, and then he said, oh, he understands what we are getting, and then so there was some papers like that. So there are many people you can see all over the country and various parts of the world who have contributed to various things. This is just a partial list. Future. Oh yes, it's the last slide. So TIFR continues to engage in areas of basic and applicable sciences. This applicable word should be taken properly, because at one time, as I told you, Institute of Fundamental Research, we were sort of, well, in some sense, in the beginning of 80s, we sort of were supposed to leave institute. So one should think how to evaluate people. That's a very big problem. And they keep the nature of the work keeps on changing, but evaluation is important, and so what should be done about it? So state-of-the-art nanofabrication facility was established, that Ravindra Kumar said, and that was done by Arnab and Mandar Deshmukh, and so and Achanta Gopal, and they make their nanostructures and devices, etc., for application. Arnab Bhattacharya, of course, has been. I'm sorry that I have not any more slides than this, but you have seen some of their work, and then more is required. They can tell you also in separate seminars. Nanowires he has been making, and nitrides of gallium and indium are mentioned by Ravindra Kumar. Sandeep Ghosh, of course, has advanced. The spectroscopy looks very grand lab now, as most sophisticated multidimensional subject and applied to study many materials as well. Pedagogy, of course, has been developed into deep into various aspects of terahertz spectroscopy, generation, detection, application. And not only that, Pedagogy has been recently helping Pedagogy in developing novel fuels as structures for clean energy. You know, this is possible in TIFR, and people can talk to Pinto about it. Achand Gopal, of course, made those photonic band gap structures, which are the basis of these new type of optical properties based on nanomaterials. And Mandar Deshmukh has delved deep into investigations of various types of nano devices, where he investigates electron and phonon transport in graphene and many heterojunctions, etc. And Vijay Raghavan, of course, he is doing excellent work, superconducting devices for quantum computing. Okay, thank you very much for attention. Yes, please. Okay. Yeah.
Thanks, Professor. It's really pleasant to delve back into those old times when we all worked together. And those were heady times, really, when the excitement of a new field which was developing even as we were working in it. So, so it is great to reminisce about those days. Thank you very much.
Thank you, Professor Dinesh Sharma, for conducting this session. And also thank both the speakers for such a wonderful journey that you took us through so many years. So now our second session is over, and now we will break for lunch, and we will come back here at 2 o'clock. Right now it is 1:30, 1:20. So another 40 minutes. If possible, we can come back at 2. Thank you very much. Okay, good afternoon, everyone. I hope you had a very nice lunch. And now we begin our session 2. Now, may I request Professor Shobana Sharma to chair this session, and there will be 3 talks in this. Professor Shobana Sharma, please.
Hello, everyone. So this is going to be a largish session with 3 speakers. And I will request the speakers to keep to time. So let me first invite Professor Paritosh Pandya, who has been in TIFR from 1988. He was a researcher at the Oxford University Computing Laboratory. And this was as part of the Spirit Pro-Cos project. Pandya's main research interest lies in the area of formal methods, including real-time systems. He has been specially involved with research concerning duration calculus, including the DC valid model, model checking tool. His paper won a 2020 Test of Time Award. This is very prestigious. This was announced on the 27th IEEE Real-Time and Embedded Technology and Application Symposium held in 2021. And he has, of course, many other awards and positions. And currently he is with IIT Bombay. Paritosh, please.
No, yes. In a minute. Yeah. First slide.
Oh. Thank you, Shobna, for that very generous introduction. It's indeed a pleasure to be here back amongst friends in this hallowed hall, and I've been asked by Bahia to talk about computing activity, at TIFR, spanning all of this 75 years, start from the era of valves to artificial intelligence. So I will try to do that. Now, throughout human history, we have passed through several revolutions. The last one was the Industrial Revolution, and people say we are in the middle of knowledge revolution. We are in information age, and which means knowledge activities are dominating the way the society is functioning in a very disruptive way. And digital computers and communication form the backbone, the nervous system through which these knowledge enterprises are being conducted. Okay, so I won't go through this detail, all of this, but the vision is that all gadgets, things around us, are going to get empowered with sensors. They will sense their environment. They will have a little bit of intelligence and computing power. They will make autonomous decisions. They will be connected to internet. So there will be worldwide internet of things apart from people. And these gadgets will talk to each other and cooperatively or competitively solve problems for us and, conduct our lives. So this includes wearable devices that we wear. It's already talking to the phone. It will soon start talking to your GP and your hospital. Your car will be in touch with the garage. And all the ACs in a big institute like TIFR may be networked, and they may cooperatively schedule their starting and stopping so that the peak load, is reduced. All of them don't start simultaneously. So extrapolating from this, there are all these visions of smart cities, smart health, energy. I won't go into it. Our government has set a big agenda of digital transformation of certainly governance, but also commerce, banking, everything. So in such a society, study of computer science as a discipline is a major area of technological growth and also of scientific study. And while this is happening now, TIFR got into the game very, very early. The story is that, okay, I can come to that story a little later. It's difficult to, it's a young subject, computer science, difficult to classify it neatly like physics, into light and condensed matter and nuclear physics. But broadly, if you look at computer science, you can say that work centers around study of these things. You know, there are algorithms. You know, these are step-by-step methods of solving problems. Then there are programming languages or computing systems, and you formulate the algorithm in terms of this computing system. Okay, and finally, there are devices, physical devices, which follow that algorithm by executing it step-by-step mechanically and calculate the result for you. Okay, and then there are many applications in the artificial intelligence, cryptography, where you would want to develop algorithms specific to that area. So the subject very roughly goes like this. Now, algorithm is a step-by-step method to calculate answers to a problem, and this calculational style of working has actually been done with us in science, in mathematics, in thought for ages. You know, throughout the history. For example, here is Euclid's algorithm to calculate the greatest common divisor of two integers. And it occurs in his book Elements around 300 BC. Okay, so I will not go into details of algorithm. You can all understand what it's doing. And the name algorithm comes from this Al-Khwarizmi, who was a polymath of Persian Uzbek origin. You know, he wrote some treatise on mathematics, and this became very popular in communicating Hindu, Arabic mathematics to Europe. So his two most famous books are Kitab al-Hisab al-Hindi, which is book of Indian computation. All arithmetic in India was done in a computational style. And in fact, the algorithmic style of mathematics, astronomy was very central to Indian enterprise. And I won't go into the details, but I had a few slides, but we don't have time. So Brahmagupta talks about, you know, solving quadratics. He says somebody who can do it will be called Gana, you know, a computer. And, you know, Panini had this grammar system. You know, you could understand language only by parsing it into a grammatical structure. And his he had 4,000 rules. And, you know, many of those rules will apply. So which one would you use? Like many moves in chess. So there are meta rules to govern these. And there will be some confusion about these meta rules. This Indian Express news is just 2 days old, 16 December. The major solution to this meta, you know, which meta rule will govern Panini system was solved by a student at Cambridge who originates from Bombay, Raj Popat. So you see, again, rule-based reasoning. So computation is being done. We use differential calculus. Again, there are calculations there, right? And calculational style of working, you know, deriving things is something that we all know. Now, of course, this algorithm is specifies what are the steps of this calculation and what is the order in which they are to be followed. And these have to be prescribed in terms of a certain notation, a certain computational model. Also, nowadays we call it programming language. And you know, the prominent programming language we all know, C, C++, Java, but there has been an evolution of this language, and this mathematical computational systems in which you could specify algorithms was something that was studied by very celebrated mathematicians and logicians over hundreds of years. So here are some very prominent systems of programming, if you like. There was this golden system of new recursive functions. So here, this GCD was an example of a recursive function. In order to calculate, oh, I'm so sorry. In order to calculate GCD of numbers in B, you would reduce the problem by some simple arithmetic operations to calculating GDC of some smaller numbers. And when the numbers became small enough, you could give the answer. So you could recursively solve the problem. Similarly, you could do same computation repetitively. And the insight of computation was that very simple steps of computation, but long sequence of such steps carried out can carry out phenomenally complex calculations and give us a power which is, you know, tremendous. Okay. Okay, so that's all I want to say about computer abstract, this programming languages or models of computation. I use models of computation rather than computational system for another reason. You know, it's not just notation. You just don't learn, you know, what are the permitted statements. You also have to understand how they behave. You know, while each statement of the programming language may be utterly trivially simple to understand, their organization into a big program gives rise to a complexity which is very difficult to master. You know, programs are amongst the most complex artifacts made by humankind. Your Microsoft Word, you know, editor, text editor, has over 1.3 million lines of code. Your Windows operating system has over 63 million lines of code. This is not the number of parts in Apollo 11. And we've got to somehow program this thing, organize that program, understand it. So we need mathematical abstractions, to understand how programs behave. And since these programs are cast in terms of models of computation, we need to know the properties of this model. Roughly speaking, if you are building an amplifier circuit, first you have to know how the circuit elements behave. They are active or passive. You have to develop a mathematical theory of that. And then you have to have techniques by which assemblies of such components are analyzed. Same thing have to be done for programs. Okay, that's why programming languages implement certain semantics and analysis, which can be called as models of computation. Okay, so programs are written as algorithms. They are expressed in programming languages, and then we construct machines which will mechanically execute those programs. You don't have to do it by pen and paper yourself. And search for mathematical systems of programming has been over the years, by people like Goodwin or Church or Alan Turing. Studying of computing machines also goes back, far away. There are much older machines, but here is a machine constructed by Leibniz, who gave us differential and integral calculus. It was called step reckoner, which could do these 4 operations, and it was working in decimal number system. Gear positions represented what digit it was. There was a bank of gears, and somehow it could do all this. Okay, Babbage will just store program. So after that, many fixed program computers were made. A computer, which would calculate the insurance premiums, because he was employed with actuaries. And for shipping, insurance had to be calculated. He designed a specific computer for that. But Babbage went on and designed the idea of a store program computer, a general purpose computer, to which you could give programmers data and give it also data when that program is to appear. So both these are fed as input to the machine, and then the machine will execute that algorithm. So now algorithm becomes input to the computer. And that revolutionary idea came first with this Babbage's machine. Babbage actually designed this machine. It was far ahead of its time to implement. We didn't have the machining technology to produce such a machine, but a model of this you can find in British Science Museum. Okay. Pardon? 18 something. I don't have. Yeah, it was quite a way back. And Shannon, all these machines work on decimal number systems with gears and rackets and pinions, transferring the state from one gear to another, etc. They are highly unreliable, very difficult to fabricate. That one, Shannon, who was the information theorist, was used to the idea of a system which could be in a number of configurations, and so each configuration carries a certain amount of information, certain bits of information. And so he naturally thought our calculation, which was of interest, could be cast in terms of calculations over bits. You could use Boolean algebra to do all forms of scientific calculation and communication, right? And so he propagated the use of Boolean logics, and we thought digital circuits could be used to do computation. And you could put all the standard computation in decimal into this. So somebody has called this Shannon, this was his master's thesis. Somebody has called this the most impactful, most celebrated master's thesis ever. Because this revolutionized the world. This idea caught on, and people started designing digital computers from that point of it. Also, electronics was growing, which was giving us digital devices which could be used in switching modes, valves, transistors, they don't have to necessarily be in the linear part, they could be put in switching mode, right? So, and then they have to switch very fast and very reliably. So this was a happening technology, and all computers after that were designed using digital technology. Okay. Many different architectures, many different shapes of computers were tried, but the one that was called von Neumann architecture. And all the early computers, were based on von Neumann architectures. It has some limitations. We are trying to get away from it, but still, the basic model of computers that we have today is also largely von Neumann. So this has been a revolution, very, very strong idea. And what was the purpose of such a von Neumann architecture machine? Well, it was idea of, machine program as a sequence of instructions, and each instruction was a simple step of calculation. Add numbers A and B, which are in some memory somewhere, and store the result into some memory location C. Okay, and there will be jump instructions which would change the flow of control. You could execute parts of code again and again repetitively. You could do many such things. So that was this thing. And the key idea was that data resided in the memory. So memory had both program as well as data. And one computer would fetch one instruction of the program at a time from the memory into the CPU. It will decode what this instruction is supposed to do. Then we will fetch the outputs of the instruction from the memory. Pass on this data to P and set it up in a mode that will do the required operation, addition, multiplication, whatever the instruction said, and then we will get the result, right? And this step would be repeated again and again. We know this. This following architecture was what was followed in all of these early computers, early digital. They were all made out of walls. And question of how to build large memories was a big technological challenge that days. It was in this scene that TIFR started making digital computers. I've read it somewhere, don't hold me to it, but I think an article by Dinesh Singh or somebody which said that Nehru in one of his visits, I want to go by honorifics, excuse me for that. And one of his visits learned that computing was a strategic technology. It had already broken code in Second World War. It had been used to optimize linear programming programs, for during the World War for supply management and many scientific, and much of this work was underground. But he understood that computing was a strategic technology. And so he put his two generals, Mahalanobis as well as Baba, to the idea of designing an indigenous Indian computer. And they designed an analog computer at ISI Calcutta. So the first computer is an analog computer at ISI, but analog computing just didn't, live on. It had severe limitations. But Baba went in for the digital computing technology, and they designed this machine, which is now called TIFR. The chief designer of the machine was Professor R. Narasimhan, who went on to get a Padma Shri for this and his other work. But actually, the work started around 52 in the electronics group, in the electronics instrumentation group. I think the group was headed by Fadke, and BK Basu was leading this digital computer design project. By 55, they had a prototype machine, which had some severe limitations, but they already experimented the key digital technologies, and a prototype was already there. At that point, Narasimhan fixed the design to, be like one of the standard von Neumann architecture machines, and in a very short time of 3 years, they produced this computer. Okay. I will not go too much into technical details, but it had some nice features. It encoded some fast arithmetic circuits. For example, when you're adding two binary numbers, the carry has to return through all the bits, and they did not use that. That takes too much time. So they stored the carries somewhere, and they included the effect of carry on the next instruction. So what we call instruction pipelining is what was already happening there. And P.S. Rao calls this the Basu Rao adder. Okay, there was an MQ bit which speeded up computation. There had a special place for carry bit which allowed you to change long integers into small bit sequences. Okay, so these are really good features. And perhaps the most important feature was that it used ferrite core memory in 3D matrix. This was absolutely state of the art. I think the matrix design and the backbone was imported from a company, and then the ferrite core memory was wound up here. Okay, so the machine had 1024 locations, words which it could store. Each word was 40 bits, and a read time was about 15 microseconds, and there was I/O. So I think, okay, another nice feature was that it ran from paper punch tape. I think Nagarajan referred to this. He ran programs written on paper tapes and also teletype, but there was a CRT display. So you could actually display, scientific functions on it. And that was very state of the art. Okay, the machine had 2700 vacuum tubes, 1700 germanium diodes, and it consumed 20 kilowatts of power. Okay, it could execute machine language programs. There was a system of machine instructions, and there was a program called Kane. It was a new device, and here is the photo of TIFR. Unfortunately, the machine is lost. I have not been able to see any design documents of the machine. There is one paper by R. Narasimhan in Journal of Indian Science Academy. I based some of the work on that, and P.V.S. Rao has given his memoirs. So, but some photographs are all that we have. No parts. Yeah. That is what I was told. Second floor end. See, this is all second information for me. This is much before my time. So, second floor end. CDC was second floor end. No. Okay. C wing or something. Oh, no, B wing end. The C wing end. Okay. Anyway, we could find that out. And this is, the machine became operational in 60 and people started using it. In 62, when we moved to this new campus, the Prime Minister Pandit Nehru inaugurated, named this machine as TIFR Advanced Calculator, TIFR. So this is certainly one of our major milestones from area of computing. Okay. The machine operated from 60 to 65. People had to be taught how to program devices like this, which was done, and then several cosmic ray people cite use of TIFR in their computation. Users were people from TIFR, BRC, some oil companies, naval dockyard, all this from previous article. And told them the demand was so much that they ran it on 2 shifts continuously every day. Okay. Around 65, the machine was decommissioned and it was presumably sent off to Bangalore. At least it started for Bangalore. Okay. So we decommissioned the TIFR around 64, 65. What happens to computer science? This is the phase 1 of computer science activity, according to me. PSRF says that even if the machine stopped, the spirit of TIFR lived on. And TIFR continued to design computing systems and system software for next 20 years. Okay, so on the strength of this, TIFR was designated the National Computer Center. It purchased a very advanced computer for that time, CDC 3600. So your last question mark is a 0. Yeah, and because our people were designed as a computer, they immediately wanted to see what was inside, and they maintained the CDC machine locally. Okay, and it became a national resource. People from all around the country were taught how to program this machine. TIFR and many courses. And today, if you go to any major government lab or an academic institute, you'll find people who used to come to TIFR and program, not just this, but the next machines that we bought also. Okay. Previously, I designed a machine called for real-time data acquisition and control of physics experiments. It was used on bubble chamber experiment. And so all this era of spirit of TIFR, where we continued designing machines, I call as phase 2 of TIFR computing activity. Okay. There was a Baba committee report which said digital technology and computing technology has to grow in the country. And because of that, Government of India set up Department of Electronics and an Electronics Commission. I think M.G.K. Menon became the first chairman of Electronics Commission. And under the umbrella of Department of Electronics, a large project called National Center for Software Development and Computing Technology, NCSD City, was formed. The story of computer activity is that, that of search for identity. It kept changing its identity. The work began with electronics group, then a computer group was formed when it became a national center, and now we have NCSD City, okay, which is its third incarnation. This was funded by Department of Electronics and United Nations Development Program, and it acquired state-of-the-art commercial computers, the 1077 or later watts, these were used as national resources. So as I said, people from around the country came and learned how to use these machines here because it was new. Very few places had them, and then used it for their computation. And you will find this having certainly a large impact on the national computing scene. There were a few research projects carried out at NCSD City along with this facility that we had. There was a project called CCN, where they designed a computer which is a closely coupled network of multiple processors. Today we are used to having multi-core processors, right? But right at that time, they were talking about how work could be divided within multiple processors and how a machine with multiple processors could run. And so they designed this multiprocessor computer called CCN. Major challenge in systems that was the system software. the language in which operating system is to be written, the language in which you prefer. For example, to write the Unix operating system, then it was designed language C, and now we use it all. But it was designed to write the operating system. At that time, perhaps a major course in operating system design, Perbrink and Son had come up with a language called Conquer and Pascal. And TIFR designed its own version called CC and Pascal. They wrote compiler for it. They wrote the multiprocessor operating system in CC and Pascal. And this design was very systematic, celebrated that a book on this multiprocessor operating system was published in the Prentice Hall CR core series, with Mathai Joseph, V.R. Prasad, Natarajan as authors. Okay, so another milestone, okay. At this time, computers started getting connected to each other and they started talking to each other. Digital communication was coming into play. Most of the communication in the country was analog. Signals were sent, at different frequencies. But digital communication was coming in. And Raman started experimenting with digital communication over satellite channels. I have a personal account. I was a young undergraduate student doing summer internship at Space Application Center, ISRO in Ahmedabad. And they asked me to design a little bit of circuit of this loop, which would communicate between Ahmedabad and TIFR over a satellite channel. You got 20 minutes per week. And they told me that there is somebody called Raman in some place called TIFR. And I was destined to come here. So it's a very pleasant memory. But he did this experiment. And we also communicated with digital communication over telephone wires. But the major issue in digital communication is the protocol that you use in order to transfer message from one computer to another. It may not be direct connection from source to destination. It will go from several intermediate computers and switches where message may be stored. Message may be broken into packets, and each packet will be stored and forwarded at intermediate switches. Each packet will follow a different route. The most optimal route at that time is what the packet will follow. Some packets will get lost, some packet and will have to be retransmitted, some packets will be predecessors. So protocols had to narrow down it so that you get your files intact. And there was this prominent protocols, in research domain called UCP and TCP/IP. Now we use it all. Raman used them all and implemented an email system and a file transfer system between remote computers. The first implementation transferred these things between TIFR, VJTI, and IIT Bombay, and later other institutes got added, and a big network of universities, was formed. It was called the ERNet, which is, we still have universities with this ERNet as the domain name. So for this effort of Ramani, he has been entered into the Internet Hall of Fame, the only Indian to make it there. And this was started at TIFR. And carried on once NCSD city moved out of TIFR. Okay, I will not go into this Pelletron dot, but simultaneously with Knut designing Metropolitan locally Mudir was designing an Indian font system called Pelletron and an Indian text processor called DOT. Okay, at that point, very large mission node projects were taken up. There was ADGIS, which was jointly done by ECIL, Air Force, DAE with TIFR as the central node, and PVS Rao was the principal investigator, if you can use those words. Okay, he was the head of that project, and it was Air Defense Ground Environment System. It was meant for providing early aircrafts coming into Indian airspace and for tracking these. And this project was completed. These devices were manufactured by ECIL and deployed. And our registrar, who was part of the signals wing of Air Force, tells me that he has seen these devices being used almost 10 years back at Bhuj. So the devices were used. So we worked on mission large, sophisticated projects for the country. Telecommunications was very important. Digital communication had to move into telephony also. And Pitke was very much working in that domain. So there was a project, very ambitious, challenging project, as Pitke calls it, called AREN. It was to set up an ad hoc digital mobile communication network. Ad hoc means new nodes will join and fall out, like in a battlefield, depending on requirement. And some you had to, reliable, secure communication had to be given. And this had to go to UHF radio links, and they designed this system. The main switch was designed at TIFR. So I think Pitke gave a colloquium on this at TIFR, and some of you may remember his account of this. But carrying on from the experience of Ireland, he later went on along with some Petrograph to build CDOT, the rural digital telephone exchange. Telephone exchange was, first rotary and then analog electric, and this was a state-of-the-art digital exchange of 10,000 lines only, and it had a very major effect on telephony in India. It catalyzed the use of digital telephony at affordable prices to the country. Okay, so there are these large mission mode projects. Okay, and that is phase 2 of TIFR's activity. This activity stopped around 85, but I'll go into that little later. Simultaneously with this system building and system design, very sophisticated system building and system design activity, there was, there were other things happening worldwide, See, computing machines, sophisticated as they are, is not end of the story. There is also algorithm which you want to execute on the computer, and there has to be a language in terms of which you want to express what that algorithm does, right? And there is deep sophisticated mathematics behind algorithms and models of computation, because they are fairly complex objects, right? And so Dijkstra, is one of the big names in computer science, and a Turing Award winner. Turing Award is our Nobel Prize, so-called Nobel Prize of Computer Science. He said computer science has as much to do with computers as telescope has to do with astronomy. Okay, and what was the other academic part, intellectual part of computer science which was being discussed? It didn't happen so much in TIFR, but also these things were going on. For example, we have to ask, how do you come up with an effective algorithm which can efficiently solve my problem? What are the strategies to be used? And nowadays we teach this in undergraduate and postgraduate programs as a subject called design and analysis of algorithms, right? For example, the GCD problem, we saw that computing GCD of a large number could be broken down to a GCD of a smaller number. This is the structure of mathematical structure of GCD computation. We can exploit this to do it. So study of this kind of things is what goes in. Okay, once you have built a program, it's a huge complex object. How do we master its complexity and understand what it does? In most branches of engineering, an artifact has a mathematical model, right? If a circuit is there, we know how circuit elements behave. If they are passive elements, we know their impedances as complex elements. And we know how, when these circuit elements are connected, the assemblies behave, right? So we need a theory of semantics of the artifact that you have behaved. And you do only mathematical analysis of your artifact to find design flaws not before they are constructed. The area of formal methods addresses this question for programs and algorithms. Okay, and the question is, how are we going to model an algorithm? Can we use differential equations, linear algebra? And the answer was found in logic. Turned out that logic was very, very useful in modeling, it's a general reasoning system. It applied to this. And special logics dealing with program correctness were developed called logics of programming. These are some of the founders of it. And all 5 of them went on to win the Turing Award, our Nobel Prize, okay, for development of this. Another approach was, you treat a program as a dynamical system. It takes the current state, each statement transforms the state to another. So you have a big state space and movement between them, right? And you explore this state space algorithmically using large graph search algorithms. This approach is called model checking, and that is also become very prominent. And these 3 people, Emerson, Clark, and Sifakis, won their Turing Award for introducing this work. Now, who visited TIFR in 77? Nearly visited several times in 90s. Lamport visited 5 years back. My last dinner in TIFR rooms was with Sifakis. So, TIFR was there. It was listening to all these ideas. And something of that carried over. I will not go over it. There are more questions to be, answered about programming, models of computation and programming languages. Maybe I will point out one, the complexity. Here we See, in theory of computation given by Turing and Gödel, we only wanted to this problem can be solved with the computer or not, whether it was computable. We never worried about resources required. It was just feasibility, yes or no. Okay. In complexity theory, we started worrying about how much time an algorithm takes to produce the answer. And then we asked a much more difficult question. What is the inherent hardness of a problem? I mean, today, which is taking so much time, n square time, if the input is of size n, can I do an order n algorithm to solve it? These are the kind of questions that complexity theory would ask. And then it would classify problems by their hardness into groups and study interrelationships between problems. So this has been a very rich area of intellectual study in algorithms called complexity theory. Okay, I will skip this, although he is our hero. Our Nobel Prize is named, it's not Nobel Prize, our so-called Nobel Prize is named after him. But along with system building activity, through NCSDCT, a lot of intellectual training happened in TIFR. UNDP and NCSDCT had resources to call international experts to come to TIFR and talk about their work. In fact, some of them are the review board of this project. Okay, and this is a full list. Don't worry about all of it. The ones in blue are the ones who went on to win the Turing Award. Okay, so they were all here during that NCSDCT period. Okay, and they came and gave lectures, short courses, and notes. Some of these were scribed. I can recall two of them. There is CR Ho came in 77, and there are these notes of his called Communicating Sequential Processes at TIFR, and this are before the publication of his very major paper, also called Communicating Sequential Process in Communications of ACM in 78. So we got this before the publication of the paper. Similarly, David Griske and taught compiler construction. Keshav Nori was the main person who worked on this. Later he moved to Kanpur. And I was lucky enough to learn compiler technology from Nori at Kanpur. He spread it elsewhere. Okay. Another thing that happened during NCSDCT was they started an international conference which would always be held in India. Okay, and the first conference happened in 81. TIFR hosted first 6 conferences, but not in Bombay, in Bangalore for cost reasons or whatever logistic. Okay, and this is the proceedings, the cover of the proceedings of the very first conference in 81. It invited. Who of theoretical computer science has come as invited speakers in these conferences. In fact, nowadays they all come without us having to pay for their 10 minutes. Yeah, okay, I'll just close. Okay, and the point is, FSTTCS is in its 42nd year. It's going on right now as I speak, and most of my colleagues, instead of listening to me, are in Chennai attending the 42nd FSTTCS. It has established itself as perhaps the foremost theoretical computer science conference in Asia. Okay, and what was most important in those days is not so much interaction between international science and Indian scientists. And FSTTCS and visit of these scientists became the main conduit for absorbing trends and knowledge about academic computer science, and a generation of PhD students, including me and 4 of my batchmates, we were 5 of us, all found our PhD problems through these visitors and through these courses. So another major milestone for TIFR. Okay, some of the research directions that these visitors passed on also stuck on. One was this area of formal method, how to mathematically model a program and how to analyze it for correctness. This was led by Mathai Joseph and R.K. Shamsundar. Government would recognize that artificial intelligence was a very important problem. This is late 80s. Okay, and they funded a large project called KBCS, knowledge-based computer systems. It was a national project with 5 nodes, and 2 of those nodes were in TIFR. One was with Ramni, one was with PVS Rao. And Ramni was natural language processing and expert systems. Much of it become the big buzzword and the big pro. We entered this, we ahead. And PVS Rao. So now in natural language processing, we are doing Google technologies on language, but these people had started working very early on it. And PVS Rao's group started working on speech technology, both converting speech into written text, which is called speech analysis, and converting written text into spoken speech, which is called speech synthesis. And some nice work came out through both of these. I have only 10 minutes. Finally, there was some work on real-time computations, and I will not go into this, but there was this equation that we contributed. That equation, this is for checking whether real-time programs, controllers sitting on onboard computers of a space launch vehicle or a Mars pathfinder, meets all its timing requirements. And analysis of that was a problem. So this equation was solved that from TIFR. This was a slight break with the tradition, and that took root, and it's been extended in many ways. The Mars lander, I think sent in 71, actually failed because of scheduling problems. Okay, and it suffered from a problem called priority inversion. So this group from CMU actually analyzed the problem, and they said this equation could be extended with this extra term, which would take into account the priority inversion and actually solve that Mars lander inversion problem. And later Mars missions all did this calculation before sending the mission. So, this had direct influence. So this test of time award that Shobna mentioned, actually this CMU group is specifically sort of fitted for doing that analysis on Pathfinder, and the original equation is also given this award in its inaugural year in 36 years after the work. Okay. This is a table from NAC about the highlights of the period that I talked about so far. What happened was in 85, NCSD city went out. This is the end of the mission mode project work for the nations that we used to do, at least in the area of computers and electronics. Okay. NCSD city went out, Summit went out, which was a microwave research center, and TIFR abandoned technological work in electronics and computer science. That should also be called a milestone. Change of direction. India, like most nations, withdrew from designing and manufacturing own computers. The know-how was with companies, we could buy them, and the focus moved to software development and applications. And TIFR turned to the foundational scientific analysis of these objects. Okay, so we made a new beginning. In 88, a new group called Theoretical Computer Science was started. NCSD city was gone. And it had activities in two areas: formal methods, the mathematical analysis of software, and computational geometry algorithms, geometric problems, how they can be solved by computer. And Shamsundar and Subir Ghosh and myself were the three faculty members in 88. Since then, the group has grown. Currently, it has 18 faculty members in diverse theoretical areas of computer science. So, we have come far from there. Here was again a slide which was presented to NAC in 15, showing how new areas got inducted into computer science activity. In 88, this theoretical computer science group, now we are no longer NCSD city. In between NCSD city and the founding this group, Mathai Joseph was there for a year, and he started calling us FOP, Foundation of Programming. So you see, we always had this identity issue. Okay, so we are now TCS. And, work was mostly at that point in geometry and formal method. In 91, Jayakumar Radhakrishnan joined us, bringing work on algorithms and complexity theory. Okay, later several people like Kavita and Umang Bhaskar joined. Kavita has some very celebrated algorithms on what are called matching problems. If students, have preferences for which IIT they want to join, which program in which IIT, and IIT has some policies about what students they would prefer over others. How do you match students to this? This is called the matching problem. And Gale and Shapiro proposed this and proposed an algorithm and got a Nobel Prize for this. This problem has become an area. There are whole conferences and courses on this, and Kavita owns some of the major algorithms in this. Similarly, William works on option system and mechanism designs. Okay, so we are working algorithm in complexity theory is one of the largest groups in TIFR. Jayakumar himself is there. He works in randomized and approximation algorithms. Okay, randomization is an interesting idea. Computer programs are definite. They do fixed things. They are supposed to do fixed things. But can you add randomness to the program, and will that give you added power to solve the problem with very high probability in short time? So we are not guaranteed all the time, it depends on the randomness, but you are using randomness and shaping it in such a way that you produce answer A with a high probability. And then you can repeat this so that you can enhance the probability of correct solution. They are called randomized algorithms. You want to produce not the exact optimal solution, but a suboptimal. So such things are being studied. Okay, sorry, I'll wind up now. Okay, Burkhardt came in 99, bringing the idea of system science from electrical engineering. This is control theory and also systems theory. I studied in electrical engineering. Okay, and we, instead of being a pure computer science department, we became an ECS department, like that of Berkeley or that of Weizmann. Okay, and this is the modern trend, So there are not sharp boundaries between some areas of electrical engineering and computer science. So we have a fairly modern outlook there. We became an independent school. Shobna referred to this. In 2000, Sandeep Juneja joined us, bringing in work on applied probability and queuing theory, and he analyzed, financial mathematics, banking, whole banking systems for the risk, the amount of risk they are taking, how to optimize it. And this is very sophisticated analysis using probabilities and queuing theory. So he brought that here, and now he uses this for machine learning. Okay, we are Pelletron and Pranav Singh joined a bit later, and they started studying communication. This was the area started by Shannon, then algorithms moved into communications, protocols moved into communication, and Vinod specializes in analyzing security from the point of view of communication. How much information is there which can be leaked? So he works in information theoretic security. Okay, currently works on quantum information theory. Okay, and so that is the work later, and our latest addition is in the area of data science and artificial intelligence, where we are concentrating not so much on applied artificial intelligence, building one more AI system which will have, you give a lot of data and it learn something, but the theoretical basis of how it learns. Are certain problems learnable? Okay, and we have Hari Narayanan and Piyush Srivastava Asrani joining us. So that is the current group. These are the areas. I already said that. These are the broad areas of work. And one minute can I take? Okay, so I would like to point this out. There are different sides to mathematics, and some very, very foundational areas of mathematics are studied on the 3rd floor of TIFR. In Bangalore, we specialize in differential equations, ergodic theory, things like that. But there is a bunch of mathematics which is applicable to newer computer-like systems. Okay, and this involves use of logics and automata, use of combinatorics, optimization and constraint solving, probability theory, control theory and dynamical system theory, communication theory, information theory and security game theory, data science, all the mathematics behind it. And in some sense, STCS, the computer group, has become a repository of expertise on these mathematical areas within the TIFR system. And I think that is valuable. Problems will come and change, but this will live on. Okay, so this is my final slide. Currently we have a small but world-class group. World-class group is actually words picked up from the last review of the group conducted in 2018 by very celebrated scientists, I must say. And it's focused on specific areas of computers and system sciences. It's a growing group. From 3 we became 18, and in last few years we have increased. And with the group, the average has come down. We are well below 40 on average at the moment. At least in the last few years, there have been 7 best paper awards in some of the most prominent conferences and journals in computer science, and several of these have been won by PhD students. So that's very hard thing. And looking at the shape of things, I can only say that, the way things are going, I can expect good things to come out of here if we just go on. So thank you. That is all I have to say. Sorry.
So, one more there was an effort by some young cats in the late 80s, led by Rajiv Gawai, to bring the Vidyanet into the some Indian PhD didn't take that, so we have to condenser. That's why we are.
I would like to catch up on that. There is also one more connection with us between TIFR and CERN called BitNet. You know, which one also did. Yeah. But UUCP was something implemented by us, indigenous, and it is UUCP and TCP/IP. So, you know, the technical choices were also there. Okay, we'll catch up on this. Thank you. Hello, that was interesting.
I think we'll have to postpone that discussion. Thanks so much, Paritosh. And thanks for keeping time.
That's super. Okay.
More or less. So I would like to invite Dr. Dinesh Daftari. He has been involved in research in cancer and pre-cancer at TIFR in rural India since 1965.
My pleasure, yeah.
And the study was conducted in the Basic Dental Research Unit at TIFR and was fully supported and funded by the NIH USA for more than 30 years. It was one of the path-breaking studies which has come up with so many relevant conclusions. It has brought the focus from oral cancer to oral pre-cancer to the concept of oral health. So I wish to invite Dr. Daftari, please.
Okay. Yeah, it's okay. Wait, because my book, ah. It's good to be back in TIFR. Magesh. All of you have been subjected to esoteric sciences, including me, of course, and TIFR is, of course, too well known for that. So maybe you must be wondering how a dental profession got involved into this kind of academic research at the time of way back in 1965 or so. And if you look at the title, though there is a scientific data being presented today on the subject of oral pre-cancer cancer, but there are reflections I've written here. So there's some tidbits of TIFR, tidbits of our life in TIFR, and these were the rural India field-based research. So there are a lot of factors that got involved into the success of this project. It was not based in the lab or something like that. But you may be wondering how come dental section got involved into this. For that, you must all appreciate that it could happen only because of Professor Homi Bhabha. The man had a vision, and the personality of Homi Bhabha was such that he created a legacy in the fields in which he would not have been directly involved. So I'll try and make this presentation interesting because it relates to the pre-cancer cancer, which has got possibly not be a part of TIFR faculty or TIFR studies. Now, I might just take a few minutes. It was way back in 1965, after getting out of the 2 years back from the post-graduation in oral pathology. I was working with Dr. Fali Mehta, and during that time, Tata Memorial Hospital, Dr. Paymaster, who was a doyen of surgeon, would make some comments that when he was treating oral cancers, it was always preceded by a white lesion. There was no preventive oncology department in Tata Memorial Hospital during that period of time also. And that prompted us to start thinking about it,
because dentistry at that stage was, maybe now also, tooth and nothing but the tooth, and that is the truth. So we are just wondering whether being a dentist, you understand mouth, you understand oral mucosa, go into the medical side of it. So why would you not change the concept of oral health instead of a tooth? And that prompted us to study, because Dr. Mehta was attached also to the policemen, Bombay police. So we started working on the captive population of what tobacco habits could lead to, because majority of all the cancers are related to tobacco, and that was understood very effectively. So during that period of time when I was studying, when I was working on it, I happened to go to Bangalore to speak at a meeting. That time I was trying to figure it out whether I can make a caries vaccine if I could isolate a pure culture. Anyway, it didn't appear. So in Bangalore, I was meeting. At that stage, I met one Professor Pinbog, who was a giant in his field of oral pre-cancer, cancer, working in Denmark. He was visiting professor, and after my presentation, he was sitting in the audience, and it clicked. We understood each other in the sense that he realized that India is a potential to understand this pre-cancer story because of the wide variety of the habit that is practiced in this country. And then he knew Dr. Fali Mehta, then he came to Bombay, and then there was a discussion. Dr. Fali Mehta was convinced that we should do something about it. And we shortlisted that NIH may be the right place to fund the project and so forth. Now, it involved that I should get into the TIFR to begin with, because I was the one who was an oral pathologist. So I was interviewed by Dr. Homi Bhabha, just getting one of the tidbits of him, at Dr. Mehta's office one Saturday morning. He comes down from his flat, from his bungalow at Mehergir in Hanging Garden, sauntering in a shorts with a dog around. And I was closeted with him for more than 2.5 hours when he questioned me on various things of life. You can imagine, if you go back, that was 1965. And that was one of my first interview interaction also with Homi Bhabha. And imagine that interview brought out so many insights for Dr. Homi Bhabha when he started questioning me. Eventually, on Monday, I get a letter from TIFR giving me the honorary position at TIFR with a princely sum of 300 rupees. So that's started my life at TIFR on a basis. And this I've written here, this was the reason we started the work. And unfortunately, today, those days there was only 30 dental schools. Now with more than 350 dental schools and medical institutions and so many hospitals, the statement still holds good. It's unfortunate, but it's a fact. Now that's TIFR. The two people who brought me the vision was Dr. Homi Bhabha and Dr. Fali Mehta. And you have a Professor Pinbog standing here. This was earlier our team who was present at there. We were allotted a 90 square feet is close to the medical section, and we had to start everything from that place. Now, field and follow-up studies which were planned by us were very effectively supported by National Institute of Health. And you know all the research workers that are here, that you are not assured that your research grant will run how long. Originally, we applied for 3 years of research grant. And this was the first phase of the objectives, which broadly speaking, we were to understand the prevalence of oral cancers, pre-cancer lesions, and so forth. But the important point is every lesion had to be photographed. And whatever cytology and histology we did was that had to be sort of recorded in a manner that we can follow it up subsequently. Then those who had the lesions but no cancers, we had settled down for the control studies. Now, this was a 3 years project. I want to bring back the history. Dr. Homi Bhabha was living the last day, and myself and Dr. Mehta met him at the foyer near the staircase of the library. And Dr. Homi Bhabha, in his old typical Gujarati fashion, tells Dr. Mehta, Fali, we had asked for a grant for 35 lakhs at that stage. If they reduce even 1 naya paisa from the grant, reject the grant. I shall fund you. And he says, I'm convinced about what you are doing. And if need be, I shall provide you with an institute of that kind so that you can really change the situations in the country vis-a-vis habits, cancers, and so forth. Well, everybody knows those were the last words that they spoke to us, and subsequently we never had anything to do with Homi Baba. I might still mention the fact that when Homi Baba died, and during the same period of Lal Bahadur Shastri also died, I realized one of the comments made by the gardener here. He said that if that man was alive, that is Homi Baba, he would have given job to the all complete India. That was the way even an ordinary person was thinking at who Homi Baba is and was. It was in 1960s, everywhere you get a cancer registries. We decided to formulate a pre-cancer registry in 1966. And these were the needle of suspicion. I don't go into the details of it. This is a different field for all of you. But if you remember, we had a condition called oral submucous fibrosis, which is listed way below. But every time it was a leukoplakia or white patch that was considered important enough for all practical purposes. This is one picture on the left-hand side, which I might just mention was well done by Dr. Bhonsle, a very effective team member of our side. And there are 32 habits that you can see on the left-hand side. But if you really have to study, we study the habits in this country from Mizoram onwards to down. A catalog also may not completely do the justice. There will be more than 100, 120 type of variety of ways the habits occur in this country. So this is the essence of the variety and diversity of the country, even in the cultural aspects. And here I've written here, there is a much that is common, but also a great deal that is particular to each area. And that's the importance of the habits, and that's the importance of our studies in this country. So we decided to choose 5 different states in India and follow 10,000 people in a house-to-house survey to understand this situation. And these villages were selected by random sample study, so it was not supported by any logistics. So one village could be on one side of the game, other one another 40 kilometers away. We were not sure about the roads and all that thing. But this was done so that our scientific data will have a validity. We use this definition, ordinary definition, a morphological altered tissue in which cancer is more likely to occur than is apparently normal counterpart, a white patch, generally speaking. And that's a white patch. One may not realize that this insignificant looking patch into the cheek and can lead to serious consequences. But the next stage came up, how do we calibrate our doctors to study this lesion so that there is an equality of wavelength in discussion of what we do. Again, another bit to realize it, how we progressed. Those days, American Peace Corps people were working in India, and one of the person was working in Manchad district in Pune, near Ambegaon and Ghodegaon area, and he was being treated by Dr. Mehta at his office in Kemp's Corner. So he suggested that this is an ideal place. And we felt that would be a better place to go and figure it out whether we can do that. We went in, and I tell you very honestly, my experience of those days, going into villages of India, your contacts are very important, the first contact, which will allow us to help, because we are always in an unknown area, an unknown territory. And my experience is that always the first contact is with a Marwadi. Marwadi Seth. He looks up to the people, he's respected figure in the villages, and he goes all out to support all our activities for many other activities. So that's why we chose that area, and we did our pilot studies there of calibration of our team of doctors. This is another, similar type of white lesion that occurs on a brachial mucosa. It still looks innocuous in that sense, but these are file pictures at the moment, but that can lead to cancer and the malignancy and bursting out into the cheek. But initial pathway of progression can be a small lesion that you saw can go. That's the word. That's why it's important that you identify and recognize anything that goes right or wrong in the oral mucosa. Now, this is one habit which I'm touching the various habits, but this is one thing that I'm sure all of you must have heard of. These are mystery. In Maharashtra, is very common, where most of the lady servants or male servants who apply mystery or cleaning the tobacco, it can be like this after application. Subsequently, it can become like that, or you can land up into this situation also. So these are the progressive situation that is happening from a tobacco habit, but it is restricted to the site of application. We studied Bhavnagar district also. So here is I've used the word pipeful meditation because we all like to be tranquil in our life, be with anything else, maybe a cup of tea or whatever it may be. So these are the habits that cultivated. And here you find somebody is taking a clay pipe, and the heat of the pipe and the tobacco inside can lead to lesions in the upper and lower lip. And these are the kind of lesions that you saw, we studied there. And eventually it may, all lesion does not have to go into cancer, but this may. Now this is another typical habit which one gets with the BD. And you realize when you smoke BD, this is happened. This is a triangular lesion in the corner of the mouth. It's a butterfly effect. And you find that the lesion is there white along with some reddish area where there's also epithelium and so forth. But these are the kind of habit, these are the kind of lesion that we studied. During those days, way back in 65, 66 and also, the only thing that we studied in the pathology book or in clinical books of medicine was this habit occurring because of the smoking cigarette. There was never anything mentioned as to what does the different habits can do in a different part of the oral cavity. And this was never registered. But a BD can give you this kind of active lesions. And you can see I'm cutting out the scientific observations on the papillary eruptions and so forth. But this is all BD is creating a lesion in the cheeks, creating a lesion on the palate, or it can create a sort of a pathology on the tongue or the posterior 1/3, where you get a loss of papillae. These are all seen and recorded by us during that period of time. And we studied all that in different parts of India. And this can be superimposed by candida infection. And if you treat with fungus infection, candida infection, you might get relief. Now, having established some of these kind of white lesions and so forth, I've just put this picture on you to realize the value of the clinical study and identification of an early, so-called early, I can't say cancers can be early or late, but so-called lesion which is dysplastic in epithelium and leading to a malignant change. You saw in the corner of the lip, and you have written here the lesion is small, but the treatment gain is big. On the other side, we have this case from Kerala. We had a large studies in Kerala, and Kerala was one place where we went in too often because the people were very literate, effective, and there's a large number of pathology does occur in Kerala. And here we have written the treatment gain is nil. We could operate on him. And Kerala area, we worked in the districts only, Nakulam, Angamali, and so forth. But subsequently, we realized that whenever we identified a person as a malignant lesion or a lesion that is relevant, it was our job at TIFR in our research group that we would fly that person with somebody attending to Tata Memorial Hospital and get them directly treated or get them treated in the local areas. But the fact is, you can't do a screening and identify a person and tell him to fend for himself. You just don't do this because he's otherwise okay. He possibly is not suffering from anything according to him. So this is what we used to do. That's one of the strong strengths of our research. And then one another thing that happened when we went to TI for the field studies earlier time, in the villages we were not welcome because it was era of family planning. So when we move in, they would think that the government crowd has come for family planning and so forth, and were most uncooperative, would not believe us. And they would feel we're being a lot of money to do something. But when you see the Tata name on the jeep, it was broadly stamped, Tata, the doors opened up. The name Tata does make a difference even in the villages of India, even those years. So we were able to do. It's not easy to do this 10,000 people in a house-to-house survey and a follow-up and effectively produce the data. Now, this I have told you are indigenous habits in India. Now, I'm sure many of you might be aware of it. This is one habit which is practiced in Srikakulam, Andhra Pradesh in India, where the person is smoking reverse. and personally ladies, she is smoking reverse. And if you look at the folklore of that area, you realize that they smoke chutta but reverse. It's known as Adapoga in the area, Srikakulam. The folklore says that these ladies wanted to smoke. The men, being a fisher folk, go into the sea. They don't want them to see that they're smoking, so they would smoke reverse. Other thing, the gusty ends of coastal area would extinguish the cheroot, so they decided to put it inside. They want their houses to be clean. They didn't mind the ashes falling on the tongue. And secondly, they will carry the child in hand, and they don't want ash to fall on the child's face. Or so this is the folklore. Now, how does the ladies get into it? Because most of the time when they do this, they're working. It's like a good time. They would tell their daughters to bring up the chutta. And the vendor would give the chutta, knowing fully well chutta would get extinguished. He will light the chutta, give it to the daughters, the young girls from the age of 7 or 8, and they also start smoking. Result was they get used to the idea of smoking reverse, and we got pelletary cancers happening at the age of 20, 21. These are the kind of pelletary changes so we never saw such things ever. It was so many wide variety of figures that happened on the pellet that you really needed a great time to study each and every one of them to figure out how to make a diagnosis. To be very honest with you, we were not very happy with calibration, so we cancelled our first 6 months of our scientific study in Andhra Pradesh just to be on the strong track of our observation. But these are the bilateral changes. A wide range of precancers can end in a. Now, in a follow-up study, it's a 10-year follow-up study, we needed the white patch. Now, what happens to the white patch? Does it stay as it is? Does it go into cancer, or it can regress? Or it may recur? Surprisingly, with the same type of habit continuing, with no intervention by us, counseling and so forth, 21 to 42% of the white lesions regressed. That's the first time it was noticed and brought out openly in such a prospective study that a precancer can regress on its own in spite of continuation. Otherwise, there was a feeling that all precancer will lead to cancer. Here you can find a cancer growing within the lesion, and you can see it's coming out from the lesion that was sitting there. It's not coming elsewhere. It's coming within the lesion area, which understands it. The lesion itself gets transformed into a malignant pathology. Here are some of the follow-up studies from Kerala, where we understood leukoplakia in a way that we defined leukoplakia in 3 to 4 different varieties, and we were able to correlate the leukoplakia with a potential malignant change. Now, that was a necessary why the pictures were essential, because you take a biopsy from a small area, at base in TIFR needed to see the picture of the patient and be able to do the histology, because we do a small punch biopsy straight into the field directly. It is not such in a medical side where you have a large section coming through. So all the peripheral changes that's happening in the features of leukoplakia would indicate which is the area which is more potential for malignancy. That was the basis of these kind of studies, so that you pick up the pathology at a very early stage. Now, Professor Vahia had seen some of the slides and was quite impressed to the extent he said, where did you get the pictures? Because you are talking about those days in those years. There was one gentleman, Parsi gentleman in Kodak, he gave me a assurance that you will never run short of films. There were so many restrictions on those days, and we are thankful that he carried on. Subsequently, during the visit in US, I might just add this extra tidbits, Dr. Mehta and sir, he met one Land, Dr. Land of Polaroid. The Polaroids were just coming in. So we made that offer that your Polaroids have got a lot of conditions that apply situation. Suppose we use Polaroids in India with those conditions, the temperature 40, 45, would he like to try it out? How would the Polaroid film function? Without betting, he said absolutely yes. And he gave us 5 and 6 sets of cameras and promised an unlimited supply of the films. And we used subsequently the Polaroid. Important thing happened when you take a Polaroid, even the villagers got impressed because it's like a magic. Any technology which you don't know appears to magic for all of us. And this is what subsequently we started using Polaroids also. So many people will help us in getting our project, supporting our project in different ways. These appear maybe small, but these are quite important to do this kind of work. This is in Andhra Pradesh, the palatal cancers, but these are all documented follow-up cases of all our field studies. One thing happened that I told you that leukoplakia on its own can regress, but here you can see that regression of the leukoplakia, a white lesion regress without any intervention, without continuation of the tobacco habits. So regression. So in a very small sentences, we could, for the people at large or the doctors, we wrote these findings. The incidence of precancer lesion exclusively among people with tobacco, carcinoma exclusively among tobacco habitués, and all carcinoma originated from precancer lesion, because we found no single case of cancer coming in from person who had no habits, like there was no turnover cancers. And this is, we called it a kind of a bedrock or mantra of prevention. And we made this little slide. I'm playing with the words, but this is very important enough when you talk to the dentist and so forth. Precancer is where tobacco is and cancer is where precancer is. This was our story and we felt we were on the track. There's one other condition I'm sure all of you are aware of now in India. It's coming up so strongly, actively that you'll be surprised. There's a progressive inability to open the mouth. And this is basically related to arecanut. Arecanut has been in India for more than 2000 years or so forth. And we never heard so much of this condition. We went to the background of Charak and Sanjita also. There was never a mention of such a condition or description of a lesion like that, inability to open the mouth. But this was noticed by us at various times in our field studies. And the entire collagen deposition takes place all over the mouth, and you find that you can't open the mouth. There's a total restrictions. And I'm just showing you one protocol, our studies on these, not going to the entire field data. That we did this in Gujarat in 1966. And we saw only 16 cases of submucous fibrosis in 10,000 individuals, and all were females, every 30, no tobacco taken. But then we went back to the same area in 1990. This was a very eminent work done by our statistician, a very brilliant guy, Dr. P.C. Gupta, and Murthy and Bhosle and Dr. Sinor. All these young as a contribution of a large number of our group. And you can see what was written then in the papers. Overwhelmingly meant 97%. And 79 patients under the age of 35 years. This is fibrosis happening so big from 1967 to this was a transformation way back in 1990. And we back in 1998. And in our Dr. Sinor's clinic in dentistry, we did a case control study. And we found 164 cases of fibrosis. And we wrote at that time that this could lead to an increase in the incidence of oral cancer in the future. And oral cancer was basically associated with tobacco, a white patch. And suddenly we found that this progressive inability to mount was becoming a serious case when you started using a tobacco. And this is a mawa which you must have seen. It was the one introduction of pan masala along with tobacco. And this is the one we studied in Bhavnagar, where there were diamond polishing workers, hiragasu what they call it, would keep chewing the pan masala all the time. If you travel in India, you'll find all taxi drivers and everybody would be keep chewing this thing in a different form. And this is I've just given a description of mawa. And you can see the relative score was 106.4, but when you add with tobacco, it's 780 so far. I just mentioned the Borgia's law was a higher administrative authority in Vatican, and sometime he had issues with the people in there, and he did make some killing. It's known as the Borgia's law. I'm sorry. Indian market in pan masala then came to 120 when this was 1995. This was and during that period of time, I was asked to be visiting South Africa because our Indian community were extensively involved in these habits also. Nobody knew that, but they were using arecanut. Pan masala possibly not gone in. That was a time where we were we couldn't use our document to go to South Africa. But there, Professor Van Beek also found fibrosis, and he felt 2 cases of cancers in fibrosis without tobacco habits. That's what his observation was. Now, this is, of course, all of you know that right from Kashmir to Kanyakumari, this is a hoarding, this is a welcome garland you'll find everywhere. I called it a cautious for carcinogen. It is a seduction, but at the upper end. Now, cancer got rejuvenated with this new habit introduced. A good cancer shot in the arm. It's the changing pattern. Our studies brought out this changing pattern. We thought what was a simple study of tobacco, leukoplakia, pre-cancer turned out to be some more complex situation. And that's why by 2004, fibrosis came out to be a force to be reckoned with. This condition was an enigma for us also in 66. It was first observed in 50, or written about in 54, in Kenya by Dr. Schwartz, and in Indore by Dr. Damanlal and Joshi in Maharashtra. But it was an enigma to the extent nobody took it seriously. But our studies brought out this thing that it became a force to reckon with. Here is a 4-year-old boy, not with a slide by Dr. Hazare, who used to work with us. You can see the 4-year-old boy because the uncle would feed areca nut in that. There are enough examples, giving chocolates and other things, uncle would be feeding areca nut and so forth. There's no tobacco. And you had a fibrosis at the age of 4. Same gentleman after 16 years. Luckily, he doesn't have a dental issues, otherwise you can imagine what can happen. But this issue is far, far more prevalent than we realize it, because nobody has repeated the study that we have done it so far. During that Manmohan Singh period of time, when India was globalized, I used the word India is Gutkalized, and you started getting these Gutka pan masala going all over the world. And this is the aid world power, pan parag, and these are the, just play with the words, but this is the power of the aid world. Unche logo ke unchi person, and so forth. You all know this, gentlemen, but this is the power that has led to a situation where Gutka logic was very simple. Pre-cancer is slow, it takes years before you get the lesion with the habits. Cancer is still slower, transformation, but the kick is fast when you take this thing. And profits are, of course, faster. It's a rags to riches story for Gutka industry. And just with a little pun, and is chew now, cancer later, that was a game changer of Gutka, because that became a prominent factor for creating a fibrosis. And when the tobacco was added, fibrosis turning into malignancy became a next natural step. So business-wise for the industry, this is the ideal disease. And therefore, I can say that you buy SMF at Cancer 2. It's like 2 to 1, buy 1, take 1. Unfortunately, we all know this thing, but it's still actually a very prevalent habit and a very strong industry. Unless you have a political will to do something about it, it may not work out. And we can see further up, this is the house of Gutka in Pune. This is the gentleman who was in rags to riches story of Gutka. This is the whole. Now, when we do this pre-cancer, it's a very simplified thing. When you look at the deeper part of the whole thing, the truth is very simple. The nature of the habit decides the location of pre-cancer and cancer. It's like it didn't require a lot of effort to figure it out, that if you apply tobacco on a site of application, you will get a lesion there. Or when you get areca probability, you will get the generalized lesion all over the mouth. Submucous fibrosis is important. It entirely sort of universalizes the entire mouth, which means the cancer will occur anywhere in the mouth. But with tobacco application, the cancer would generally occur at the site of lesion. Here you find, I'm just showing you a few cases here, the cancer of a person. They're very difficult cases to treat and so forth. Here is on the tongue. You can see entire tongue has become bald. And on the lip. So if we saw anywhere in the mouth, it can get you cancer, or it can land up, if not treated. You can see these cases still, particularly in the field studies we saw there. But today also, you sometimes, once in a while, I do come across the cases which has not been taken care of. We had 30 years of work, 2 in the population, 7 Indian states in India. I might mention here, we had a big issues of to how to take out the tables and statistics and so forth, because we didn't have a computer. We didn't have experts in TIFR. Narasimha Rao and Maithili Rao came into picture, and then it was, during those days we had to do with hands, everything. But that's why I said dedication was there. And I was mentioning in the recently in the afternoon for coffee, the word, I used the word P. There was a passion for all our teamwork. Otherwise, this would not have happened. If you look at it, even the girls who were employed with us in our studies, who wanted to join us, knowing fully well, we had to go to washrooms and toilets out in the fields and the villages. Those were the days when they did from 66 to 69, those ladies, 2 doctors, that they worked. You have to work. You don't know where you're going to stay. You don't know when you're going to eat your food. We did work in the villages with that pathology. There's a lot of this publication, what you say, we have three of these volumes joined together. This is one of the books that is released by me and other 3 editors written, published by Oxford, London. And this is the 3rd one you see tobacco. We had produced 287 pictures showing the different morphological features which indicate the potentiality of precancer lesion. The book is still there. We sold it for only 75 rupees. For anybody to understand, appreciate when to take a biopsy and for where to take a biopsy. Simple biopsy doesn't make a difference. We take a biopsy of the wrong area. And of course, we had this, the early detection, the absolute on the extreme right is a small little 40-page little thing which explains to in practical reality how to go about it by every dentist. But as I told, we gave it distributed free to all the ENTs and all the dentists. Many other things came out of our TIFR research. I'm just mentioning briefly. For the first time in the history, that WHO Collaborative Center was given to a central, like basic dental research unit in TIFR. There was an argument at the government of India level in Delhi, when I think Professor Srikantan was with us, that the center must go only to the country, not to the sub-center, to the place. But Professor Sensward, WHO chief, just wrote down the list that on the chalk with the board and said quiet. So it's a pretty honor to be rewarded this. And we, besides this Southeast Asia, we had a lot of people from Australia, US and other coming in to study this pre-cancer thing. That was to me very distinguished recognition for TIFR also to be honored like that. And I might just say by side, those who were there in American European institutes sometimes wondered that TIFR is only an institute for medical and dental research, having not understood what TIFR is truly. So to some extent, I suppose we did added some value to TIFR also in our own manner. We were basking in the glory of TIFR, but we added some value to TIFR. I think that was the way. This Gutka ban in Maharashtra came only because of our study. We were the main side document. At that time, I just wanted TIFR to call a press conference and take the credit. The lessons learned, very simply, the biorealistically, oral cancer is not an effectively targetable lesion. Oral precancer, I'll go very briefly. Now we came to 3rd phase, intervention. That can I, with our method, bring out the tobacco habits to reduce the precancer to normal. Accordingly, the cancers will also possibly go down. Because we know the cause and cure for oral precancer. Here the tobacco road piggy bank of Bitla. Arecanut was the most innocent thing till we studied. And that time International Association of Research Cancer meeting at WHO in Paris, in Paris 1985, they put arecanut also as a carcinogen. How far it is true, to be very honest with me, I still will not be able to subscribe to that thought. And why do people tobacco habits? I'll just go very briefly with a study in Kerala. 48% picked up tobacco habits in Kerala because of the tooth problems. Tobacco does dampen the toothache as a counter-agent. This is a very fine study done by, reported by principal author Gupta and others, and Murthy. And you can find that the relative risk for particular type of nodular leukoplakia we have identified is 3,243, and the submucous fibrosis was unheard of, becomes the second one. So if you give up tobacco habit, as I've written there, you lose a habit, but you do win at the end of the day. And here are the just example of a regression of the leukoplakias with intervention studies. We use basic health workers in Kerala also to do this kind of work for us. Later, this was a new thing came up, that we found cancers happening in the people with no habits. It's a malignant punishment to habit innocent. You have no reason why this will happen. So therefore, like the absence of evidence is not evidence of absence. And we use a common sense approach because absence of absolute proof does not predict absolute absence of common sense. So in a scientific audience, we may not use the word tobacco causes. Because if A causes B, B must occur because of A, and B cannot occur without A. So, but for general public and for generally all speaking, tobacco is a prime devil for these kind of a thing. Here, nutshell, oral cancer is our limitation. Oral precancer is a holy grail. And this is a very simple thing, it can be followed, total clarity, and it's a wide one that, I mean, there's no two opinion on that. And I wrote a small little thing, that I used the word temporal role, time associated role, and prioritization of precancer, and indicating the reversibility of precancer and the absolute irreversibility of the fait accompli cancer. This is one thing that we must realize. It's a fait accompli oral cancer is absolutely irreversible. We have all the strength and the reason and the power to bring out pre-cancer to normal, but not cancer to any other thing. And all said and done, cancer is still a situation which possibly has no cure. Worrying about a fait accompli cancer is impotency on part of the profession, everybody. But you work on pre-cancer is very important for all together. You needed the paradigmic shift on oral cancer in Indian. It's like a penny drop. It was there. But all these exhaustive studies that we have undertaken, it proved beyond any reasonable doubt that you need to figure it out the way you take care of the precancers. Simple solution, but not being used. You can use primary prevention by removing the risk factors, easiest thing to do. You can just prevent the disease. It's a paradox. The most preventable disease becomes a serious issue all over the world, maybe more so in our country, where you find 5 cases of cancer happening in mouth and 5 in hypopharynx, which effectively put to 10 cancers a day in that area. Leukoplakia can be reverted. Submucous fibrosis is again irreversible. And that's unfortunate part of submucous fibrosis. You have a morbidity and inability of such a high order that you can't do much. And there's no cure. Etiology, again play with the words, tobacco and leukoplakia, so eat and be damned. I might just touch the social aspect of it on this kind of a presentation. Advertising created demand where none existed. Edward power at its zenith. This is still going on so strongly. I never silence it. All the medical dental profession, we are all very silent at these things. Philip Award function 2020, and you have a Philip media and corporate houses. The Times of India has unfortunately some other has always followed the path of making money rather than looking at the health of the issues. But this is the true thing that's happening. And most of our actors, you must have seen the advertisement by Vimal and all those things. Here is a triple power working out, and this is what happens. So how do you do about it? You have to explain to them. You can't be moralist. The people who take habits, you don't just condemn them, but like Jean accuse. You have to be suggest to be friendly. In these days, affluenza to change lifestyle is not easy. But it's important for you to understand the human nature of the people who take up the habits. We also take habits. So you have to understand, you can't accuse people. Doctors treat disease, but they also treat people. And this is where you come into, like, when you deal with a personal communication, like your Duryodhana dilemma. He says, Janami dharma nacha me pravrutti. I know what I ought to do, and jolly well I don't. This is the same dilemma existing with the people who have the habit. You have to be careful. You can't force. And Chanami Adharmam, knowing what I ought not to do, but still I continue to do it. So this is a kind of a dilemma. Now it is a part of the profession to deal with this kind of a human nature also. That's the only way you can succeed. Regression of the leukoplakia. Secondary prevention, which I just showed you, you can do this, and that might make a difference. Here, I still write this. I cannot accept the true association. 2 minutes. And cancer in tobacco. This is again an SMA with a habit. And here is squamous cell carcinoma. You can imagine how do you treat such person? Revisiting and challenge some norms, a shift from cancer to pre-cancer. And I call it attention deficit syndrome. It's so simple. You have to be aware, then you can get attended to. And then only your energy flow into the direction of doing something serious. But this attention deficit syndrome is so strong. This kind of work, what we have done, has never been duplicated. Nobody is following it up. And if I write here what Siddharth Mukherjee wrote a very book on Emperor of Maladies on cancer, the fear is the cancer. And its palliation is the daily task. Its cure is not possible. And you can imagine, you can go go backwards, you will find which medical disease has a cure. Majority of them are chronic. And therefore, when you try to cancer as a cure, you should rather be take as a palliative situation rather than curing. In reality, philosophically speaking, when does a patient ever become a person? Now, those days of mine were TIFR, they're gone. And this is when in Vanvas, Lakshman asked Ram, they went happy days with their mothers were treating their family. And Ram says this, those were my happy days at VA. At TIFR, as I told you, it was a P for passion that made our team work, and we were happy about it. And I thank TIFR for that. And I'm grateful to the team that worked for it. I couldn't get a better word in English for Kritagna. And I say grateful and obliged for all those in our team who did the disperform in our research. The word is Kritagna. I used it from Sanskrit. Both of Sarvanpati, Aham Kritagna Asmi. A lot of people in TIFR, right from workshop, Gadial and all that kind of things. These are grateful. And I'm grateful to you all for this patient gathering and inviting me to come over. I thank alumni group and the director for making me come. Thank you very much, all of you. Okay.
So much.
Microphone. Well, thank you.
I'm sure there are questions, but then please catch him at the free time and we can catch him. Okay. So now we come to the third speaker of this session, Dr. Arvind Kumar. So Professor Arvind Kumar, he is a PhD from Theory Group TIFR in 1969. He's a well-known educationist. He joined Homi Bhabha Science Center and after a few years became the center director. And he was the director during the period 1994 to 2008. For his contributions in the field of science education, he was awarded the Padma Shri in 2010. He is a fellow of the National Academy of Sciences, India, and is the recipient of several other honors and awards, including the TWAS Regional Award for Science Education. Professor Arvind Kumar.
Yeah.
Only this, not this point.
Thank you, Professor Shobna. And I'll be giving an overview of science education work at NVCSE. In fact, the amount of material that I have is very substantial. So I'll have to rush through. There is a large number of slides and I would have to rush through. But if you have any questions, I think we can discuss those during tea time. So let me begin. So probably some of you may not know, I mean, most of the audience would know, the origins of HBCSE. They started with some informal educational interventions by TIFR scientists. Then it started as a unit under TIFR in 1974, became a regular unit of TIFR from 1981, and it operated from a municipal school at near Grand Road for 18 years before it came to this present campus. And then there was a rapid expansion of its profile. A small hostel building came up, an Olympiad block, NIUS. Some undergraduate level program started from 2002. There was a major expansion in infrastructure. And an important milestone was the establishment of graduate school in science education as part of TIFR University. So with that, HBCSE became, it was always a unit of TIFR, but it was institutionally kind of integrally linked with TIFR in terms of, it was like on par with other national centers. This is the campus, new campus, the new NIOS building, the lawns and so on. So what's the scope of this center? The scope is science and mathematics education from primary through secondary, higher secondary to the senior undergraduate stage. And these twin objectives of equity and excellence, they shape our work profile. Now, equity and excellence, we don't mean that equity is at the lower stage and excellence. We don't mean that. These are not opposite ends of excellence or anything of that kind. They're they're two complementary aspects of the same goal, that is quality education for all. So you can have excellence at the lower stage and also equity at the higher stage of education. So there is no such distinction between stages. Equity and excellence are not with respect to stages, but there are two aspects. Equity is for universalization of science education. Excellence, one of its dimensions is subject excellence, but there are many other dimensions of subject excellence. There are six dimensions of work, as you see. Research in science and mathematics education. There are co-curricular materials. There is a very important project, Vigyan Pratibha project that has come up recently. The Olympiads, NIUS, and various other collaboration with other agencies. Graduate school at NVCSE, it operates as part of TIFR through an independent subject board. It's a very large number of areas with many perspectives, as we shall see. There are courses in cognitive science, learning theories, history and philosophy of science, etc., and also overviews of science disciplines. And one important point is there is a compulsory field work as part of the graduate school, I mean PhD requirements. Now, broad types of research at NVCSE, we have science and mathematics education research in the cognitive and socio-cultural perspectives, and discipline-centered science. You will get to know as I go along what all this means. But the first part is usually at school level, and the second part is usually at the college and university level, but there are several studies which cut across these levels. So it began with very extensive field experience in grassroots projects, and these are some of the names of the projects. And this early focus on grassroots work has continued to influence several research PhDs in TIFR ever since. So some simple remedial measures, almost common sense measures, were for these early projects were language simplification, active learning, and respect for student conceptions. And we found that they result in gains, and the most important thing is it reduces the gap between high and low performance. Now, I don't want to go through all these. They're almost common sense measures that any good teacher can anticipate himself or herself, but they're not implemented often. So we implemented them and found gains. These are some rural school. Now, student conception studies is a very important backbone of science education research, and the center actually pioneered these alternative conceptions. Now, what are alternative conceptions? They are actually incorrect in science, but they are universal, very robust, and in some cases actually have parallels with scientists' conceptions. And a very notable work was done on children's conception with a well-known group at University of Leeds. There were other learning barriers and remedial measures in chemical equations. And also more recently, there was a very interactive teaching sessions over a year or two. We got to know some insights on the middle school student, alternative conceptions and what is the sequence of concepts that one should teach at the middle school level. Now, the more, professional science education research, visual spatial reasoning is a very important area. As we all know, science often involves visual and spatial reasoning, besides, of course, conceptual and mathematical reasons. And this is basic to creativity of many great scientists, even no less than people like Einstein and Feynman and so on. They have attested to this fact that their original creative process they used to have visual spatial thinking. Of course, their later products are highly theoretical and they are not perceptual, but the discovery process is visual spatial quite often, not always, but quite often. And therefore, a number of significant research studies were done in astronomy, human physiology, DNA, etc. And the center got recognition. The member was invited to be the guest editor of a special issue on this topic in a very prestigious international journal of science education. A similar thing, analyzing graphicacy, graphs, figures, tables, etc. As we all know, they encode scientific information. And it's again a very important part of science education research to how to code this information and how to decode them. And there were studies in these regards. Design and technologies altogether is a very novel dimension of science learning. As we all know, technology permeates every aspect of human culture. And what happens, science, it's not that science can immediately give you a solution. It offers many solutions. So something else is needed other than science. And a very creative choice is needed to combine various elements to design a solution appropriate to the local context and taking into account the marginalized groups, etc. So this is an entirely new culture. In fact, many people believe this is a new epistemological culture. There are two cultures, as we all know, science and humanities, but now design and technology is emerging as a new third epistemological culture of humankind. So this is all very well known at the higher levels, but the innovation in HBCSE was to do it at the school level. And in fact, it has now been recognized all over the world that design and technology has to be right from the beginning. And even at the primary level, books are coming up at this level. This is a DNT workshop at HBCSE. Now, mathematics education. Mathematics education research at HBCSE, curriculum development and teacher, they are all integrally, it's not that first you do research, then you do curriculum development, it's not that, it's integrally connected to each other. And of course, mathematics education research, I must tell you, is an even more professional discipline and than science education research. Science education research as a professional decision started some 50 years ago, but this is even earlier, and some of the many eminent mathematicians are involved in this. So there's a lot of global research in this topic. And this was combined with common mathematic use, because in different work contexts, not just in classrooms, but in different work contexts. And of course, its goal is universalization of mathematics education. So these are some of the techniques. I mean, it starts with some remedial measures, and then the important thing in mathematics education, you take into account the teachers also, their own beliefs and their own pedagogic content knowledge, as it is called, and how the beliefs interact with these content knowledge, etc., etc. I can't explain this, it needs a lot of explanation, but this is what it is. One notable area was how to transit in 5th, 6th grade from arithmetic to algebra. And then is quite a deep topic of cognitive science and as applied to mathematics education. And the real problem is the symbolic expressions for children. And symbols, they have representations, there are procedural aspect of it, there are transformational aspect of it, etc. So all that has to be researched on. And there was one very interesting study on out of school mathematical knowledge from for very young age students. For example, some low income groups in Bihar and low income urban groups like in Dharavi, etc. So these insights were combined, and so what do they learn out of context? Not in the classroom, but out. They are dropouts of a. So what do they, or even if they are not dropouts, they are marginalized in classrooms. So they're in mathematics knowledge in their work context that can be used to support their maths learning. And several studies have appeared in very highly regarded journals. And there has been a recognition. I mean, this International Congress of Mathematics Education is a very prestigious conference of mathematics education. And India was invited, and one member of us on its panel, etc. And in fact, this book was produced as the first Asian resource book of research in mathematics education in India, and HBCSE member was a co-editor. This is a mathematics education workshop. As you see, there are students in the upper part of the slide, and professional development of teachers. All of this is combined to produce materials. Now, science education has a cognitive dimension. It has also a social dimension. It's a very important dimension. And first, of course, the most important thing is self-image and attitudes and aspirations and expectations. This is very low, even if the students are good, but if they're coming from certain backgrounds, their aspirations are low. They don't want to go beyond class 10. At most, the parental expectation, if they get through class 10, okay, that's fine. That's very different from the so-called privileged families where the expectations are very high. So that's one important point. There was also an interesting attitudinal survey of students. How do students view science and scientists? And very interestingly, Indians have a very positive image of science and scientists compared to, say, students in Scandinavia. They have a very negative image of scientists. So these guys are come and spoil environment and so on. But in India, there's a very positive image. It's a good feature. But the same survey, of course, shows gender stereotypes. And gender, of course, is a very important focus of many research studies. Another focus was this hegemony of English. And we all know this. I don't need to explain this. And just mere knowledge of English is regarded as a as meaning a lot of knowledge and wisdom and so on. So NVCC sort of worked on the fact that the multilingual character of our country. I mean, it's a myth, not among us, but among many people, that English is often equated to intelligence or wisdom and things like that. And therefore that stereotype has to be removed. There were two notable works in science and mathematics of the visually impaired students. Very interesting studies. You can see all these on HVCSE website. There are socio-scientific issues. There are issues that science alone cannot handle in society. Science, of course, is an important input, but some ethical interventions on the part of the society is needed. And this was done quite thoroughly in one study. And for example, the students' views on these matters are the very highly privileged science, but do not know the importance of ethical interventions in those, as reflected in how they respond to issues like surrogacy and genetic determinism, etc. So our work in science, social dimension is quite well known, and it was on the gender issues in NCF, one member was there. This is a modern construct. It's a modern conceptual construct of the same kinds of things. Identity. It is not only about gender and class, but it is also disciplinary identity. It's a very interesting issue, especially in physics education research. In the USA, it's being done at a large number of universities, that people develop disciplinary identities, and they almost think they have to behave in a certain way. And of course, its negative aspect is that right at school stage, you develop a negative identity. Well, I'm not meant for science, I'm not meant for maths, etc. So it's a very powerful determinant of expectations and hence scholastic performance. So scholastic performance is not just being, bright or intelligent. There are so many other factors that give scholastic performance. And there was another program, health education. I won't go into it. So very interesting and in fact very urgent program, where the student, first of all, you understand student understanding. I mean, you try to expose student understanding of these things, and then scale up your programs of intervention and so on. Environment education has been a recent work, and it's again a very interesting work in which, see, it has been made part of curriculum by the government anyway, but that hardly promotes actually ecological sensibilities. So a recent action research study was that you go to people who are actually doing that, environmentally conscious community, be part of that. It is called participant observer mode. You just you do the same things as they are doing. And there are methods of such analysis in sociology. And then you come back and you see what are their motivations and actions, etc. And that you have to analyze that. And using that, then the student who did this PhD, she implemented a participatory program in school students, in urban farming, and then found out that it does matter. And another study is going on waste as an issue around which this thing. So this I was talking about cognitive and socio-cultural aspect, but equally important is the other aspect, namely discipline centered. So far, I was not focusing on disciplines, but discipline centered science is a very important part of Homiva Center's research. Some examples I'm giving, there are many pieces of research done. I've just chosen a few. Problem-based learning in chemistry laboratory. So it's a well-known pedagogic approach. What you do is students are encouraged to solve not a typical textbook problem like it is given in usual chemistry labs, but a contextual problem and with graded level, etc. They are given reading material, they are given laboratory and asked them to solve the thing, read and try to find solution paths. They can get wrong, of course, because there are multiple solutions. And then the method is intrinsically collaborative. It's not just one person doing, but there are groups. And in HVCC design, what happened, the bigger group was split into smaller groups. They discuss among themselves, and then the smaller groups as a whole discusses and finds the solution. Of course, teacher is always there. It provides what is known as a scaffolding. I mean, it supports, and particularly in chemistry lab, it has to make sure of safety and so on. So there were some themes on which it was done and data collected, and it does show tangible gains. So this is a paper published in journals, etc. This is just a slide on the dyeing, etc. Now, student understanding of evolution biology is again a discipline-specific topic. How do students understand evolution? So this student, what he did was, first, he did a cognitive study of the actual original work. Of course, all the biologists know all this very extremely well, extremely technically on technical point. But what is the conceptual part of the origin of species? That was the first trend. And then he made surveys on students' meanings on this thing, and it was found what is sort of expected, that students' causal explanations of evolution is quite flawed. They actually introduce teleological elements, and teleology is not there in Darwinian theory, but students can't get out of this. The reason is because students easily understand artificial selection because there is an agency. But what is the agency of natural selection? This point confuses young students, although it's obvious to scientists. But this point of teleology, what is the agency of natural selection, confuses many students right up to the undergraduate stage. Do not think this is only children's confusion, but fairly advanced students also have these confusions. There's another technique called concept maps in biology, where I won't go into it, it's a bit complicated, but concept map means you ask the student to draw concepts and of a particular topic, let's say cell biology. So she will draw various things and connecting terms. And the point is the connecting, the knowledge lies in the connections. This is one paradigm of cognitive science, that the concepts by themselves are not enough. I mean, when concepts are linked to it, then that is when the meaning comes out. And therefore, certain things were done in school level textbooks, and there was interesting connection between linking words, the words used in higher text and the words used in linking text, and therefore it gives us a method. So professional biologists use very clear-cut economic parsimonious words, whereas students would not use those words, linking words, etc. Now, physics education research has been at a fairly advanced level right from the beginning at Homi Bhabha Center. And we first started with Galilean relativity. Later, it was extended to different themes of Einstein's relativity. And actually, this area of work has not been PE physics education research usually does not go beyond undergraduate level, but this is a bit advanced level. We did some themes of general relativity, not the technical aspects of general relativity, but some of the qualitative themes of general relativity, and found some very interesting ideas. It was published in this very broad journal, Physical Review PE, and very few work. Similarly, quantum mechanics. And another was the concept inventory rotation mechanics. So concept inventory is concept inventories by American Association Education Research. So we representation also mean even text. Text, diagrams, models, even gestures are key to the embodiment recognition. I'm sorry, I can't explain to you this very much. And even I do not know it as well as some other cognitive scientists. So, but this is a new paradigm. And it was used in a new thesis where the students are able to interact with vectors and they found gains if you do this. Computational modeling, of course, everybody knows it's an important thing, but there was an important piece of work as to how to introduce this in schools and colleges in India, because you can't, go full steam in computational model right in the beginning. So a kind of gradual design was introduced, because this is a very important topic with the importance of interdisciplinary sciences and so on, etc. So this is a there are conferences and seminars every 2 years. There are conference seminars. Their research publications have shown a marked growth in the last 3 decades. So HBCSE graduate school students and their mentors have published in the fairly reputed international journals like Journal of Research in Science and Teaching, which is a very high rejection rate and so on, etc. So in various journals, it has been, because that's a condition for PhD in homeopathy, as it is in TIFR. Also, discipline center science education research has.
People on Zoom are not able to see you. Can you just give me a minute?
Because of the internet.
Yeah, there's some internet problem. Okay. Yeah. So physics education research, chemistry education research, biology education research. So there are dedicated journals on these fields. For example, American Journal of Physics and the new journal Physics, Physical Review, Physics Education Research. There is a new journal. Physical Review has a name. And similarly, there are journals in chemistry and biology, Journal of Biology Education, Chemistry Education. So our discipline center research is published in these journals, and the graduate school students who are doing PhD, most of them, some of them have published in discipline center and some of them have published in this thing. And of course, we publish in resonance, current science, etc., etc. But the most important point about HBCSEs, which is quite unique for any science education center, is that we publish even in journals, not in science education, but actual sciences, the mainstream journals of, say, Physical Review or something like that. How has that come about? Partly, of course, some staff members personally do that, but it has come about due to a very important program, the NIS program, where the goal is to give practice, sort of research practice to undergraduate students. I must emphasize this is an educational program. This is not a research program. It's an educational program of motivating research students through research practices of professional scientists. So sometimes we use the word proto-research, but sometimes not proto, it's actual research publishable in mainstream journals. So that has been a very satisfying aspect of this program. But I want to conclude this research by saying that it is not just for research, because research at HBCSE is connected to other things, materials and this thing. So research is not for own sake, like in a proper pure research institute. Well, that's just their business. But it is, in every program, it is linked with materials and teacher professional development or field programs and so on. There's some conference, etc. Now I'll go quick. I think I must have, how much time do I have? You have to give me another 15 minutes. So one important product has been Homi primary science curriculum. So all the contemporary educational practices, all cognitive science, socio-cultural perspective, etc. It has all gone into this very nice product of Homi Center. These are the books from the center. And these are not approved textbooks of Government of India, but they can, they are model books which can be used even in new education policy. People can use that book. These are maths books. This is the whole set that has come about. And just some achievements from Homiva Center. Actually, we were on the National Curriculum Framework 2005, and we in fact led the teaching of science group there. So it was done, the focus group document on teaching was done by HBCSE with, of course, a lot of other members from HBCSE and outside, but the leadership was with HBCSE, and we have been in state NCRT books many years, etc. In NCRT books, physics, I must tell you that a very important innovation was done when they were developed in 1990s. More than 1,000 problems of physics were designed for that purpose, and this has gone on and on from that. There have been various additions, but those problems have stayed. So that's an important thing. These are the various NCRT and school. It is not only higher secondary, Maharashtra State Board, etc. It's books of that kind. There are co-curricular materials, many co-curricular materials. Right when we were at the old campus, several of these books were written by earlier members. They are excellent books. And there is a portable laboratory of mathematics as well as sciences. We take it to various fields, to tribal schools, to various other schools, to schools in Mumbai, schools elsewhere, etc. These are the co-curricular materials, some of them. I'm just showing a sample. There are a large number of them available in HBCSE. This is our school laboratory. This is the mathematics laboratory where students are mathematics teachers are being oriented to do mathematics laboratory. There are materials in Hindi because that has a larger reach. So these are materials in Hindi. These are all co-curricular materials. Expository science, there are two very important exhibitions. Almost 2 years was spent by a large number of HBCC members on designing these exhibitions. These are the exhibitions, Gender and Science, History of Science. If some of you have visited HBCSE, some years ago, it was all there on the campus. And now it is, I'm told, being digitized. And this lower part is actually the mathematical resource exhibitions, So it's gender, history of science, and some mathematics exhibition also. Astronomy popularization is always an indispensable component of any science popularization program. And the astronomy cell leader is the chair now of the National Astronomy Education of the International Astronomy Union. So this is a kind of international recognition, and the International Astronomy Union has selected India as one of its centers for joint IUP and HBCSE initiatives. So this is one sky observation session, etc. I want to spend just a few minutes on this Vigyan, a very important convergence of all that has been done that I told you. A major program currently at Homiva Center started in 2017. It converges all the cognitive, disciplinary, socio-cultural dimensions of the center. Again, something. Okay. So number of premier institutions across the country, NICER, and I think SAHA Institute and many others. I would not know this happened after I retired. So, but I know it's a very, very important program. And the output is some very, very nicely developed learning units. And those learning units are available for everywhere. Although the actual teaching is done only at select schools, but the learning units are universally available. Now, why is there some problem? Yeah, so these are the Vigyan Pratibha learning units. They have all the standard dimensions, and local context is built into them. And the implementation is through a science circle in a school, and a cascade structure has been built up that those teachers come to HBCSE for orientation and so on. And as I have said, it's a very important milestone in around which a lot of research, materials development, and field activity is going on. So I hope it goes on like that. These are some materials. This is a Vigyan Pratibha activity in some school outside HBCSE, some unit on evaporation which is being done, a unit on shadows, very interesting, and they're all available and you can see them on HBCSE website. It's a very well designed unit on shadows and how the length of the shadows differ from, see one part of the year to the other and time of the day and so on, etc. What is the point? I mean, why is it? No, this is not mine. No, this is not mine. Yeah. No, this is not mine. Yeah, this is yeah. Yeah. Why does it happen? Okay. Okay, finally, Olympiads. I'll be very quick because this is a very well-known program. Olympiads at higher secondary stage. Though it is higher secondary, it's actually very, very advanced. It needs a lot of higher level understanding, although that understanding has to be brought to the syllabus given for Olympiads and so on. It's a nodal center of all these different Olympiads. And its basic aim is to promote subject excellence and, of course, to bring honor to the country. And another collateral objective is that the teachers get trained because teachers come to the program. And it's a 5-stage program. I won't go into details. It is impacting large lakhs of students. And its most important feature is that it has an experimental component, which is not there even in the best IIT exams and so on. So I do not think there is any examination in the country which is, I mean, it's the highest level, the best level program for searching for excellence in terms of subject, because it has both theory and experiment. And even the theoretical problems are thematic problems. They are not the usual standard problem. They are problems woven around them. They take months to develop. So there's a tremendous effort in developing those problems. It's not a one-day job. It takes months, and several distinguished scientists help us in this program. Mathematics Olympiad, again, has been an even earlier activity and has been doing a great job of nurturing higher order talent and getting problems. Every country submits problems and then some of them appear in the final paper. And that is a very, very big achievement. And it has been done quite a few times by the mathematics cells. And there are other things going on there. International Olympiads, these are huge events, and HBCSE has hosted a large number of them. All I have given you this thing. As far as our performance is concerned, it's quite outstanding in many subjects, sometimes good, not outstanding. And many, as I have told you, many scientists are involved in it, but some of of course, the main nodal thing has to be done by HBCSE academic members. So that is these are some pictures from International Olympiads. This is the observation round of Astronomy Olympiad at GMRT grounds near Pune. They are assembling for the night observation session. This is Astronomy Astrophysics. This is an optical task developed at International Physics Olympiad 2015. It's a very brilliant task that was developed by the people who are involved in. Do you think I am told it's a kind of optical version of the discovery of DNA structure. So optical version of that experiment was designed, and hundreds of copies of these are needed because there must be 400, I don't know how many students participating in the Olympiads. So what do you do with those copies? Then they are distributed. And this particular task is there at all ICERs, NICER, various IITs and various colleges, hundreds of colleges, etc. So it has a benefit of that kind also. And same thing happens in chemistry. When chemistry we hosted in 2001, there were a large number of copies and then those materials were distributed at the copies. This India in physics at this, all the 5 gold medalists. This is a chemistry Olympiad student when we hosted in 2001. This experimental thing in chemistry is again a very, very challenging thing because the questions of safety, the material, the chemicals and so on are extremely important, particularly in these subjects. And it's quite a challenging thing to organize it for hundreds of students in a program. This is a chemistry Olympiad team in Paris recently, and various people have got medals, as you can see. This is the Bio Olympiad experimental task at, these are HVCSC laboratories. So by then we had developed, we had got the new infrastructure, so we got these things, etc. This is one Indian student at IBO, International Bio Olympiad, receiving gold medal, etc. The NIUS program, again, most of you know, actually it started with some homeopathy study circle in physics, which ran for 13 years, but then we made it national in all subjects. And it was greatly supported. Okay, 5 minutes, yeah, I'll try to finish. And I can't go into its details, but its basic point is to enthuse undergraduate students to go to higher careers, research careers in sciences, etc., through proto research or laboratory development and so on. So a lot of proto research goes on. These are various areas in physics and astronomy. Astronomy, we go even to GMRT and actually participate in the data analysis there, etc. with the students. The scientists have been very kind and courteous and very helpful in all these matters. And most NIU students have chosen research careers later. I'm told some of them, they are in TIFR also, I don't know. This is NIU's Astronomy Olympiad camp. This is a physics camp. Chemistry focuses on theoretical chemistry, interfacial chemistry, organic synthesis, etc., etc. Some of those are done by us and some of those are done by BRC and IITs, etc. A similar program in NIUS in biology. This is an NIUS program in biology. NIUS, some outcomes. The outcomes is large number of students are this. Just I want to emphasize that these are not just the bright, just some selected students from Olympiads. A few of them are there in biology, but physics, chemistry and biology students, they come from college students. They come from colleges and they come often from even non-metropolitan areas. So it's not an elitist program for just some very bright students, not at all. It is open to many students, and it's doing a great job at this. And a large number of projects are coming out, and a large number of actual publications. And there are materials coming out of this NIUS programs. These are the various materials. As I told you, nothing is just alone. I mean, it's always with materials and field work. This is a very beautiful problem manual for 33rd ICHO that we hosted. And I must say for completeness that it is not only NIUS. Another group is doing a similar work in biology, a work of different kind. They call it CUBE, Collaborative Understanding of Biology. And then they're doing it. I must mention it because that's an independent program of from NIUS, etc. We work for national and state agencies, various agencies we are working on, AES, etc. And various workshops we do. IGNOU, I must say there were very good quality materials brought out by IGNOU, in which we participated. And one important thing is the Vishwakosh, Marathi Vishwakosh project. It's a huge project of the government of Maharashtra, and HVCC has participated in it, etc., etc. And CEBS, of course, we participate, and More recently, we even have participated in Vigyan Vidishu program, etc. So that I think is well known. So I cannot conclude this talk with some observations of mine. And that will, if you just give me 3 minutes. So let me now, I was very hurried. Now let me say a little relaxedly. HBC is a unique center of the country where research, materials, field activities, student nurture, etc. are carried out often inseparably. It's also unique. No science education centers does science at both school as well as college level. You will find these at universities or you will find it at and some other places where they actually indulge in only school level activity. It's the only place where both things are done. And research in science and mathematics is now of professional class. It's, as I have told you, published. This is different from NGOs. There are a large number of very, very commendable work. I mean, NGOs doing very commendable work, but they are not professional institutes. So HBC is a professional institute in R&D. All the global insights of cognitive science and various other things are being put into our research. And equally important for content expertise in HBCAC, we have introduced these Olympiads and NIS programs. And I want to emphasize this is just as important as research. Of course, even under this, some research programs and PhDs have been done under content expertise. So whereas, so this is what I meant initially by equity and excellence. Equity excellence pervades both these programs, but Olympiads and NIS promote the value of high content expertise. This we have introduced because sometimes science education centers lose sight of this. And they do great work, but lose sight of the content expertise. Sometimes in HBCAC it has not happened, and that is partly because of the Olympiads. So to conclude, the field of science education research, sorry, I think just give me 2 minutes. Field of science and mathematics education is intellectually very important and very useful. It needs scholars with high competence. It needs scientists with kind of interest in education. So they should be content experts. But that is not enough. It needs also scholars with deep understanding of methodologies of cognitive science, history and philosophy of science. So it's a combination of both that defines HBCAC. One is not enough. Neither one nor two. Both 1 and 2, they are complementary and they together define HBCAC, and I believe I should define HBCAC. Thus, it is important that HBCAC continues to forge strong academic links with premier scientific institutions. In particular, I am saying the obvious that it is academic links for TIFR should be greatly cultivated. HBCAC finally is the science education center of TIFR. Its positioning must be greatly appreciated by people who are now, who shape HBCAC or in future will shape HBCAC. They should remember that the positioning of HBCAC, it is a science education of TIFR, dedicated to science education at all levels from primary to this thing. So its promise can be fulfilled. This is the last slide, that, subject content as well as pedagogy, cognitive and socio-cultural issues, lower and higher stages of education. They should be they should be thought of as complementary thing. They should not be thought of as opposite to each other. They should be thought of as complementary. And I hope center continues to, and parents, I must acknowledge, first of all, the names have not been given. All the photos are by HBCAC. We must remember Vijay Kulkarni and B.M. Mudgaonkar, who actually guided the center in the first 2 decades. And I must say, as a disclaimer, that this is an informal overview of work from my own perspective. It is not an official report or anything of that kind. And whatever I said as my concluding observations are my observations. They are not, have nothing to do with HBCAC as an official institution. And I must have omitted a lot of work in this very hurried review. So my apologies to all people and my thanks to all HBCAC colleagues and all well-wishers. And I thank TIFR alumni, Mayank Ohaya, and the chairperson who chaired this meeting. Thank you very much. Yeah, I'm sorry for delay.
Thank you.
Yeah.
Thanks.
We can now close it, I think. We can close it. Yeah.
Yeah, we'll take it. Okay, so this brings to the conclusion of this session with very wonderful insights into various aspects, computer science, oral cancer, and science education. So now I'll hand over to the alumni.
Okay. Thank you, Professor Shobana, for sharing this wonderful session. So this completes this part of the session. We are going to break for tea break now, short tea break, because after at 5 o'clock we will begin the lecture by Professor M. Krishnamurthy, and this will be a very insightful and very important in terms of future of TIFR Hyderabad. So I would request all of you to assemble here at 5 o'clock so that we begin on time. And so thank you very much for being here, and I also thank all the speakers and the chairman of the previous session. Thank you so much. Good evening and welcome to the final session of today. I request Professor D.M. Arora to chair this session, sir.
So the last speaker of the day and in the last session of this program, Professor M. Krishnamurthy, everybody in this hall I'm sure knows, but I will read out the handout. Professor MK is a leading expert on high power, high intensity, short pulsed lasers, especially in the laser matter interaction. He heads group at TIFR Hyderabad on ultra fast studies on laser matter interaction. Currently, he is Dean TIFR Hyderabad, and as Ravindra was saying, it is the future of TIFR. So, MK.
Thank you, Professor Arora. I'll try to be as quick as possible. And unlike the other talks we have had, I don't know what the definition of landmark here is, because we have got the land, we are trying to make the mark. But before I start, there are some people whom I thought we all should remember and acknowledge for sure, because they have contributed immensely, and there are errors already even in this 10 years. Professor Vengalekar was a pre-TCS before the so-called TIFR Hyderabad was born. He was a coordinator, getting the activities together for people to find what are the spaces where we can think of an activity for TIFR expansion, TIFR Hyderabad, which became later. And of course, Rajaram Nityanda, Sriram, Professor Chandrasekhar have been the center directors once the activity started. We had Director Mustansir Burma, who was right at the beginning, then Sandeep and Jairam now. Professor KVR Chari was really crucial and essential for this Hyderabad. Without him, I don't think we would have had the place, and it would have been very difficult to imagine the kind of things we can hopefully imagine. Krishanu was a very crucial contributor at very initial stages. Sampath Kumaran and Professor Pillai have been troubleshooters, whether it is trying to get people together or trying to fund the bills of whatever we have to do. We also had a saga of one principal secretary who was one of the most dynamic persons who said, you know, what are you talking about? You know, can you think of a place for 20,000 students? Why not? I mean, you know, like the big American universities. Why are you only talking about 200 acres? Why not 2,000 acres? So very emphatically positive person, Mr. Pratap Reddy, and it was his really crucial role to facilitate for the state government to do this. Two states, because the state went into division right at the beginning of as soon as our GO was signed, and then of course we had problems. 3 directors and 4 DAE chairmen, all of them supported this very well. And at July 2008, when we were looking for these places, we landed in Hyderabad, and the first steps took quite good routes. We could manage to convince the government that they should give the part of that land that was actually belonged to Central University of Hyderabad in the outskirts of their university, so that it was independent space which have our own access but contiguous to Hyderabad Central University, and that was a huge advantage. And of course, these things don't happen instantly. Even 3-minute Maggies, forget 3,000 minutes of Maggies required, maybe more. They have to convert it to the expression of interest has to convert to government orders, land transfers, and then the concept paper itself, whether we should have an institute of this kind of, I mean, I don't say institute, expansion of this kind for a second campus. This was the rough sketch I had scratched in 19th May 2012 when we made a presentation to the DAE PAC at Bhubaneswar, saying that, you know, we need some money to get going with
what could possibly become the second campus. And as you can see, the land actually came in 3 parcels, 4 parcels, but 4th parcel is still under dispute. So let's not count that right now. So this is what we call as plot A, which is 143 acres, 66 acres, and a 3.5 acre piece. And this is, believe me, the most prime land of Hyderabad. There is financial district, there is all the best of activities being planned and expanded in Hyderabad are in a very close circuit to us. This is what we had planned, saying that, let the big master planners come and make the mega plans when we have more permissions and approvals. We will go with the first unit at 3.5 acres. And, we had to give what kind of new things we will do. And we put lots of things together because the initial concept was pedagogy laser and NMR was the major activities. And if I may say, the Bakras who were in the run for this. And lots of other activities being planned, biology, physics, chemistry, interfaces, soft condensed matter, areas that we don't have, and so on and so forth. And all these got sort of merged, thought through brainstorm sessions, discussions with different groups in Bombay, Bangalore, Delhi, everywhere, whatever you can think of. And at the end of a lot of brainstorming, this was the vision plan that finally was presented. It talked about 3 things: unification of traditional disciplines and interdisciplinarity. Of course, this had been the strength of TIFR, and TIFR has been doing this, I think, essentially ever since TIFR took off. And we wanted to strengthen that because that is still something which is not that easy, that clear elsewhere. When you have people with physics, chemistry, biology, and put together, will they sort of dissolve each other or converge to something else? We know that how to do that, so we thought that is the best thing to do it. Convergence of fundamental science and applied science. We had this right at the origins. Today, last 2 days, when we heard like how different things had been happening in TIFR. So again, this is something that's not really new, but it's I would say, old wine in a new bottle. And because people, if you talk about translational research, resource generation, technical transfers, and blah, blah, blah. So there are all these nice new committees, new words that are being formed, but probably TIFR knew all this all along and has been doing, maybe forgot a little bit. So we thought that would keep us the emphasis. And then, of course, the possibility of synergy between teaching, research, and innovation, because more often we keep hearing that where there are students, there are no labs, and where there are labs, there are no students. So this was supposed to be a place where these things would come together. And then, of course, what kind of science we do. And quite frankly, it's very difficult to put TIFR science in any one particular way. And one of the attempts which seemed to have caught on and became sort of more acceptable or interesting was this concept of light, matter, and life with scientific computing and modeling in the middle. There are many people who say that if you talk about all these 3 things, and what else is left? But still, there are things we know that are, still have not rooted in Hyderabad for possible, not exclusive inclusion of them in this triangle and this circles around. The initial vision was eventually we will have 250 faculty, 2,000 students, 500 postdocs, and to be hopefully able to spend 2,500 crores in 10 years. And this is what we had dreamt about. And then, of course, we know that this is something that is going to be very big. It's not going to come in a day. We need to do this in a series of steps and timelines and what we can chew at any given time. So phase 0 was the initial plan to have a quick first building, not sort of be part of maybe the legacy of Bhava in terms of art, architecture, and the finesse and the sort of grandeur of the place, but something that we can get going, start putting the labs, start putting students and start graduate school programs and things like that. So we planned a small entity with about 25 different closely related disciplines that can be supported, 25 people, not 25 disciplines, but in these lead areas that we have been talking about, and then later expand research into new areas, new paradigms, create a contemporary facility for cutting edge research, promote new initiatives, and right at that time we were calling it TIFR 2.0. Then this started having first develop what kind of space, and there are a lot of, I know none of you can read this, but there are a lot of people who have claimed that they would be happy to come to Hyderabad, and their names and their labs are still there. Well, all this further moved on and to the good feel of everybody. In October 2010, Prime Minister Manmohan Singh laid the foundation stone for the new campus, unveiled a plaque, and we were really at the new beginning. We started working quite vigorously to convert that idea maps into more palatable building structures and layout designs. And this is the design that final layout that was finalized by 2009. And then we realized that, you know, with the DCACM and with the kind of things that we are trying to do, things may not go as fast as we want. So right at that stage itself, we thought like, okay, it's better to start rent a space and see how we can get going even before the buildings come. This was the, it took about a year and a half for the architectural work to be completed with all the details, BOQs, building designs, what have you. And June 2012, the beginning of what we call as the first research and teaching block, funnily acronymed as FREDB, because when I was writing taking the minutes of this meeting, I was lazy not to write this more than once. And then unfortunately that became the acronym in the DAE and everywhere. So as I said, we didn't wait for things to be completed. Right in December 2010 itself, in few months, we hunted out for a rental campus. And you can see here, there was nothing other than this building at that time. It was built for a managed hall, which was not going to take off anywhere soon because the 2008 recession killed most of the activity in that area. And then we got a very good space, which was not exorbitantly expensive for us to take. So we had a 4-storied building, about 10,000 square feet per floor, all for ourselves to be able to modify the way we want. It was just the shell initially, so we could completely change the way we want. And we did lots of things there. We built labs, but even before the labs, within very, very quick succession, we started taking, started activity there. But even that few gaps of months where, you know, things had to come, things had to move and so on. This is the nice narrative of Professor Nityananda. He was the only person in a 40,000 square feet place with one table, one chair and one computer. And he would have to go almost 8-10 kilometers to have a cup of coffee or a lunch. But very quickly, we started having different meetings, workshops, and things slowly started. Students started trickling down. And of course, the major change was we had Sriram come over as the center director. And so we started off very quickly the graduate school program in physics. By 2012, we had already a few students, and very quickly, as I said, you know, Sriram joined in VC, and there were a lot of early fast movers. In fact, it started getting to be called more of a soft matter physics place because the number of theoreticians and number of people who were interested in soft matter was so large that it looked as if we had planned it for soft matter physics, but that was not really intentional. And Sriram was quite clear right at the beginning, saying that, you know, okay, we have enough now soft matter, no more soft matter, no more stat mech. Let's start looking for people in other areas of physics, chemistry, and so on. So quickly, more and more people joined. We were hoping that the building will happen in a year or 2 years, because the rapid pace with which they did was so good, so fast, that we were feeling that we will not have enough time and building has to be vacant after getting completed without us occupying. But then the company that we had had its own financial troubles. Things got delayed, but that didn't deny us from doing whatever we wanted to do. More students, more groups, and the numbers kept growing. The marriage hall was converted to HPC, to an NMR lab, to a laser lab, to a chemistry lab, what have you. Anything that people were found interesting to be able to come and do, we did whatever we could. As you know, these are sort of clean rooms that actually stood the test of better than class 10,000, made out of no great engineers, no great consultants, just a few of us who started putting whatever we could put together from materials that we could think of at that time. So we had a femtosecond laser quickly in very quick session and installed there. And it's a 8 femtosecond ultra short pulse laser. And many of you will probably know that these are sort of very crazy machines which have to be tendered very, very carefully. And if the things are not very good, they won't work. But luckily they worked. And in rapid progression, the science progressed in the place. And well, that took quite a few years, 5 years. So we were there in the transit campus for nearly 5.5 years. And whatever I'm going to talk about the science is going to be what we have done in the transit campus and what we have done after that. So we packed all our suitcases, all our computers, all our lab, equipment, dismantled all the things that we and in about few months, we moved in trucks, maybe about 25, 30 of them, to bring all the equipment back to the transit campus. And by end of 2017, all of us were in the transit campus. And we did adios to this. And unfortunately, where we had the laser lab and the NMR lab are now a grocery store. So shifted to Fred B in 3-4 months, and more students. As you can see, this is 2017 symposium, and 2 floors was not enough. By the time we came close to this picture, which was maybe about a year and a half ago or a year ago, even the 3rd floor had to be sort of filled up to take a picture. So we have a decent facilities there now. Auditorium, of course, not of the class of Humibab Auditorium, but decent enough to house 150 people with all kinds of meetings. I thought some of these pictures would be good for those of you who have not seen, or of course, all of you are welcome to come, but if you've not seen it, at least this will entice you to come. Places where we can put posters, reasonably good gardens. Actually, if you see here now, this whole place is full of lot more trees than we had. There was not a single tree here at that time. And the new houses for some of the activities that was planned to be shifted. The National Facility of High Field NMR shifted to TIFR Hyderabad soon enough. And so let me now tell you what we have been doing for the past 5 years in the transit campus and the 2-3 years in the main camp, or 4 years in the main campus after we shifted. As I said, this was not a lock, stock and barrel shift, because people started trickling down 1 per year, 2 per year. And as people came, we started expanding whatever facilities that are required. But the theme was light, matter, and life. So today we have labs in really all the 3, a lot of interfaces, a lot of nice activities. And so 32 faculty as of today, 31 faculty as of today, 1 more to join. Lots of students, 146 plus around 80. Lot of visiting students, about 25 plus PhD students have graduated. More than 550 papers have been written by people who have their address as TIFR Hyderabad, and a lot of papers actually coming from the Narsingi campus, which was a temporary transit building, and the main building. Of course, I'm not going to expect you to remember all these things. And we have the 550 was not just a number to sort of say that we've been doing a lot, but there have been real spikes in the spectrum. A lot of high-end journals being accessed by people who have been tenured by their work in the last 5-6 years. What have you, PhysRevex, PNAS, Small, Nature Communication, Nature Materials, JAX, PNAS, Angevantishemi, that is the PRL of chemistry people, JAX, so on and so forth. So lots of different activities have been happening. And of course, as I said, this is interdisciplinary sciences. We don't have a department, but we don't even have a groups, but we see a progression of different sciences, how they intermingle. So we start with theory in computer science. We have people who works on interfaces of how, for example, a catalytic activity of how a gold can be used to break water, and all the charge transfer reactions that happen in molecular systems. A lot of material science, biophysics, conjunction, and also theory and computational chemistry. Smarjit is an expert in computational physics and soft matter physics. His favorite is glass transitions. He will talk about how non-equilibrium statistical mechanics can be used to define things which are not that easy to explain and progress in understanding. Prasad Parlekar is a fluid mech person, does a lot of computational work with biological physics and theory physics, like things like how bubbles change the whole dynamics of the flow, how having an active matter in a liquid changes the whole fluid dynamics and fluid mechanics of the system. Saroj is another stat mech person. He works on soft matter, bio, and glassy dynamics, how spins transitions happen, what is the relaxation time, how things go from one state to other without, and especially when things are complex. Kabir, some of you probably know, he was a PhD student at TIFR Hyderabad, Bombay some time back. He's another statistical mech person, soft matter, computational physics, how non-equilibrium behavior at low temperature scales change, developing theories for some of these rich novel physics that cannot be easily explained. I don't need any introduction to all, Professor Mustan Sharma Burma, to all of you. He is a professor emeritus, has been with us now since his retirement from TIFR. Of course, he continues to do the stat mech of different systems. Jagannath is a border between chemistry and theoretical chemistry and theoretical physics. He works with how small molecules get embedded in big molecules, molecular dynamics. He works with condensed matter physicists, how charge transfer reactions happen. Lot of pure computational chemistry, theoretical chemistry. Raghunath is another person who can be sort of somewhere in between computer science, chemistry, and theory physics in terms of quantum mechanics and so on. So he has this expertise in big data, artificial intelligence, to be able to churn out a few million chemicals for a particular property, how to retrieve properties from fundamental structures and so on and so forth. So he has this very nice MOLDIS program that is open for public use, and it's a very nice fun thing to actually go and see, because you can throw some molecule and then you can say, okay, sort out all the million molecules for dielectric constant or whatever. So from the science without matter to drift to the science with hard matter. This is a laboratory of one of the condensed matter physics persons there. He does spintronics, and he has built up a fantastic setup which can really create any really complex topological materials, devices that can be fabricated, tested to do things related to topological insulators, spintronics, and quantum technologies and applications. So he's been there now for more than 5 years. TNN is a material science person. He does again things which are related to how to generate electrons using light, how to store the energy in batteries, graphenes, MOS2, how to make devices out of them. And he's one of the prolific publishers with a really fantastic group working. Pavitra is more recent addition. He's a perovskites person, does interface between chemistry and material science and device making, trying to generate kinds of doped perovskites that are not easily available or a very specific technique, at least at this stage, and how to use them for solar cells, LEDs, transistors, and so on and so forth. Pranav is again one of the students of TIFR Bombay, Sanjay Vadavankar's student who graduated with supersonic jet spectroscopy, but he does not do supersonic jet spectroscopy anymore. He's building up a neutral atom scattering based microscopy. Of course, there is atoms and scattering, but not infrared spectroscopies or the spectroscopies that he did in his erstwhile thing. He also makes for some of these, there are very high wavelength controlled laser with a very nice line width that had to be made. None of these are available. So he actually has made, he's actually patenting it. And there are already companies which are interested in using his methods. He is setting up complete experiments to be able to look at catalysis from a fundamental perspective. For example, if a hydrogen lands on a surface with certain intermolecular energies like rotational quantum numbers, vibration quantum numbers, and the kind of rotational energy, molecular energy, does it stick, does it break, and what is the time that it takes, how does it break, and so on and so forth. Chaitanya is even more recent addition. He just joined about 3-4 months ago. He is actually expert in building lasers in a regime where the lasers don't exist. 4-micron lasers, 8-micron lasers, lasers that in this regime that can be pushed to femtosecond, picosecond, or CW depending on the applications. So he's raring to go. His lab is getting made. This is myself. I've been trying to do the kind of laser physics that we do here with 100 terawatt laser, but with only the 1 terawatt laser that I have. And we have found some very interesting ways of modifying a morphology of a liquid drop to be able to produce unusually large energy of electrons, positive ions. It can be actually now the emission strength and the repetition rate of the laser is large enough to be able to put a mouse paw and collect an X-ray with completely different kind of perspective. The beauty of this will be because the X-rays are not CW like what we get, but X-rays will be like sub-picosecond. So that one could exploit a lot more. We recently had Prashant Singh join us about 2.5 months ago. Prashant again was a PhD student of TIFR Mumbai. He worked with Professor Ravindra Kumar. He has worked in all the 5 petawatt lasers that are there in the world in all the different countries, US, Korea, Japan, whatnot. So he is setting up a new program on ultra-fast relativistic optics, how the electrons, as you push them to higher and higher relativistic velocities, how the whole plasma dynamics changes, how we can actually see them, how we can visualize, how we can optimize to be able to convert some of these generations into things that can be used for X-ray imaging, neutron imaging, and these are multimodal imaging because from one single source you get electrons, X-rays, protons, neutrons, and hopefully positrons when we have the petawatt laser. Chemical, not so chemical, because we have both people who can be characterized as pure chemical sciences people, but also, like for example, Kanchan, really we don't know where to put him because he uses fluorescence correlation spectroscopy. He's again a TIFR product. Sipta Maiti student left TIFR, worked in US for a while and then came back. He has built up more versions of the FCS that are now much more good at looking at real-time polymerization of molecules like fibrils, which are have a lot of neuro diseases that can be tackled. So he's both an instrument builder. He has his own biochemistry set up to be able to make expression of some of these proteins that are crazy, and how to use them with the things to do biophysics mostly. So, and all of you probably know Professor Chandrasekhar, who is our center director at the moment. And he and Anukul Jana are the pure chemists who builds molecules that are not there. Crazy complexes with metals and all kinds of things around into form cages, structures that are very unusual, very difficult oxidation states, to be able to stabilize silicon in a oxidation state that is normally not possible, or carbon in a state that is bonding with a metal, and that can be used for many other applications. Kalyaneshwar is another chemist who is not pure chemist, but a biochemist. If there is a hemoglobin with left-handedness, he wants to make equivalent of that with right-handedness. And there are lots of reasons to do this, a lot of interesting applications that one can think of. But just the idea that you can make really big macromolecular complexes to the design that you want, with L and D being switched over at your will. Ritesh is another new person who has joined about a year ago. He's another chemist, but with a lot of material science perspective. He how to build hetero molecular structures, which can be like filter carbon dioxide or send out H2 and so on and so forth. Very specific functionality to be able to create to matter. NMR group, all of you know the kind of NMR sciences that happens. The new addition here is not only the number of NMRs per PI, but also the solid state NMR. I think we have one of the really strong solid state NMR groups in this part of the world. And they look, of course, looking at protein structures, DNA, protein-DNA interactions, molecule structures. They're trying to acquire another big tool, the 900 megahertz NMR, and DNP, dynamic nuclear polarization, which is supposed to be one of the next big things that is happening in NMR. Chemical to more biological, we have people who are at the interface of chemistry to be able to create chemical stuffs to be able to crystallize proteins, but look at their molecular properties inside a cell and look at the molecular biology of this. So he has both a leg in pure chemistry, pure biology, and the interface between chemistry and biology. Kamal is a mechanical engineer who has become a biological physicist or scientist who looks at how the cell-cell interaction happens, how repair happens, how when we have a cut, how cells patch themselves up. And he does a lot of, uses a lot of physics, mathematics, and of course with techniques of microscopy and so on, and has been doing some fantastic work, which came in very nice journals. Apratim is one of the first, the so-called biologists we had, biophysics, a person who uses visible light microscopy techniques to look at tissue-specific differentiation, cancer development, and so on, genome organization, and so on. Adish is an animal house person. He uses, develops his own microscopy techniques, things like STORM, which will actually produce very, very nice image, high resolution images of things like neural synapses and how the sensory organs perform and their vis-a-vis the chemical correlations with synapses. Manish is a Drosophila geneticist who does a lot of molecular biology and regular biochemistry to look at things like mitochondrial biogenesis, neuronal health and so on. Ullas, all of you know, I don't need to say, he has now got a big home in Hyderabad, doing lots of stuff that he has started here and continuing with a lot more expansion there. Anish is another new person who joined about a year ago. He makes interesting molecules which can light up any part of the cell and organelle to make it visible for people to see functionality, applications, and so on. Mrunal is another person who joined less than a year ago. She's how the DNA repair and DNA breakdown happens. She uses a lot of radiation related things, how these things affect the system. So it's a quick run of all the different things that people have been doing. And as I said, you know, it's a very dynamic place. Everybody is excited to do things, and also, of course, you'll hear how they want to be more pushy to push things to take it forward. Lots of things on the kitty already, and going forward. Not only we have, as was the plan, you know, it's not only just pure science and research, but also something that can go more towards technology and innovation. And luckily for us, Rajiv, who was here, you know, there was a Newton-Boger science program that ended, and then with a sort of serendipitous extension, we came upon this Extreme Photonics Innovation Center that was funded by UKRI. So it's a joint project with TIFR and RAL. Basically, the aim is to develop next generation technologies for laser-based accelerators. So we have almost 20 people working in different areas of how to produce the new age targetry thin films, which are like designed to 500 nanometers, 10 nanometers to a micron, but 2 kilometers in long. You know, these are things that you normally don't hear because it may be 1 inch piece or 5 millimeter. But we are talking about 2 kilometer long films that are very nicely designed. And there are lots of TFR people like Achanta Prabhuji, who is part of this activity. We have a detector stream, we have a control system stream, we have people who are working on mechanical engineering to be able to how to make optomechanics for this very large lasers, because you're talking about a 400 kg optic which has to be controlled and very precisely in vacuum without much of a jitter between vacuum and out of vacuum. We right at the beginning of TFR, the idea was to start a petawatt laser program, and we wanted to coin a name when Dr. Vyas was going to come and inaugurate it. Traditionally, all the big lasers in the world in US were named after Shiva, or the third eye of the Shiva, because people felt at that time this is the only thing that can come into close comparison. So Shiva was already taken, Trident was already taken. So we came up with Trishul, which is TIFR research infrastructure for studies in ultra high intensity, ultra short lasers. So more than a normal imagination that we needed. But so the Trishul is coming up. Agmira is another new program that is raring to take off. This is advanced research on metabolism, development in aging, how people, when they eat, where does the body mass come from? And what should I eat to build a particular muscle? Is there a scientific basis, and what is the genetic basis for the Indian diaspora? So these are the kind of things that they want to do. It's a close collaboration with BRC, almost like the joint center. Hopefully, it will develop into a very nice program. We have right at the beginning itself, science communication outreach that has been part of the system. We have a couple of people who have been helping us out with conducting visits with the students, with programs where we are going to the village schools or to even Tata Institute of Social Sciences to be able to teach to a journalist the basic physics or things like that. So that kind of activity has been going on right from the day one. And 2019, of course, we had the TIFR Hyderabad, the DPR got approved, 890 crores, but then the pandemic came, a lot of things became gone to a halt. Not that the work stopped, lab didn't stop, the activities didn't stop, I'll show you, but we want to go with a new beginning, and we started after the pandemic with having Baba Banyan being planted in TIFR Hyderabad with two directors, the founder one and the director and the present. So apart from, so very quickly we finished off all the space that we could think of there, and as the programs required, like, somebody wants to start animal house based research, we don't want to say no to him. At the same time, we don't want to wait for 4 years. So what we did was, this is the 3.5 acre piece, and this is the 40 acre piece. This is right at the beginning point of this. It extends to another 1 kilometer at least. So what we did is we carved out about 4.5 acres of this place and started putting things. And these are two hostels that have come up right in the thick of the pandemic. Each of them got developed in about 6 months. In about 7th month, people are already actually staying in the hostels. So there are 2 hostels that are already up. 100 students are sitting there. And the Google is not able to catch up with us, because otherwise it should have shown a 3rd hostel already. This got cleared about 3 months ago. And next month, the students will actually move in. In February. January to be completed, February students will move in. So we have 2 labs that are already built, and the panel that Ravi was showing didn't show up again, because probably the picture was taken about a month ago or a month and a half ago. So today, if you come and see, it is actually a lot different. So this is where we have the animal house and the bio labs. This is the physics and chemistry labs. This is where the pathology lab is going to come. These are the hostels. They're reasonably good looking and quite functional, and all the students are happy. So to have 100 people with almost 0 complaint is not bad situation to be in. These are typical rooms of a hostel. These are the new bio labs that got occupied. I think about 4 months ago, we opened it, and then it's full on. This animal house that has already been made, 2,800 square feet animal house, completely tested with air conditioning and everything. The first shipment of the cages for the animals have just about arrived in. So in about a few weeks, we should be able to have the animals move in. And I don't think we'll have a housewarming ceremony for them, but this is the Pedagogy block. What Ravi showed was the bare structure. This is the first architectural impression of what it is likely to be. It's not finalized yet. In the next few days, we'll finalize it to build a facade rather than along with the structure. So new beginning also has been made with the architectural work, as Jairam had already said. Just about 10 days ago, we had the INI Studios had the first kickoff meeting. This is their first impression. This is, of course, not the final one. It looks quite crowded, but it's this is when we have the full money to develop the full place, and the total amount of space that we can develop is close to 85 lakh square foot, and it took us 10 years to develop enough to be able to occupy 1 lakh square foot. So a lot more to do. This is another impression of the architect's work right now. Thank you. I didn't show it here. I didn't bring it here. So there is actually like given a walkthrough. Since it's of course not the final, but it's the preliminary version. I thought it may not be necessary to show it. Did I take too long?
On behalf of the chairman, Professor Aruna, I thank you. And I also thank Professor Aruna for chairing this session. And MK, this is a wonderful trip that you took us all to do. And he has really done a commendable job. He was building the hostel, just amazing. So now we are through with this program. So now I request, no, no. Now I request Professor G. Ravindra Kumar to say a few words. Yeah.
Just a few words. Thanks for all the patience that you have displayed from the time we conceived this program. And I think on behalf of all of us, on the TAA committee which organized this, your support has been great, but we expect much more. You know, dil mange more, as they always say. So the association, two events, GS 15 2019 and this one, but there's so much more to do. And this is the first time we have actually engaged with the alumni. We didn't even know the email addresses. So that was a pathetic state we were in. Now we are on much firmer footing. So please get us in touch with more people, stay in touch, and also send money and tell us where to find more money so that we can have more such events. And I think the engagement has to be much more, well, this is, well, I don't want to give speeches at the end of this, not a homily, but I think we are at a time when we need a lot of guidance. Times are very challenging in multiple ways. The situation has changed in the country, elsewhere, science has changed. Preeminence cannot be taken anymore for granted. And the governmental policies are certainly not, they don't seem favorable. In fact, science itself seems to be in some sort of, the view seems to be one of, I wouldn't say, let me put it politically correctly, not so favorable. More emphasis on what can you give me tomorrow. Fundamental research of the type that yields long-term dividends doesn't seem to find favor. And the winds are changing, and how to withstand these winds. I think we need a lot of guidance from the alumni, from the experiences that you have, and also get us connected with people who can make a difference. And the uniqueness of TIFR that has come through in the last 2 days somehow has to be preserved. I mean, initially we had a giant in the form of Baba. We can't expect such giants to come every often. I don't know, probably once in a century somebody like that comes. But what kind of vision, guidance can we take forward? And while it's presumptuous to say what the future will be, great people, we should continue to recruit and give them free hand. That has been Baba's policy. Maybe we can continue that. And I also think this is something that we have got, many people have talked about, that TIFR should become truly international. We need international faculty, international students in the new campus with beautiful hostels, Gachibowli, high-tech city infrastructure that you can generate. I think we can attract a lot of people to come from abroad, spend long times here as a start, and maybe stay on as faculty. So I think we should become something like that. And we need more help in getting all these ideas forward. And we need certainly more help in retaining and nurturing our autonomy. And I don't know how it will happen, but it has to happen. So thank you very much. And I leave it to Prabhu to do the great job of thanking once again.
Thank you, Ravi, for such a nice, wonderful observation and your guidance. And personally, I wish to really thank Ravi and Professor Vaya, both of them, because I took this responsibility and completely inexperienced with this, but it is because of their constant push, guidance, that I could get all this thing through. If there are any mistakes or there are a lot of inconveniences which occurred during this, so those glitches, I sincerely apologize for that. I know that some of the people painted their names and the tags were not there, but I'm really sorry for this. बड़े बड़े शहरों में हंसे हादसे होते हैं, छोटे छोटे हादसे, whatever. So with this I will come to the end. So first of all, this is a very wonderful get together. We are now towards the end of this, and it is my pleasure and privilege to thank all the people who made this possible. I first want to thank all the generous support of these various companies. For example, Amplitude from Advanced Photonics, Laser Science, Wraith, Coriolis, and many individuals who paid very generously for this. Then we wish to express our gratitude to the director TIFR for his very generous help and the entire administration of TIFR for their enthusiastic support. We thank all the speakers for their wonderful presentations covering 75 years of TIFR's adventures in their respective fields, and it must have been a Herculean task for them to summarize this in such a short time. But all of them have done a wonderful job. Many of those things, I knew those people, but I didn't know the background, and now I can see I'm much more enlightened, much more educated. I'm sure this the same sentiment was shared with me by many people here. Now, I wish to thank especially Mr. Kishore Menon and Miss Snehal Sawant. They have done a really wonderful job. Can they come on the stage? Kishore? Okay, and Snehal? Snehal is outside? Okay, I think Snehal is outside. But Kishore, please.
Fantastic.
Fantastic. Thank you very much. Thank you so much. He did a wonderful job. He really did a wonderful job, and all the time he has been because we have been busy, and we just tell him and he just gets things done. So even okay, Sneha, let's come.
Word about what you do.
So Snail did all these arrangements and many of these printing and everything. So thank you so much, and all the volunteers team that you and Menon Saab is actually they actually supervise. So thank you very much from all of us. And also I wish to thank the central services, the auditorium, gardening, canteen for such a wonderful, nice food, transport, security, PRO office, and the registrar's office. So thank you very much, all of you, for all this help. Thank you. And now we hope to see you again in 2 years in Hyderabad. Where is MK? Yes, so MK, we had some discussion and he has agreed. So we will hope to see you in 2 years in Hyderabad to discuss the future trends and perceptions, whatever, of the activities of TIFR. So that will be the future of TIFR. So thank you very much, all of you, for coming in from all the way. And on behalf of TA and TIFR, thank you so much. Good night. Jai Hind.
चलो हो गया सबको थैंक यू बोलना चाहिए एक पार्टी करना चाहिए पार्टी फॉर ऑल
करेंगे सबको
अब तुम्हारे सवाल